Hello everyone and welcome to today's video on artificial intelligence at Intellipaat. Today, we will introduce you to the fascinating world of artificial intelligence. Artificial intelligence or AI is a branch of computer science that focuses on creating intelligent machines capable of performing tasks that typically require human intelligence. AI systems can learn, reason, and make decisions based on data. There are various types of AI. So let's start with the narrow AI, which is also known as a weak AI. Narrow AI is designed for specific tasks such as voice assistance, image recognition, or recommendation systems. It operates within predefined boundaries. On the other hand, general AI aims to possess the same level of intelligence as a human being. It can understand, learn, and apply knowledge across various domains. However, general AI is still largely a concept under development. AI has a wide range of applications in various fields, including healthcare, finance, transportation, and entertainment. It can help in diagnosing diseases, predicting stock market trends, optimizing transportation routes, and creating a virtual worlds. As AI continues to advance, it creates numerous job opportunities. Roles such as AI engineer, data scientist, machine learning engineer, and AI researcher are in very high demand. Companies across industries are seeking professionals with AI expertise to develop innovative solutions. In terms of salaries, if I speak, AI professionals often command high pay due to the specialized skills and demand in the market. The exact salary can vary depending on various factors such as job role, experience, and geographical location. However, AI-related positions typically offer a very high competitive compensation. As AI technology progresses, the future holds even more potential for job growth and exciting career opportunities. Now, before we move on and learn more about artificial intelligence, I request you that do not forget to hit the subscribe button and click the bell icon. So we are going to start our session with what is artificial intelligence. Then we will discuss how to make a career in AI. And then we will discuss life cycle of deep learning project. Moving ahead, we will discuss what is generator, motivation for neural networks, and what are the phases of neural network. Then we will have a thorough discussion on what is a single cell neural network, what are deep learning frameworks, and what are different types of framework. Moving ahead, we will have a thorough discussion on what is scaling, what is gradient descent, and then we will have artificial intelligence tutorial, and at the end we are going to conclude our session with interview questions and answers.
Artificial intelligence has revolutionized the way people think, learn, and work in various fields from finance to healthcare and mobile apps. What's more interesting is that AI plays more of a role in our daily lives than we can imagine. From Siri and OK Google to various virtual player games and social media apps, AI is everywhere. It sure is the most happening topic in every business right now. It is the most wanted and exciting career domain right now in the market. Artificial intelligence or AI uses intelligent machines that build in a way that they react like humans. The primary process involved in making these smart machines is to carry out decision making, which analyzes and uses data available in an enterprise. It is similar to the human mind absorbing and synthesizing information and providing the required decision. So how does an AI work? AI systems work by investigating large amounts of data labeled training data, analyzing the data for correlations and patterns, and using these patterns to make predictions about future states. In this way, a chatbot that is fed examples of text chats can learn to produce lifelike exchanges with people, or an image recognition tool can learn to identify and describe objects in images by reviewing millions of examples. AI programming focuses on three cognitive skills: learning, reasoning, and self-correction. Learning processes. This aspect of AI programming focuses on acquiring data and creating rules for how to turn the data into actionable information. Reasoning processes. In this aspect of AI programming focuses on choosing the right algorithm to reach a desired outcome. In self-correction processes, AI programming is designed to continually fine-tune algorithms and ensure they provide the most accurate results possible. So there are four types of artificial intelligence. First, we have reactive machines. These AI systems have no memory and are task specific. An example is Deep Blue, the IBM chess program that beat Garry Kasparov in 1990s. Then we have limited memory. These AI systems have memory so that they can use past experiences to inform future decisions. Some of the decision-making functions in self-driving cars are designed this way. Theory of mind is the third thing. It means that the system would have the social intelligence to understand emotions. And finally, we have self-awareness. In this, AI systems have a sense of self which gives them consciousness. Now let's see what are the applications of AI. One of the best known healthcare technologies is IBM Watson. It understands natural language and can respond to questions asked for it. AI can automate grading, giving educators more time. It can assess students and adapt to their needs, helping them to work at their own pace. AI tutors can provide additional support to students, ensuring they stay on track. Banks are successfully employing chatbots to make their customers aware of services and offerings and to handle transactions that don't require human intervention. AI technologies are used in transportation to manage traffic, predict flight delays, and make ocean shipping safer and more efficient. That's it about artificial intelligence.
First of all, we shall go ahead and talk about AI as a career domain. Since the last few years, artificial intelligence has grown in popularity. With the inception of tools like ChatGPT, Bard, generative AI, people are talking so highly about artificial intelligence and things it could do. Not only that, the research for putting AI to use has been going in almost all possible sectors of businesses. It's kind of a trend of recent times. Almost all organizations of different scales are leveraging AI to gain insights from large amounts of data, to automate their processes, to enhance their decision making, and to improve customer experience. As a result, there is high demand for skilled AI professionals who can design, develop, and deploy AI solutions. According to various reports and studies, the job market for AI professionals is projected to experience significant growth in the coming years. For example, a report by Indeed indicated that job posting for AI-related roles have seen a substantial increase over the past few years. India Times has reported that there are almost 45,000 job openings in the domain of artificial intelligence. What that suggests is there is huge potential in this field. So now the question is, how do you approach this journey of becoming an AI expert and secure a high paying job? Well, let us answer that question to you guys with the help of step-by-step process that will help you reach the goal of yours. First step on our list is understanding the AI landscape. As with any career path, it's crucial to have a solid understanding of the career domain. In this case, the AI domain. To be specific, AI is a huge field which involves multiple subfields such as deep learning, big data analytics, data science, machine learning, computer vision, robotics, natural language processing, etc. There are different jobs available across all of these subfields. So literally speaking, you won't actually be dealing with AI as a whole. Instead, the job that you will get will be related to the subfields that we discuss right now. So read details about these subfields. Evaluate which part of AI interests you the most. Now focus your attention on that one particular subfield. Look into its career prospects, current trends, and the big players in the market. Attend a few online webinars to gain insights into what's new going in the field. By doing so, you'll have a bright idea about the current AI landscape, and ultimately, you'll be better equipped to make informed decisions about your career path. Now that you are equipped with the AI landscape, it's time you start entering into the learning phase. First thing we want you to do is revise mathematical concepts. Remember, most of the AI deals with learning from data to develop intelligent machines. And mathematics, or to be specific, statistics, is the ideology that drives this process of making sense of data. So it is increasingly critical that you cover statistics. If you have completed the first few years of college, you already have learned all of the mathematics required. Yeah, you heard me right. During college, all of us have already learned terms such as normal distribution, mean, median, variance, calculus, linear algebra, etc. You just need to recall all of that and touch upon a few more technical terms down the line. Once you are done with that, you move on to the next learning step, that is picking up Python programming language. Python is the most used programming language in the domain of artificial intelligence. All the subdomains that we talked about earlier have been quite awesomely integrated or rather implemented in Python programming language. Hence, it is critical to learn this programming language. Begin with the fundamentals of Python programming. Familiarize yourself with the syntax, data types, variables, loops, conditional statements, and functions. Try and master the concept of object-oriented programming in Python. Learn how to use classes effectively, and then dive into the rich ecosystem of Python libraries and tools for AI and machine learning. Start with basic libraries such as NumPy, Pandas, Matplotlib. Experiment with data frames, learn the difference between them and arrays. Create different graphs with Matplotlib and gauge how graphs are communicating the data. Consider this as important step because graphs are going to be very helpful when you perform exploratory data analysis. You can also look into the Seaborn library framework. Also, if your interests lie around something like data analysis, business analysis or business intelligence, you could also try your hands on R programming language. Alright, now the next thing on your path should be learning how to work around data. Data is actually something that fuels the field of artificial intelligence, be it data analytics, data science, machine learning, natural language processing, or computer vision. Everything requires data. You need to have a clear picture of which subdomain you want to go ahead with. However, irrespective of that, it's better to learn how to clean all different types of data available out there and make sense of them. You have already learned NumPy, Pandas, Matplotlib, and Seaborn. Now using those learnings, you can import any dataset into your programming console. Then you can begin with learning different steps of data preprocessing. This process involves removing incorrect or irrelevant data, checking for missing values if they are there, perform row deletion or value imputation. Next, check for data completeness, removing duplicates or producing important values such as mean or averages. Here, you basically take in the raw data and convert it into something that can be fed to the artificial intelligence algorithm. Now the next thing is listening to what data speaks. Once data is cleaned, it's time you use Matplotlib and Seaborn to visualize the data. You can use multiple plots like bar graphs, scatter plots, and pair plots. Graphs will provide you with insights into the relationship between output variable and multiple features in the dataset. And if you're interested in big data analytics, you should go ahead and learn tools such as Apache Hadoop or Spark. These tools can help you churn huge datasets and find insights into how to drive business decisions based on the data. After that, the next phase is quite interest specific. You should pick up upon the subfield that you like and master all the important stuff that is necessary for you to master that particular subfield. Let me cover the overview of all the subfields one by one. First, data science. You'll have to learn many things if you wish to become data scientist. Your learning journey will begin with data exploration, data visualization, and statistical analysis techniques using libraries like Pandas, NumPy, and Matplotlib. Then go to the core topics such as feature engineering, model evaluation, data scraping, deep learning, etc. Next we have machine learning. Machine learning is at the core of AI. Understanding the concept of supervised and unsupervised learning, regression, classification, clustering, and dimensionality reduction is essential. Familiarize yourself with popular machine learning libraries like scikit-learn, TensorFlow, and Keras to implement and evaluate machine learning algorithms. Third one is deep learning. Deep learning is subset of machine learning that focuses on neural networks and has revolutionized the AI industry. You will have to gain expertise in deep learning architectures like convolutional neural networks, recurrent neural networks, and generative adversarial networks. Hands-on experience with deep learning frameworks like TensorFlow, PyTorch, and Keras is crucial for building complex AI models as well. Then we have natural language processing at fourth. NLP is a crucial area of AI that focuses on enabling machines to understand, interpret, and generate human language. Familiarize yourself with NLP techniques such as text classification, sentiment analysis, named entity recognition, and language generation. Gain hands-on experience with popular NLP libraries like NLTK, Spacey, and ZenSim. Next up is big data technology. We already have talked about learning big data. AI applications often require handling large data sets, making knowledge of big data technologies essential. Learn technologies like Apache Hadoop, Apache Spark, and Apache Cassandra to process and analyze massive amounts of data. Familiarize yourself with distributed computing, parallel processing, and data storage techniques to handle big data for AI applications. After that, we also want you guys to learn something out of AI domain, that is cloud computing. Cloud computing has become an integral part of AI development. It is critical that you familiarize yourself with cloud platforms like Amazon Web Services, Microsoft Azure, and Google Cloud, which provide tools and services for building and deploying AI applications. Understand concepts like virtual machines, containers, and serverless computing to leverage cloud computing for AI projects. And finally, we have model deployment as a critical skill. You'll have to learn techniques for deploying models as APIs, containers, or serverless functions. Understand model versioning, monitoring, and management to ensure reliable and scalable deployment of AI models for real-world applications. After you master the subdomain that excite you, it's time you take on a multitude of projects and keep practicing. Remember guys, until and unless you get your hands dirty with real-time problems, you won't actually become good at developing AI solutions. So it is quite important to take on multiple AI projects. You can use Kaggle for that purpose. Kaggle has thousands of AI related projects. You can visit their website and start learning your way up. Besides that, you'll find a competition section there as well. Once you have got enough experience dealing with different types of problems and really have built the confidence, go ahead and participate in a competition. Besides winning prize money, you'll know what kind of work you'll be doing once you get employed. At the end of the day, I want you to upload all of your projects on GitHub. Ultimately, building digital profiles is equally important as building skills is. Besides that, you can also optimize your LinkedIn profile for the certain subfields you have mastered. However, mastering a certain subfield or AI as a domain is not the walk in park. You'll really be required to do hard yards. So we recommend you to go ahead for formal education in the field. You could join any university BTech program that lets you select artificial intelligence as a minor. If you are a graduate or don't have facilitation of going for AI as a minor, then we recommend you to go for proper extensive artificial intelligence certification training. While the internet is full of wonderful and free resources, it won't give you the structured approach or the hands-on practice that you need. If you want to become an employable AI expert, the most effective way to do so is through a specialized program or course. Intellipaat thus provides state-of-the-art certification that are designed according to different sets of industries that artificial intelligence spans across. And it can definitely act as a ladder for your career change with an exciting salary hike. With this program, you could get planned curriculum, wide learning materials, live lectures from IIT Madras faculties, 24/7 expert support, and many more. So go ahead, visit our website and launch your speedy journey of becoming an AI expert. That being said, the next stuff we want you guys to do is build your portfolio. Your portfolio is arguably the most important asset you'll have when it comes to applying for jobs. It showcases how you work and demonstrate to employers that you have not only mastered the right practical skills, but that you know how to apply them in the real world. Focus building LinkedIn, GitHub, formal resume clearly. After done with that, the last phase will be networking, creating job applications, and preparing for interviews. Well, guys, by now you have developed the skills, you have built your portfolio. Now you just need to tie it all together and get that job. Mention your projects, technical skills on your resume. Apply for different job openings on different web portals. Be patient. You'll get that interview schedule call. Meanwhile, start preparing for the interviews. Go through different interview preparation questionnaires and also do mock sessions with your friends to gain more confidence. Ultimately, with some time, you'll crack those interviews and land a job in the domain of artificial intelligence.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Life cycle of deep learning. Right? The very first thing that I'm going to take that we are going to go together is the life cycle. That how does a typical life cycle of a typical deep learning engagement goes, right? How do you start? How do you go in the between? How do you reiterate and then go back, right? And then what we're going to do is we are going to talk about this. We're going to talk about this life cycle, and then we're going to talk about that how a particular neural network is made, right? What is the inspiration behind the deep learning systems? How did you approach any machine learning problem? What was the cycle for you? What is the life cycle of a project? The very first thing that you have to do, my friends, is that you have to do problem solving, right? You have to do problem solving attitude. I know it sounds very different that, hey, Shivam, this is a deep learning class. Why are you talking about this thing? My friend, believe me, that nobody will come to you and say that, hey, listen, data scientist, I have a set of data set and I have this problem. Please run a classification problem for me and run it through Adam Optimizer. If you are thinking this is how a problem statement will be given to you, the answer is somehow, unfortunately, a big no. This is not how clients will reach out to you, right? I know in traditional software industry, we have this kind of culture where, let's say your problem statement is already broken down and they say that, okay, make us an app which can navigate the route for me, right? Just an example. Here, this is not going to happen. They will call you and say that, listen, this is our train route map, right? This is where the train travels. And we are spending almost 9 hours just checking this thing. Please tell us a solution through which we can reduce this 8 hours into some 1 or 2 hours. That's the problem statement. Or they might call you and say that, hey, Shivam, we are a coal mining company, right? And this is our fundance. Our fundance quality, the quality of the coal that is being produced has been degrading since last 3 years. Our quality yield has decreased from 70% to 58. Do something. They will just give you a blank statement, and that is what you should expect also from clients. They will never give you solutions. So what the first thing is that you have to develop a problem solving approach, that understand the problem and then figure out solutions for it. Remember, not just finding solutions, finding optimal solutions. It is not always true to suggest your clients that deep learning will work or machine learning will work. Sometimes there are heuristic operations that can also work for you. That every problem does not require a deep learning solution or a machine learning solution. There are certain times where you can have the problem can be solved through any heuristic based model also. Correct? So the very first thing that I want you guys to develop is a problem solving attitude. The second thing that is the most important thing for all of you is to set up a North Star metrics. What does this mean now? See now, Very good. Let's say you went to a client and the client defined you the problem and you came up with a solution. Let's say in next 3 days, you drafted a rough sketch for them. Let's see, yeah, this is what is this. This is, we will do this for you. And the client is very happy. They're like, wow, fantastic. Go and implement this. And you will start working on it. Correct? All of you will start working on it. You will collect the data and you'll find this thing. The answer is no. The most important thing is that you will ask them, hey, please tell me that when do you think the problem is solved? If I increase your coal quality from 58 to let's say 65, then you will be happy. With 75, then you will be happy, or will you be happy with the 80, right? And first of all, what do you mean by quality, right? So the very important thing before you set up any deep learning project, or even for the sake any machine learning project, my friends, is setting up the North Star metrics. What is that one thing on which the client will evaluate you? Correct? Do you all agree? That we need exactly the goal or the KRA, exactly as our friend says on the chat, that KRAs are very important. Very good, right? So let's say if you're making an image classification model, so the very first thing that you're going to see, a client, tell me what is valuable for a client. A 95% accurate model is very important for them, or a simple solution which delivers business to them, that is more important, right? A solution which solves their problem. Correct? They don't care about your deep learning model, right? They don't care if it is 99% accurate or 100% accurate, until and unless it is solving their problem. So make sure that your North Star metrics are, as one of our friends says, accuracy score, R2 metrics, very good, right? But they are metrics for you, right? You need to translate these metrics into business oriented metrics. Correct? Very good. Very good. Do you understand this one point? This is the major rookie problem that everybody does, right? The moment junior folks, they come into, or let's say non-experienced folks, they come into deep learning, right? They're very enthusiastic. They know how to run the model. They know the data, right? They'll jump on this thing. But they do not have a conversation with their client that what is success. So define success. Correct? Define success. Okay. What is next thing? The next thing, I think, what do you think after, let's say we have done all these things, right? What do you think is the next thing for you? Let's say the client told you that these are the metrics that I will judge you on and you will be evaluated. I will pay you only when, let's say, this metrics is moving. Now what next? Data collection. Now what you will do is, based on your rough draft, right? Also, you'll do one more thing over here. Yeah, I forgot that based on your conversation with the client, you will build a rough.
Let's have a quick quiz question, guys. And the question is, which of the following is not a subfield of AI? And your options are machine learning, natural language processing, robotics, or cybersecurity. Please mention your answers in the comment section below.
Sketch for the problem. Correct? And based on this rough sketch, right, now you will ask relevant questions, right? You will frame the requirement, right? You will frame the requirement, because see, data collection is something that the client is going to help you. You will tell them that, see, I want images with this angle, or I want images with, let's say, these many images. I want 25,000 images, that too with good brightness, good contrast. You need to tell them each and everything. We cannot expect the client to, to go and bring data for as per your requirement. You need to tell them the requirements, right? What is, let's say, define quality and quantity. Define quantity, very important. You need to tell your clients that, what is the quantity and the quality needed for you, right? Do you all align on this thing, this statement? This is very important. In your machine learning, right? In machine learning, majority of the data that you have trained on might be tabular. So there it makes sense that the data is coming in JSON, Excels, CSVs, or TSVs, right? But here in deep learning, my friend, our problem will be solved using cognitive data. Remember, we talked about that majority of the deep learning networks are solving cognitive data. Cognitive data requires what? Image data, right? Video data, speech data. So it is not necessary that your data is going to come into a data frame, into a CSV, right? It can be a S3 bucket on Amazon also, all right? Yeah, on an AWS server also. It is not necessary. It is going to be a CSV. So see, you are not responsible for data accuracy, but making sure that the correct data is going in the model is obviously your responsibility, right? As a deep learning engineer, we need to make sure that the correct data is going inside the model. This is a very difficult conversation with getting data. I'll tell you my real first-hand situation that I'm dealing with right now. Right now, I'm working with a European financial client, right? And they're not sharing data with us because we do not, first of all, had an NDA signed. So we had to sign an NDA. Then the problem is that they cannot directly share it like how you and me share, right? That even does a zip it and send it to us. So we have to make a secure box location or a secure thing, right? There you have to put it, you have to invite them. There you have to make sure that the data is compliant over there. Very good. One of my friends said GDPR, very good. Exactly, right? So sample data and population data is a very different conversation. I think whatever the client is giving, just take it, just grab it, right? I would say I generally never have a conversation with my clients about sample data. I just tell them that, see, I need at least 25,000 images or any X amount of images. And then from that, I can take sample and do whatever my sample statistics that I want to do, right? I can do that. But I always ask clients for more and more data. So then what next? Next is EDA, right? EDA means that, as I told you, right, that client will give you any data, right? They don't do a quality check. It is your responsibility to make sure that you are getting correct data, right? So it is your responsibility. The moment you get the data, you will do data cleaning, right? And these are the same steps that you might have done in your machine learning classes also, right? First of all, cleaning the data. The same thing happens in our images also. What you'll do is you'll lay down the images and you will do a histogram contouring on them, right? Multiple processing that you can clean the data. The second thing that you'll do is what? Data QC, right? That, let's say, if you have asked for steel plant, let's say, images, are they all steel plant images or there's something else also? Next is feature engineering. Feature engineering is something similar to what you have done in your machine learning also, that you will take the images, you will check them, that what is the height consistent across all the images, is the width consistent, does all the images have 3 channel or 2 channel or 4 channel, right? Don't worry, my friends. We will talk about this feature engineering lot more into details later on. But right now, understand that images, or not just images, but let's say any cognitive data also have certain features on which you can do a engineering, and you can check on those engineering parameters. If this would have been a machine learning, right? If this would have been a machine learning aspect, but here we are working for cognitive data. Here we merge both of them, because generally all your feature extraction and the engineering that you are thinking from a machine learning perspective is actually done by deep learning itself. But there are certain things that you need to check. You need to check for those features, right? And if there are some external features that you can generate, you should definitely generate them. Correct? I'll give you one example later on also, that, in real life example also that I gave you, that, information might not necessarily be inside. I'll give you one example. Okay, I'll just right now only give you an example. Let's say you have got 25,000 images, right? Now, as my friends are saying that, Shivam, features are extracted from images. Very good, yes. But you know what? These 25,000 images are coming from 3 different, let's say, plants. This is coming from plant 1, this is coming from plant 2, and this is coming from plant 3. Now, because there are 3 different plants, they might have different environmental issues, right? Humidity might be different for that particular city, temperature might be different, right? They try to control the process as much as they want, but still there are some external variables which can't be controlled. So what I do is, whenever I'm making my deep learning model, right, I try to supply my own features over here. So I will do a one hot encoding, and I will say this is coming from plant 001. This is coming from plant 010, and this is coming from plant 100. And you won't believe, this one distinctive feature actually helped me to increase 3% my accuracy, 3 percentage points of my accuracy. Do you understand now the difference when I say feature engineering is done by deep learning, but then additionally I'm also supplying very simple things, correct? Okay. So once you have done, let's say, your data cleaning, and you have done some feature engineering that you wanted to do, right? Cleaning, what next? What next do you do? What I would do is, I would, let's say, split my data, right? I would split my data into 3 different parts, right? I would split it into, all of you are aware of train versus test versus validation, right? TVT, very good, very good, very good. So that's one thing, right? Now, most of you might be thinking that, Shivam, why is it such a big step, right? I mean, I just randomly do it, correct? I just randomly take my data and I just split it. Very good. A random split is one of the most common it is one of the most common types of split that people use. But certain times the data is not balanced. Then what will you do? What do I mean? See, listen over here. So let's say you have images, right? Let's say you have 20,000 images, right? And let's say 18,000 images are from category A, and only 2,000 images are from category B, correct? Only 2,000, and this is 18,000 images are from category A. There's a ratio of 9:1. Now, if you go and try to randomly make your test data, it might happen, my friends. I'm saying might because this is random, right? I also don't know. It might happen that you might end up with all category A images inside your test data. Is it true or false? Tell me. Can this happen? Possible, right? So what do you do in this particular situation? How do you classify images from 20K? I call it no, because this is the trained data. I have the labels for them, my friend. This is the trained data. I already have labels for them. The client has given me the images and the label. Stratified sampling. Stratified sampling is the answer. So what does stratified sampling will do? Stratified sampling will first of all calculate, and it will say that, okay, the data is imbalanced. The data is imbalanced and it is in the format of 9:1. It is in the format of 9:1. So what it will do, it will create a test data for you in such a way that 9 parts of the test data is category A and 1 is made up of category B, the same way in which they were originally mixed. So stratified sampling takes care of this particular thing. And this problem becomes more problematic when you have more categories, right? So let's say if you have 20 categories and the last 15 categories have very less data. Stratified sampling is one that we can definitely do, right? Images, you have split the images and you have done random split or stratified split, you can definitely do that. But tell me one thing, my friend. So how many data points are there? It contains 500 rows, 500 columns, and 3 channels. What is this channel? We'll talk about more, but this is just the data from one image. This is just one image. If I have 20,000, 30,000 images, just imagine what is the amount of data that you're dealing with. Do you think that you can read this complete data in one go? Do you think that even your supercomputers can read this thing? Your huge, let's say you buy some Amazon machine, right, which has huge capacity, huge RAM. No, it cannot do, right? This is where our friends generators, they come in. Generators, they come in. Generator says that we will help you. Don't worry, right? We will generate data for you at a bunch to bunch basis, right? Into a bunch to bunch basis. So these are 3 important data selection things that I wanted to share with you. First of all, splitting, and what kind of splitting, and then splitting might not be one of the best things, right? You want to do it into a generator kind of a thing. What is generator? We'll talk about more into details, but just think of it as a problem that you cannot load your complete data. You cannot load your complete data inside the RAM. So what you do is you make something, you take a help of your friend generators, and those generators will divide the data into multiple small batches, and they will send the batches to the trainee. There would be no help in using a Docker also, right? Because you need a distributed deep learning system to work on multiple Docker images, right? I'll tell you the difference between why Docker might not help you and what is generator, why it is different. Don't worry, we'll talk about it. Generator is not generating data. This is not a method of generating data. Rather, how many of you know what is this? Let's save it into a variable called A. This is not even a lambda function. Let me show you. Wait. So I saved it inside a variable called A, and if I show you the type of A, this says something as generator over here. Okay. And if you type A, nothing will happen. Those of you who are saying list comprehension, no, this is not a list comprehension. This is a Python generator function, right? It is a generator function. If you don't know, no worries. As I'm telling you, do not worry. Do not worry, right? This is what a generator is. Generator is not, it is not generating data. Let me write down. Rather divides big data into smaller batches so that they are compatible. They are compatible with RAM. Do not worry, we'll talk about this more into detail. Now let me explain you what this thing is. See, take an example. All of you, please see here for 2 minutes, only for 2 minutes. Let's say this is your 100,000 images, right? And each image is what? 500 cross 500 cross 3, right? And then multiplied by 100,000. This much amount of data needs to be stored in the RAM. Do you all agree when you are doing your deep learning training? This is what you have been taught in your machine learning also, that the data will be loaded, it goes and it will learn. Do you all agree? 500 cross 500 cross 3 into 100K. This is the huge amount of data that will be stored inside the RAM. Now, do you think that our machine, so right now, this particular collab machine that I'm working on contains 13 gigabytes of RAM. All of you, I'm going to mouse over it. See here, 13 gigabytes of RAM is over here, right? 12.68 RAM is over here. Now, do you think that this much amount of data can be stored inside RAM? Do you think this much RAM? The answer is absolutely no, it cannot. So what we are saying to the system is, we are saying to our deep learning system over here that, hey, this is, let's say, our DL model. This is our DL model. We are saying to our DL model that, buddy, I am not going to send you as it is. I am not going to send you as it is, but rather I am going to divide you into small pieces. So what we will do now is we will make small pieces of this particular thing. Let's say we take only a batch of 32 images. So now I am sending what? 500 cross 500 cross 3 into 32. This much my RAM can handle. So we will send a small block to the machine, the deep learning system, and this will only go over here. So rather than sending 100K, I will divide this 100K into batches where each batch will contain only 32 images. So they are going into small batches so that my RAM does not burst out and you get a OOOM error on Python. Out of memory error. Remember this error also, OOM, out of memory error. Do you understand now? That rather than sending the complete data, we are sending small batches of that data. Please understand the fact that this particular thing will not generate data for you, right? This is not like a synthetic generator for you, correct? We will do pre-processing. Now, pre-processing has multiple stages, right? I can think of something like resizing the images, first of all, right? Balancing the images, right? Balancing the color balancing might be there, right? Changing channels of the images. Now, what does this mean? That, certain times image channels are not correctly balanced. So it might happen that the library that you are using is not reading the data into RGB but BGR. Now, what is this RGB BGR? Do not worry, again, there's a separate topic, but let me help you. See, all the images that you're seeing right now also, right? What is happening is that, let's say this is your eye. This is your eye. And this is, let's say, the object that you're seeing. What is happening is that there is a source of illumination, right? There is a source of illumination. It might be in the night. It might be your tube lights, your lamps, right? They cast a ray over here, and this ray is bended over, and then you see this object, right? Now every object is made up of only three colors: R, G, and B. This is called RGB: red, green, and blue. These are the primary colors of the world, right? These are called the primary colors. Everything is made up of this RGB, and that is why, my friend, let me actually tell you one more trivia over here. So what happens is, now there are three colors, three actually primary colors, right? R, G, and B: red, green, and blue. Red, green, and blue. Now you might say, no, Shivam, there are different shades of red also. There is, exactly. There are 256 You can say shades, or you can say intensity of red color, right? Intensity, right? 256 intensities of red can be made, right? These are also called as pixel values. So they can go from 0 till 255. I will show you a demo also. Do not worry by making these images. But every color, every R, G, and B, these three colors, my friend, they have their intensities from 0 till 255. Where 0 being the lowest and 255 being the maximum, like the red blood color over here, right? Similarly for green also, and similarly for blue also. So there are 256 different types of red, 256 different types of green, and 256 different type of blues are there, my friend. In such a way, if you mix them, you can make any color in this particular world. Any color that you can think of can be made with these combinations. Now, does this make sense? This coloring thing, channel, what is the channel? It means each image. Now whenever you see a image, now you might see a image like this, right? Like this, but actually it is not like this. Actually this particular image that you are seeing, my friend, is actually like this. There is a red channel. It means the red colors are here. Then there are green colors over there in the background, and then there are blue color also there, right? So all these three colors, they match up, and then they give you a multicolored image. Now you don't see this kind of three matrix in the background, you don't see this kind of nature, right? But this is how a original image is made, right? With the combination of red, green, and blue. Make sense? You see it like this. For you it is a 2D image which has height and which has a width over here, right? It has a height, it has a width. But actually any digital image that you're seeing, right, will have a height, will definitely have a width, but will also have something called as depth, something called as depth over here. Correct? This is how an image is generated. Now, have you ever seen that whenever you see a commercial of a television, they prompt you that you can see some 12 million colors into this thing, or you can see some 8 million colors into this thing? Have you seen some commercials of TVs where they say that, you can see these many colors? Now, how are these colors coming up? Is that we know that 256 color is from red, 256 colors are from green, and 256 colors are from blue. If you multiply this thing, and you will notice that this number is 16.7 million. This is where that number comes from. The more the panel can display or render the colors, the more colors that they can generate. So you might see that some can generate 8 millions, like cheaper televisions can generate 6 million, 8 million. And with the more higher quality that you go, they will generate 12 million or 14 million or 16 million. Right? And this is where this number 16 million television comes to you. Okay, so we were talking about pre-processing, resizing, balancing images, changing channels, because it is not that we have only 3 channel images. We have depth is always 3. Very good point. No, depth cannot be 3. It can be sometimes 1 also, and it can be sometimes 4 also. What is different channel images? I will explain, right? What is channel? Channel is exactly the same thing that I told you, right? The depth of an image. 2 minutes ago, we talked about this thing, the depth of an image. This is called as that how many channels do you have. So generally, an image will have 3 channels: red, green, and blue. For a colored image, it will have a 3 channel. But sometimes you have 4 also. What is the 4th one? I will tell you. However, we are saying 500 into 500 into 3 always, where 3 is the depth. If this is a question, then yes. Because to you, it looks like this, right? For a human, it looks like this, but actually it is like this. It has 3 layers. Think of it as layers, right? Stacked on top of one another. So the below one is blue, then green, and then on the top is red. So you don't see them, but they are stacked together. So 500 plus 500, it means height into width into depth. Height into width into depth. Correct? If pre-processing is before data selection, we might end up pre-processing on more than one train validation itself. See, so you always do not want to. That's a very good question. Okay, you tell me. Do you pre-process your data first and then divide it, or divide it and then pre-process it? Pre-process and then divide. Okay. Pre-process and then split. Very good. See, there's a small risk into this process, right? When you pre-process and then you split, what is happening is that let's say that if you are doing any kind of a standard scalar function, right? Let's say if you are doing any kind of a standard scalar function, what is happening is if you do this pre-processing earlier, what you have done is you have taken the mean of the complete data, not just the trained data. You have taken it for validation and you have taken it for trained data also, test data also. Correct? So generally what we do is we divide this first, right? We do all this selection first and then we process it so that we do not bias our data. In certain problems, like I was working for the steel manufacturing, right? The biggest challenge for us is that whenever, let's say, you have an image, right, you will notice that now slowly, right, that color patterns are also very important, right? Color patterns are also very important, and in some cases color are the majority differentiator. So in one of the examples that I will give you, right, I will give you an example of plant leaf error detection, right? Detection, sorry, not error detection, disease detection. So what is this thing is, see, I'll answer your question, right? In this particular problem, plant leaf disease detection, what do you think? How do you know that a plant leaf has a problem? A very simple question I'm asking you, that how do you identify that the plants are suffering a disease? So in this particular problem, right, a problem like this, you will see that, you know, your leaves are there, right? And you have to do this for crops, right? Your leaves are changing colors. They will have some patches of brown, gray, yellow over there, right? And this is where you see that these leaves have some problem into it. And I will tell you that this particular problem can just be solved by identifying the colors in the patches. That's it. This particular problem can be solved. So, right, do you understand that in certain cases it is very important to have the color knowledge? If, let's say, if I give you a grayscale image over here, it is hardly identifiable that, you know, that there's a patch of gray over here or there's a patch of yellow over there. Do you all understand this particular question? Especially my friend who asked this thing. That please make sure that you do the splitting first and then you do your data pre-processing, right? And again, this color thing is correct. And also to your point that you have made over here, right? In one of the problem solving, I will actually tell you to convert your colored images into grayscale and then do it, because then you are reducing your data and because color is not playing a very important factor over there. And right, while we will learn about convolutional neural network, I will show you that how a 3-channel image is suppressed into a 1-channel by running a filter on top of it. But again, this is again going into the jungle over there. But let's come back, right? See, again, don't think images as a human. Think of it as a matrix, a big array filled with numbers, right? Suddenly there was a single depth array, and now we have converted into 3 depth array and you have added some random numbers into it. Have you not changed the data? And just asking your opinion. Again, see, please don't think from a human perspective. For a human, yes, definitely a black and white and a colored image might not have some changes, but think of it from a matrix perspective, from a mathematics perspective. Have you changed the array? The answer is absolutely yes, you have changed, right? So, okay, pre-processing, coming back. Pre-processing can be, you know, resizing, balancing images, changing channels, might be rotating. What is null value in image? Either there is an image or there is no image, right? So no null value, at least of over for here. But yes, there are multiple things, like you can rotate your like rotating the images, or, you know, flipping the images, right? There are multiple things that we will learn over here in our pre-processing, but some of them are rotation, flipping, and etc, etc, etc. Changing the rotation, flipping, adding some padding over there, you know, shifting the image, width shift, zooming the images, right? Those things you can do. Feature reduction, very good. So see, feature reduction is that images have so many features. Should we not run any kind of a dimensionality reduction or a feature reduction and try to make it a smaller version? Yes and no, both, right? Definitely we want to reduce the features, we want to reduce, and we want to get and we want a smaller size, right? Correct. But I will answer your question in a different way. See, for images, right, I would never want to do a feature reduction. Rather, what I want is something called as region of interest. What do I mean by that? Let's say that there is an image of a dog and you are doing something called as dog identification. That is there a dog in the image? Yes or no. This is what you have to identify. Let's say this is a dog that is there, right? And let's say these are buildings in the background. Buildings in the background, right? Some mountains in the background, right? All these things are there. Now, what is a feature reduction for you might not be feature reduction for deep learning, right? In deep learning, what I want is I do not want to focus on these random, let's say, mountains, on these buildings, right? What I want is I want something called as region of interest. Region of interest. It means that I want to actually focus on this particular cat only and not on these buildings and mountains. And the problem is, as a human, you cannot, right? As a human, you cannot go into 30,000 images and then remove these things, right? Because if you have already done that thing, you have already identified the data, correct? So we will let this also happen with neural network. We will train our neural network in such a way that they focus on something called as region of interest, ROI, region of interest, correct? Do you understand now? So what kind of feature reduction we are going to do over here, my friend? Right? I know from machine learning, you're thinking that, I will combine two features, I will remove the unnecessary features, right? But here in deep learning, you cannot figure out a redundant feature. You cannot figure out that what is necessary, what is not necessary. So we will leave it up to neural networks to figure this out, that what is necessary and what is not necessary, in such a way that our error or the loss is minimum. Now, what is this loss? Deep learning handles all your feature extraction and feature engineering. This is exactly what is doing over here. This particular session that we have designed is majorly around images, but I will also give you a session on text also at the end. So we will have a non-image data also at the end. Yes, we will have. But again, this is very much focused um, on images. Voice, no, unfortunately, this cannot be done in this particular case. But I can share my sheets with you. I can share my historical sheets that I've done, basic synthesis, classification of sound. I have definitely done that. And again, you will notice that sound is again nothing but a matrix only. Sound is again nothing but a matrix only made up of height, width, and depth over there. And then again, you will be running almost the same networks, the neural networks that I will teach you on speeches also. Practically, how is it possible to get all pictures of small size? I might have big images, small pictures, all are different images acceptable as data input, or is it a pre-processing work? It might happen that the client might give you small images, big images, middle images, right? So should we enter all the images inside the deep learning, or do I need to do resizing? Right? That's a very good question. See, it depends on the architecture that you are using, and you might see I have written resizing as one of the pre-processing input features, right? So for low-ended networks, right, you might need to do resizing, but later on I will teach you those models where you can set them independent of image size, right? They are not dependent on, or let's say they are size agnostic in nature. You can send any size of images. But again, please don't think that if you have trained a model on 1048, 1024 into 1024 and you're sending a 8x8 image, it will work with the same accuracy. It will not. Train the model, correct? Now, training the model, how do you train the model in machine learning, right? You would take the complete data, do a mix of your data into train and validation, and then send it to machine learning, correct? And then you do your things back and forth, correct? In deep learning, please remember this thing. You will always make a baseline model. Please listen to me very carefully. And this is not just important for deep learning, right? This is important for machine learning. And I'm telling you from my small 12 years of experience that this is a rabbit hole. Training a model is a rabbit hole. It looks very simple, right? That somebody gives you a data, you just make it, and then the model runs. In real world, it does not happen like that. It does not happen. So please understand this thing. It's a very, 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 very important part, right? The important part is that you will start with a baseline model. Now what you have is whatever the accuracy or whatever the losses have come up, now they become the baseline for you. Now anything better than this, now you know a benchmark for you, right? If I get, let's say the baseline model gave you 60% accuracy, just an example. So what is now your next thing? Your next hyperparameter tuning that you will do should at least yield you 60 plus. Then only you will say that my hyperparameter is good. What people do, the people do a small mistake is that they never make a baseline model. They always start with hyperparameter tuning. Now what happens is they never know that is this a bad accuracy, is this a good accuracy. They never know this thing. So first of all, always make a baseline model for yourself with default settings, and then you can try your hyperparameter tuning as much as you want, right? The next thing is record your metrics. Always record your metrics. It is always better to record your metrics and then save the model. Hyperparameter. Correct? Hyperparameter. I have an example, say in auto insurance claim project. Can I use the accident damage images and tell and categorize how much is the damage, and tell categorize how much is the damage worth high level? Should the car be totaled, less or heavy damage? Yes, you can. And you, I think yourself gave the answer, right? See, ultimately, whenever you give a car image, don't think that the machine learning model will only be trained to tell it that whether it is a car, yes or no. Definitely you can ask it about the damage, that is the damage likely you categorize, right? Like total, less damage, heavy damage. Definitely you can do. I am a little skeptical that how would you give a price tag, that what is the amount, but definitely you can categorize it, that okay, what is the level of damage, right? So I did one project, I remember, for a car insurance company, where for the European car manufacturer, where we did this thing, that we told them on a scale of 10, on a scale from 1 to 10, that how much is the damage on the car. Definitely we did it. Pricing is something which actually depends on multiple things, that what was the material which was damaged, right? What was the part of the car which was damaged? So we can identify all these things, but quantifying it into a price, I think that was left to the company to do. You can do object detection, you can count the number of instances in the image, you can do segmentation. I just did one problem with an South Korean client, where we're actually helping them to do image search, right? That you take any of your star, whatever they're wearing, right? We will extract clothing from them. And we can find that in our database. So not just detection or recognition, segmentation can also be done, counting can also be done, image search can also be done. There's a triplet loss thing that you can do, content based image retrieval. Yeah, exactly, you can do that also. It is my personal recommendation, never solve a open domain problem, right? So the moment you say Google Earth, you have gone into an infinite circle, right? Try to boil down your problem into a smaller part. And then, so let's say if you're asking me that if I give you an image of, let's say, a particular building, and I need to find it in a particular pin code location, can I do it? Yes, you can. This is not a big challenge. Definitely you can. And that is exactly what I was telling you, right? Image to image search, you can do that. So the next thing that you will always do is validation, and validation is different from testing. All of you are aware of this concept, right? That validation is not testing. Validation means that you applied a hyperparameter. Is it working or not? Correct? Very good. And the last thing after validation that you will do is testing. You will take your test data and then you will try to test your complete model on this thing. Now, some of you have a question, and I think in the earlier session also somebody asked me that what is the difference between testing and validation, right? The biggest difference between testing and validation is that test data is never seen by the model. Never, ever in the creation of model, test data was shown to the model. Validation data is still shown to the model. The model knows about validation data, what it is, how does it look like, what are the characteristics, but the model has never seen testing data. Do you all agree with the statement? Right? In the complete life cycle, it has never seen. So that is why a testing number is always important, right? And you will always quote in all your conversations, you will always quote your testing accuracy and your testing losses. Please, I'm repeating it again. in any of your conversations, it might be internal conversation, tech conversation, client conversation, you will always quote the testing numbers, so that you avoid embarrassment later on that your model is, let's say, overfitting, or let's say if it is underfitting, you might not say the wrong numbers. You will always quote testing data, right? Okay, so that is, sorry, so that is testing data. Do you all agree with my statement? Validation and testing, how they're different? And I think you already know this thing by in your machine learning days also. The last thing after testing that you have done is inferencing. Inferencing means, and I think most of you gave me a feedback also, that most of you have not done prediction on your ML model. Inferencing means that you will build a system, that will help the other application. See, now there is no value over here. There is no use of a model until and unless it can be used on an application. So what is inferencing? Inferencing means that, see, a model in itself is nothing but a pickle file, right? A model in itself is nothing but a random file with huge numbers inside it, right? So what do we want is, see, okay, tell me one thing. Netflix recommendation system, all of you have used it, right? Netflix, or let's say I'll take a simple example, Spotify's recommendation, all of you have used it, right? You use that Discover Weekly, right? You have used Netflix or YouTube's recommendation. YouTube, I think everybody has used, right? YouTube's recommendation. So now tell me, if that recommendation model is sitting somewhere idle in the system, it is worthless, right? It came into value only when it started recommending people on YouTube, correct? When the model was deployed on YouTube, then it became famous, right? Then it became helpful, then it became monetizable, correct? Do you all agree with my statement? That is exactly going to happen with you also. You will go at a client, you will make these models, but until and unless you can't use these models, they are just nothing but a huge space taking giant things on your machine. That's it, right? So what you would do is, in inferencing, my friend, you will make small functions, or you will make small APIs, so that other folks, the product folks, can use your model to find the answers, right? Now it can be as simple as making a Python function. It can be as simple as making a Python function, expecting that the function, you will pass an image in the function, and in return the function will return you the result. Like, you can do it like this. I'll give you an example over here, that you can make it like this, that model predict. You can make a function like this, predict, and you can ask for, let's say, image path, that anybody who is making the, let's say, the product can just, let's say, use your function. Your function is asking for what? An image path. What you will do, you will read the image, then you will pre-process the image, whatever your pre-processing is, pre-process the image, and then model dot predict, right? And then share the results, and you can say return results, correct? It can be as simple as like this, making a function like this, right? And it can be as complex as making a distributed scalable machine learning arc, right? But again, this is not a responsibility that you will be given. You will never be given a responsibility like this. You are always expected to simply make the model and do the inferencing. But as and as you grow in your career, right? Slowly, when you'll grow in your career, these responsibilities will also come under your belt, right? Does it make sense? Right? So that is inferencing. I will write down, can be a simple function with image pre-processing, and can be a large distributed scalable system, right? Depending on where you are, but again, nobody is going to expect you that you will do these things, right? And in the pre-processing, I want to tell you one more thing, that is image augmentation. So see, I was talking about this 1980s, right? And we are in Canadian Toronto University. These are these three folks, generally two folks, Geoffrey Hinton and Yan Li Kun, right? And they are working on deep learning, trying to figure out that how we can solve for cognitive issues. And somehow, Geoffrey Hinton says that we can't do it until and unless we replicate how humans do it, right? And he has a very good sense of biology, and he says that if I try to mimic how a human thinks or what actually happens with a human, right, we'll try to replicate that thing synthetically, right, artificially, and then we'll make a network, and through that we should try, right? So what he says is, and now understand what happens. This is a simple neuron over here, right, in front of you, that you are seeing, right? I just this is what actually it is, right? You need to see three different things. This one is called as dendrites, right? This one is called as axons, right? And this is the middle neck of this thing, right? Now what is happening is, you will, let's say, if you copy paste the same thing below, right? So the dendrites of, let's repeat it again, this is axons, and let's say if I copy this again at the lower part, the axons of this neuron will be touching the dendrites of the second one, and then similarly they will make a chain. And this is what is running inside your nervous system, right? That is what is running inside your nervous system. Now take a small example. What happens when you touch a hot glass of water? What actually happens is that when you touch that particular thing, the tips of your finger, right, the tips of your finger, they take up the particular signal, right? They transfer it from this neuron to neuron, neuron to neuron, from dendrite to axon, axon to dendrite, dendrite to axon, axon to dendrite, and it sends a signal from your hand through your elbow, elbow to your shoulder, shoulder to your neck, from neck to your spinal cord, and then through your brain, right? We'll not go into details of biology, but let's say that's how a simple, let's say, transmission happens. The brain sees the signal, it says, okay, interesting signal, that the fingertips are burning and we need to, let's say, take some action. Now the impulse is so high, the brain says, okay, drop the glass. And the signal now goes back into your brain, goes back from your brain to your spinal cord, to your shoulders, to your elbow, and then back to your fingertips. And then you leave that particular class. This is a very simple representation of what happens when you touch a hot and burning thing. Now for you, it's just a thing, a blink of an eye. I think in less than a blink of an eye, you leave that, but actually this is what is happening from your fingertip to your brain, and then from your brain back to your hand. This is what you are doing, right? And you drop it. Correct? Now this is now this is what generally happens. So they said that, okay, let's try to replicate this process of sending the data, evaluating the data, and then taking appropriate decision. Correct? This is what is happening from your brain to your hand, right? First of all, hand sends, the fingertips sends a signal to the brain. Based on the intensity of the signal, it takes a decision and then sends the decision back from your brain to your fingertips. That is exactly what these folks also did, right? What they did is, now let's try to mimic that over here. So Geoffrey said that, okay, we are going to make a neural network. We are going to make a neural network. It is going to look like somewhat like this, right? And you might have seen this image almost everywhere, right? Please be with me, and I'm going to help you. What is this? Now see here, this is called as input layer. The first is the input layer. The first one is the input layer. This is always connected like this, right? Every neuron, right? Every neuron is connected like this to the next neuron in the next layer, to the neurons in the next layer, like this, and then like this, and then like this, and then like this, and then like this, this, and then that, right? This is called as a hidden layer. I for just 5 minutes, I will not see the chat. Please focus here, please. And then this is the output. Again, what is the responsibility? That every neuron or this every red circle has to connect to every red circle in the next layer. Right? And this is a very typical neural network that you will see on your Google images also. Right? Now, what it is, how does this operate? We'll talk about this thing. Give me 1 second. Run this over here, run this over here, and one this over here, one this over here, and one this over here. Okay. So now what is happening? Let's take an example. Let's take an example, my friend, where let's say we have an image of a dog, right? Let's say we have an image of a dog, DOG, and we will send this image to a deep learning model. Let's say we will send this image to a deep learning model, and the model can say either yes or no based on whether there is a dog in that image, yes or no. Correct? That's a simple classification problem that we can do. Do you all agree? I'm taking an example of a dog classification that we will send an image of a dog, and the deep learning is expected to say either yes and no based on if the dog is present there or not. Correct? So now what happens? This is what you see in the broader picture. What is happening in detail? What is happening in detail is, my friend, that the image of the dog you have, right? You send all the pixels of the dog image like this input, right? In this particular example, we have 3 input neurons. Each cell is called as a neuron. Each circle is called as a neuron. Neuron, right? And this particular collection of vertical neurons, is called as a layer. Is called what? It is called as layer. So this particular one is called as input layer, and this particular one, this 4 vertical ones are called as the hidden layer, right? These are the ones which are between the input and the output. Correct? And this is your output layer. I will also draw this thing. Now, the first question that comes into our mind is that, Shivam, can there only be one hidden layer? Can there be multiple hidden layers? The answer is yes. There can be multiple hidden layers. Multiple hidden layers can exist. Multiple hidden layers can exist. For the simplicity of this example, I have taken one hidden layer, but you can have multiple hidden layers, right? And I will show you some models in which we will take some thousands of layers, right? The second question that might come in your mind is that, Shivam, how are we deciding that number of neurons inside the hidden layer or input layer or output layer? Correct? Most of you are thinking that, Shivam, how did you decide that there will be 3, 4, and 2, right? They can be 2, 3, and 6 also, right? Okay, very good. See, the number of neurons in the input layer are decided by the number of pixels in a particular image, right? So if your image has only 3 pixels, we will send 3. If it has 30, we will send 30. And one of the examples we figured out, what if you have 500 cross 500 cross 3, then you will have how many inputs? If let's say you have a 500 height, 500 width, and a 3-channel image, you will have got 75, 0, 0, 0, 0. Correct? 750,000, let's say 750,000 input neurons will be there. So all of you understood this thing, that how many neurons will be there in the input? Say yes or no. Do you understand how many neurons are there in the input layer? Understood? Very good. Fantastic. Now we will decide the output. Now we will decide about the output. Now, output, it is designed, or let's say output number of neurons in the output are decided that, let's say, how many, what do you want the model to yield? What do you want the model to tell? If let's say your model is, let's say, a decision model which says that whether this model has a dog, yes or no, it will have 2 outputs. One which says yes, and the other one which says no. Correct? One which says yes, the another one which says no. Correct? Or let's say you might have a problem that you are solving where you have to identify the type of dog. Let's say you have to identify whether it is a German Shepherd, whether it is a Golden Retriever, or it is, let's say, a Labrador. Just an example. So you will have three outputs, correct? One for each category. Similar to how you had in your machine learning also, that based on the number of categories that you have, those many numbers of output you will have. So in this particular case, if I have to identify between three dogs, I will take three outputs. Understood? But for this example, what we're doing is we just want a yes or no. So we have two, let's say, outputs over here. My friends, the number of, please listen to me very carefully. The number of neurons in the input layer are designed, or let's say are decided by the number of pixels that you have in the number of images, right? So let's say, my friends, if you're working with a very small image, let's say a small image like this, I will draw it over here. Let's say if you have an image which is, let's say, 50 in width and 50 in height, and let's say it's a 3-channel image. So you will have how many inputs? 50 height, 50 width, and 3-channel image. These many number of input neurons you will have, correct? 7500, 7500 neurons will be there. Does it make sense? Okay, everybody says yes. Very good. We will now jump to the output neuron. See, in the neurons in the output layer are decided by that what do you want the model to tell you, right? What do you want the model to tell you? Do you want the model to tell you that there is a dog, yes or no? Then there will be two options. If you want to, let's say, tell that I want to identify between categories, like, like we took three categories of dog A, dog B, dog C, then the model will yield three outputs, right? Or let's say if you are making a model between cat and dog, let's say you have a model which has to identify between cat and dog. So this model will have how many outputs? It will have two outputs, correct? Does it make sense? So that is what your outputs are defined. So one of my friends says that answer that you will resize. But then I also said one thing to you, that there are certain neural topologies that I will teach you, in that you don't need to resize them, and you can send your recalibrated image. It means you can send a 50 cross 50 also, you can send 150 cross 150 also. It will work for both of them. For a cat versus dog operation, my friend, you need two outputs. Whether it is a dog or a cat, you need a two model. I'll tell you why also. I know you guys are coming from machine learning and you think that if there are two categories, you can do it with one only. But the point is, here in deep learning, it's a little different. I'll tell you why also. Don't worry, I will tell you why also. But let me go above and see one of the questions which says that the output of the neuron is only one axon. So the same output is input into next layers of all neuron. That is what is happening over here also, right? And you see, if this particular neuron is acting as the, so let's say whatever it is outputting actually becomes the input for these two in the output neuron. If I have two categories, let's say dog and cat, only one thing can work for me, right? I only need one neuron which can say dog found yes and no, correct? Which is actually a little bit wrong. Why? Because deep learning do not always say yes or no. They actually return the percentage probability that they think whether it is a cat or a dog. Listen to me now one more time, please. Let's say if we have, let's say, a dog problem over here. Let's say if we have a cat versus dog thing. Let me just delete this yes and no. And instead of it, let's say cat and dog. Let's say if this is a cat neuron and this is the dog neuron, it is not saying a yes or no or a 1 or 0 over here, my friends. The neural network will always regress, that it thinks, the model thinks based on the image pixels, based on the features that were given to me. I think that this particular percentage is a cat and this percentage probability is a dog, right? One of my friends says, I suppose the way we see image and deep learning sees an image is very different. Obviously, see, you think that image is the image, right? Whereas for machine learning or deep learning model, it is just a big matrix of array, right? Very good. Also, one more thing that you have to remember is that the probabilities are regressed in such a way that if you sum up these two probabilities, they will always come as one in one of the activations. Again, Again, see, I don't want to go into details. I know some of you are very smart, some of you know about this thing very good, but others do not know. So I will restrict it to here only. Just understand that, please, these outputs are not outputting something like that, this is a cat or a dog. They are actually giving you the confidence that we think that 70% this is a cat and 30% we think this is a dog. Now you take your own decision. Now this is all at your discretion, that you want to say it a cat or a dog. The model never says it is a cat or a dog. It always gives you a predicted probability. I will erase this back to yes and no. So okay. So now do we understand that how the neurons are, let's say, figured out, at least for input and output layers, that how many circles do you want in the input and output layer? Is this fine to everyone? Now the only thing that is not understandable to us is that how many neurons do I want in hidden layer, right? How many are required in hidden layer? So see, hidden layer neurons are decided by the architecture or the topology that you are using. If you are using a FCNN, it will be different. If you are using a CNN, it will be different. If you are using a RNN, it is going to be different. So it is dependent on what kind of topological ML model, or let's say deep learning architecture, you are using over here. Correct? Now I think I mean, when first time I read this architecture, right, and I think you guys are not asking this question. The biggest question that I had, I mean, I was not caring about how many neurons or how many layers do I have. When first time I saw this thing, the first question that came into my mind is, how is this mesh of wires solving this problem? How can this mesh of you know pixels go inside this and can give a yes or no? What is the magic happening inside, right? This is the first question that came into my mind when I saw this, that how is it possible that you are sending this data inside, and then some data are connected to some circles, and these circles are doing some magics and they can produce this thing, right? See, ML machine learning was very intuitive, right? Because what was happening is that there was pure mathematics, and you could see that mathematics, right? That if you're doing a linear regression, you have a line over there, you're regressing the line on that. If you're making a decision tree, it made very clear over there. But when I saw this for the very first time, right, I mean, for me, it was magic. I mean, one of my friends says it is not magic. But for me, it was, at least for me, it was magic, right? That how can this happen? And this is what exactly we will learn now, that what is happening in the background, right? I know some of you know this already. Some of you are saying activation, gradient. See, those of you who know, very good, very good. Thank you so much. But please refrain yourself, right? Don't, give a spoiler alert to my other friends, please, right? Okay, so let's understand now what is happening over here. I'll give you just a small gist of what is happening over here. See, for you it might not be magic, right? But for me, at least, it is magic, that how it was happening for the very first time. But then I understood that here also it is mathematics. Here also it is mathematics. Now see here, what is happening? What is happening is, you took your image, you took your dog image, and you flatten that image in such a way that you're sending each pixels over here, right? One pixel goes over here, then second pixel goes here, then third, then fourth, then fifth, and then your 7,500 pixels are going inside your neural network like this. Correct? Now, what is happening, my friend? Listen to me very carefully, please. Every neuron that is connected to another neuron with this black wire that you see, right? What do we do is, we say that we have a relationship with you. We have a relationship with you. This neuron 1, N1, this N1 has a relationship with this N4. And what is that relationship? That relationship is called as affine relation. That relationship is called as affine relation, right? Affine relation. Now, what is affine relation? Affine relation says that, see now, please listen to me very carefully. Who is this N4 connected to? This N4 is connected to N1, this N2, and this N3 also, right? It is connected to all the three. You can see over here N1, N2, and N3. So we are saying that N4, you are made up of N4, you are made up of the sum of N1, N2, and N3. Please listen to me one more time. This N4, this buddy N4, this that I'm rounding it right now, this N4 is made up of N1, N2, and N3. This is N2 and this is N3. It is made up of these three, all right? And this is made up of the summation of these three. It means I am saying that there is a linear relationship between you, right? There is a linear relationship between you. But obviously, it cannot happen that all the pixels are contributing in the same way, right? Because some of the image pixels are actually drawing the building, some of the image pixels are drawing the mountain, which are not required. I want to focus on my dog and I want to give it more weightage. So rather than just simply adding it, my friend, we add a weightage over here. We say that we will add a weightage to each pixel value, to all the 7500 pixel values I have. For the example, I am writing only 3, n1, n2, n3, but just imagine it will be n1, n2, n3, n4, and then n7500. Everybody is given a weightage over here. Everybody is given a weightage. So just imagine one thing, that for every connection that you see over here, every black line that you see, there is a weightage given to it. So let's call this W1, let's call this W2, and let's call this W3. So what is happening is that for every connection that you're making from N4, and to make N4 in the hidden layer, we are saying that N4, you are nothing but, let's say, you are a summation of weighted sum of all the pixels in the input layer. I will repeat the statement one more time. Please listen to me. N4, you are nothing but a sum of weighted neurons in the input layer. And you might see that I might sometime also write it like this. In some literatures, you might find it that it is written like this: Wi into Ni, where I goes from 1 till, where I goes from 1 till 7500. Correct? In our case, it is 3 right now. So what is happening over here is, my friend, I told you that we are saying that N4, you are nothing but a weighted average of this particular neurons in the input layer. Now, obviously, we know the value of N, right? N1, N2, N3, because these are the input of from the image. So, right? All of you, do you agree, right? We know the value of N1, we know the value of N2, we know the value of N3. Why? Because these are nothing but, let's say, our image pixels. So we know the value. But what is this W now? Where does this W came from, and why it is interfering with us? How do I derive these W, right? And I am going to say a thing which will blow up your mind. These weights are random, because I don't know. I don't know when the first time I am sending my image. I don't know which pixel has more weightage, which pixel to give less weightage. I don't know, right? If I already knew this thing, I have solved my problem. The point is, I don't know this thing, right? So I will take random weights and biases. Now I know most of you are confused. You are saying, Shivam, what? You will take random weights and biases? You are going to definitely blow the mod. But no, we are going to start with random. Listen to me now. We are going to start with random, right? And then this, let's say, process will repeat for N4, N5, N6, and N7 for all of them. And then similarly, at this particular neuron, same thing is going to happen. O1, let's say this is called O1. O1 will become what? O1 is nothing but, let's say, a summation of N4, N5, and N6, right? I can say O1 is nothing but a summation of Wi and Ni, correct? Similarly, this O1 is also made up with connecting with these, let's say, neurons, N4, and then this is N5, this is N6, and this is N7. So what is going to happen? We will complete this chain and we will take all the weights as random for the very first time. We will take them all random, right? We will take all of them as random. Now what is going to happen? Obviously, because we have taken everything as random, this output will not be equal to our expected answer. Do you agree? Output will not be equal to actual answer, right? Do you agree? Output is not equal to actual answer, right? Very good. Now, so this is where the second step comes in. The second step is called as error calculation. The second step is called as error calculation. The second step is called as, let me write down, the second step is called as error calculation. Here we will calculate the error. We will say that model, you are very good. Model, you are very good that you chose all these things, that you have done all these random weights and biases. But my friend, whatever O1 that you are giving, whatever O1 that you have given, right, it is not actually accurate. This is called as error calculation. Let give me 1 second. This is called as error calculation. The output that you are doing is not matching with my actual. And what we will do now, we will penalize the model. We will penalize the model by saying that, hey, listen, this is a very bad thing that you have done, right? And this is actually wrong. That output is not matching to the actual. So go back now. The third phase, go back now. The first phase was sending these weights and biases. The second phase was error calculation. The third phase is back propagation, right? The third phase is back propagation. In the back propagation, we will say that, listen, whatever you have done, go back and change your weights in such a way. See, listen to me now, please. Change weights such a way that error is minimum. These are the two terms that you have to always remember. This should always be your dream. Error is minimum, right? Error is minimum. Do you understand now? So what is going to happen? We will change the weights. How? You can change the weights in such a way that the error becomes minimum, right? We will find the culprit. Who is responsible for the higher losses, and we will actually change it in such a way that the losses decrease. And eventually what is going to happen? We will again do a feed forward, again error calculation, again back propagation, again feed forward, again calculation, again back propagation. This phase will repeat 1 2 3 1 2 3 1 2 3 until at one point our weights will be so much optimized. That the error will be almost zero. It means your output will almost become equal to the actual.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
A neural network is actually made up of three phases. Is made up of broadly three phases. The first phase is called as feed forward. What is that phase? Where the connection is going from input to the output, right? The second phase it's called as, right, and the phase 3 is called as back propagation. That you can use, right? These are the three broad phases. I know for a lot of you it does not make sense. Okay, so these are the three broad points over here. Let's now go one by one on the point over here. Phase 1 is called as feed forward neural network, right? Feed forward neural network. Now what is feed forward neural network? I'll draw the same image that I drew yesterday, right? Let's say that these are the two input neurons. These are the three hidden layer neurons, and these are the two output layer neurons, right? All of you at least are comfortable with the statement layer and neuron, correct? 3. In the hidden layer, how many neurons are there? 3. So all of you are comfortable with at least this statement that this is input layer, this is hidden layer, right? And the next one is output layer, correct? Each vertical thing stack is called as layer, and inside these layers we have neurons. Now see now. Can you also please help me understand how many neurons can a input layer have? How many neurons can an input layer have? I mean, here in this example, you can see 2, but how many neurons generally do we have? As many? No, equal to the number of inputs. So the number of neurons, listen to me now, please. The number of neurons in the input layer number of neurons in input layer are dependent, or let's say equal to the number of features of an image, right? Number of features of an image. Let's actually not write it over here. Let's write it in the paper sheet itself. We write it down. That number of neurons is equal to number of features in image. I would actually say image because that's what we have learned over here, right? That's what we will be dealing with, right? Images. That is what it is. Okay, and then how many are there in the output neurons? Number of neurons in input. How many neurons will you have, my friends, in the output layer? That is equal to the number of categories. Can I say the number of categories in the solution? Correct. So let's say if you are trying to distinguish between three different types of cats, then you will have three neurons in the output layer. Correct. Do you all agree with this statement? Very good. Very good. The first kind of architecture that we are going to learn, that is called as artificial neural network, right? Artificial neural network. It means nothing but, let's say, a neural network which is inspired by human nervous system, but it is artificially used. Correct. That in that particular case that we're going to build over here, and this thing is also called as fully connected neural network. The most basic network that you will learn in neural network is fully connected neural network. What does fully connected means? It means that every neuron has to connect. Every neuron has to connect to the all the neurons in the next layer. I'll repeat again. Every neuron, this one, right? Every neuron has to connect to every other neuron in the next layer. In the next layer, right? This is what is happening. Similarly, we will draw the same thing, and it has to connect to all the neurons in the next layer. So it will connect over here. Right? This is a fully connected neural network that we are making over here. So first of all, we talked about input layer. What are input layers? Input layers are nothing but, let's say, they are carrying neurons, and they are equal to what? Number of features inside a single image. Correct? They are equal to the number of features inside a single image. Very good. So now what neural networks tell you is, neural networks are saying to you that please connect yourself to the next neurons. Please connect yourself to the next neurons. Generally in the literature, when you will read, right, this thing is called as I1, right? They are generally denoted by something called as I, because they're input, right? So let's say there are two input neurons, I1 and I2. And I1 and I2, can I say this thing that I1 and I2 are constant? They bring their value from the images. Their pixel values are coming from the images, correct? If, let's say, for the sake of example, let's say there is an image which has only 2 pixels, let's say there exists an image, and we have entered this image. So I1 and I2 are nothing but those pixel values, correct? We all agree with the statement. I1 and I2 are constant in nature, right? Very good. Very good. Now, the next neurons, I will call them H1, H2, and H3, right? These are hidden neurons. These are what? These are hidden neurons. I will request all of you to please, just for 10 minutes, right? Forget about your pen, paper, pencil, phone, whatever you have, right? Please drop them and just stay with me, right? Please listen to this commentary that is happening over here, because this is what exactly is going to set up the base for you. So these are the hidden neurons, H1, H2, and H3 over here. Now, H1, H2, H3, do they have any value right now? Do you know the value of them? The answer is no. We don't know, right? We know the value of I1 and I2. We don't know the value of H1, H2, or H3. Okay. So what do the neural network propose? Neural network proposes that H1 is nothing. H1 is nothing. H1 is a combination. H1 is a summation, is a weighted summation of all the input neurons. I said a term called as weighted summation of all the input neurons. It means that H1 is nothing but, let's say, weight 1 I1, correct, plus weight 2 I2, and weight 3 I3. Now, what does this mean over here? And Shivam, why did we use weights over here? Why can't we just simply say that H1 is the sum of I1, I2, I3? Correct? Can't we just directly say that what is the sum of I1, I2, I3? That H1 is nothing but the sum of I1, I2, I3. The point over here is, my friend, that we don't know. So the point over here is, my friend, do you right now know that which pixel is important to categorize that image? At this particular point, when you're building a neural network, do you know that which pixel is more important, I1 or I2? Do you know this thing? No, right? And definitely there will be only one neuron which will have more weightage than another one. Do you agree with this statement? Right? So what we have done over here is, my friend, that every green connection that you're seeing, every green connection that you are seeing, my friend, you will give a weightage to it. You will give a weightage to it. So it means when I1 is connecting to H1, we will call this as W11. Right? We will call it as W11. And when I connecting to H1, we call it as WI2. Right? Just for example, we will call it as WI21. W21. So what I've done over here is very simple thing. I am saying that H1 is nothing. H1 is a summation of weighted sum of I1 and I2. Now the biggest question that comes, so I am saying that yes, both the inputs, they don't contribute equally, right? They don't contribute equally, but then what is the contribution? Right? Listen to my question one more time. I am saying, you guys said that, Shivam, we agree that both the pixels might not contribute equally. But do you know what is the contribution right now? Do you know what is the contribution of I1 and I2 to H1? No, right? We don't know. So how is the value of W1 and W11 and W21 be used over here? We don't know. So what is going to happen is, and listen to me now, we will take it as random for the very first time. We will say that we don't know, I don't know. I will take these two values as totally random. I will take them as random. I know now most of you are confused. Shivam, how can this happen? How can you take a random number over here, right? You can't take a random number over here and then just build it. Give me 10 more minutes and I'll explain you why this random is the best approach to take, right? Because you don't have any knowledge right now, right? You don't have any knowledge right now that which one might give you more weightage, right? One of my friends is saying domain expert opinion, all those things. See, my friend, listen, right? Domain expert values, they will work for you. Let's say, even if you have, let's say you are working with a finite number of features, right? Just imagine you're working with an image of 1024 cross 1024 cross 3. Can your SME still tell you that which pixel is contributing more? The answer is no. Domain expert can tell you the business value. He cannot tell you which pixel is giving more value, correct? Right? You can't detect that which pixel is more important, right? Very good. Okay. So now what we have done is, we have, let's say, calculated H1, and similarly we will calculate H2 and H3, right? Any problems in this thing? Remember that, but when you will connect I1 with H1, this will be a different weight. So please remember this thing, that every connection that you're making will have its own different weight. So can someone very quickly tell me how many weights are there in this particular input and hidden ratio? In the input versus hidden, let's say, neuron, how many weights will be there? Unique weights will be there? 6, because there are 2 inputs and there are 3 hidden layers, 3 neurons in the hidden layer. So 6 weights will be there. Very good, right? So similarly, we can build H2 and H3 also. Do you all agree? We can build a similar H2 and H3 model also, right? Very good, very good, fantastic thing, right? We all we all agree with this statement. Now there is one problem. There's one problem, that because W1 and W11 and W21, because they are random in nature, they are random in nature. Can this happen? Listen to me. Can this happen that when W11 is multiplied by I1 and when W21 is multiplied by I2, they both might be same magnitude number but with opposite sign, and they might eventually make H1 as 0. Can this happen? No. Why no? Because W11 and W21 is random, right? It can be any number. Okay, I'll give you an example. I'll give you an example. Let's say that I1 is, let's say, 1, and let's say I2 is 2, and let's say I2 is 2, right? So what are we saying? We are saying W1 multiplied by 1 plus W2 multiplied by 2, correct? What if I say to you that the value of W2 is nothing but -1 and the value of W1 is 2? What is going to happen? This will become 2 minus 2, 0. This can happen, right? So all of you agree that this thing can happen because W1 and W2 are uncontrollable numbers. It might happen that they might lead to a H1 which is equal to 0. Possible, right? I am not saying it will happen every time, but it has a possibility. And that is why, my friend, we will introduce a newer term to make sure it never becomes negative. That is called as a B term, which is called as bias, which is called as bias. Now, bias is not unique for every connection. Like weightage is, let's say, unique for every connection. Bias is unique for every neuron. So this H1 will have its own bias, H2 will have its own bias, and H3 will have its own bias. So you will have 6 different weights, but only 3 different biases. Do you all understand this term? Is it possible? Let me ask you the question again. Is it possible that because W11 and W21 are random in nature? Please listen again. W11 and W21 are random in nature, right? Can this happen that this particular equation, this that I'm going to make a box around this particular equation, which says that W multiplied by I1 plus W2 multiplied by I2, can this become 0? Can the summation become 0? So what I am saying to you is that can we make sure that we add a bias over here? We add a small term called B, which will always make sure that H1 never becomes 0. I will make sure always that W1 and W2 are not negative in nature. First of all, this is not correct, right? You should never assume this thing that weights should not be 0. No. Okay, see, don't think weights as a number, think of them as a weightage. So what does a negative weightage tells you? A negative weightage is telling you that there is an inverse correlation. All of you are coming from machine learning background, and all of you are very versed in something called as collinearity, correct? All of you are very versed in this term called as collinearity, right? Whenever you, let's say, find a correlation, whenever you find a Pearson's correlation, the value is from -1 to +1, correct? What does +1 tell you? If, let's say, there are two features called A and B, and let's say their Pearson's coefficient is going to be +1, what does this mean? It very good that they have a positive correlation and they both are inversely proportional to each other, and they are like this. But what if somebody is saying -1? What does this mean? That they are still proportionate, but they are inversely proportionate, right? So it means if somebody is going over here, the other one will follow the same slope but go in the opposite direction, correct? So weightage does not only tell you it's not a negative number, but weightage can also tell you that this particular pixel has a opposite or an inverse relationship with the output. Do you all understand now why weightages can be negative and why they are important? Please, I know that we are choosing them at random and I can control them that they cannot be negative, but I want them to be negative, my friends, right? Because negative correlation actually helps me to understand that that particular input feature has a negative relationship between the model. And all of you know, right, that in machine learning, it does not matter if you have a positive relationship or a negative relationship. We are looking out for features which can distinguish between the output. For the time being, bias is also going to be random, right? But bias can never be 0. We will make sure that bias is random. It can be positive, negative, but bias cannot be 0. And again, see, listen, right? Bias there's one more thing, right? It might happen that later on, when the model is optimizing itself, and later the model says that, listen, I do not want these for this particular H1. I don't want I1 and I2. And it might happen that the weight might become 0 and the bias might also become 0. But at that time, the model is showing the confidence that I have checked the error. And if I make them 0 right now, then they are best for the losses, right? They are giving me the best losses or the lowest losses. Please listen to me one more time right now. What I'm saying, please listen to me. Right now, I am saying it is our responsibility to make sure that neither of the 3 features are negative in nature, because then we are killing them intentionally, right? We are killing them unintentionally, sorry. But later on, let's say, if the model optimizes itself, and model says that, see, I have the evidence that if you make these weights, this weight and this bias 0, my losses are going very low. This is what we want, right? So what we are doing right now here is we are taking a countermeasure that because not of our random values, they should never become zero. And that is why we are doing over here. Some of the neurons is redundant in case of zero. Might happen, but for your safety, but for our safety, we should not assume that anything can be negative. So that is why we will always pay full attention to everyone, and we will never make anybody intentionally zero. Later on, if the model thinks that yes, these neurons should be dead and they should have zero value, definitely it can be. Again, I am saying, I will repeat the statement one more time. Please listen to me. Please listen to me. It is our responsibility, yours and mine responsibility, to make sure that we are not unintentionally muting a particular hidden neuron. Correct? We are not unintentionally, let's say, muting a neuron. That's why what we do is we make sure we add a small bias to it. And bias is a different, let's say, case also. I'll explain you what this different case is. But later on, it can happen. Again, I'm repeating, it can happen that this W1 can be zero, W21 can be zero, and this B can also be zero, because the model has decided that for the benefit of lower loss, it figures out that this neuron should be dead. We have said that the H1 will have a linear relationship, right? Linear relationship with I1, I2. Now, what kind of relationship this is, we don't know. And we have taken random weights and random biases over there. And those of you who are asking me about what is bias over here, see, do you remember this equation? Have you seen this equation? Have you seen this equation? Y is equal to mx plus c. Very good. This is a straight line equation. Exactly. It's a straight line equation, my friend. So what does this do now? What is this C? Do you know? This C is called as intercept, right? This C is called as intercept in over here. And this M is called as the slope, right? I just, let me revise you these, let's revise this particular thing. So whenever, let's say, you are drawing a straight line, this particular thing, this particular area is called as C, where the y-axis, where the line cuts the y-axis, and this particular distance from the zero is called as C. This is called as the constant or the intercept, correct? You all remember? Now, what is this doing? If, let's say, if I keep changing this value of C, what is happening over here? Does the inclination of the line changes? The inclination of the line does not change. The line stays as it is at that particular angle. Only the elevation of the, let's say, line might increase or decrease. It might go up here or it might come down over here. Correct? And let me show you this example in real life also, right? Let's quickly import numpy as NP and matplotlib.py plot as PLT, right? And PLT, let's say we will have equation of y is equal to 3x plus 5, right? So we can say PLT dot plot for I in range -10 till 10 and 3 multiplied by I plus 5, right? This is exactly what your line looks like when you draw this thing, right? And if I change the slope now, if I change the slope to, let's say, 7 or 8, right? Nothing is going to happen. The slope remains the same, only the inclination goes up and down, right? And now let me draw the same for you with a 3.
Let's have a quick quiz question, guys. And the question is, what is the purpose of reinforcement learning in AI? And your options are to mimic human decision-making processes, to enable machines to learn from data, to optimize a system by trial and error, or to analyze and interpret visual information. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Do you all see what is happening over here? So now, why did I give this example to you? Why did I brought this particular example over here is, my friend, you need to understand that the value of bias is nothing but, let's say, moving those. Yeah, these are three lines, but do you see that slope is not changing? Because the inclination of this line is dependent on this particular term 3, in this particular term 3, correct? Do you all agree? Even if intercept changes, m is constant. Exactly. Very good, very good, very good, right? So the intercept is nothing but it is moving the elevation of the line up and down. And if you just imagine the same thing into a hyperplane, right? Does anybody know a hyperplane equation? If I convert the same straight line into a dual 2D plane, what it is? Okay. So this is like nothing but, let's say, somewhat like this. Just an example. Just an example, right? Okay, so sorry. Right? No, this is not hyperbola or ellipse. This is a plane equation. A plane means the line which is in 3D, like this. This is called as a hyperplane, right? It acts as a straight line in the three-dimensional world. What are the three dimensions? This is dimension 1, this is dimension 2, and this is dimension 3, right? So here also, if you increase this 5, the slope does not change, but this plane will move up and down, correct? This plane might move up and down like this. This is called as a hyperplane. All of you understand? So bias will do nothing, right? Listen to me now. The bias, the use of bias in our term is nothing but to make sure that we do not accidentally, let's say, negate a particular neuron at the very first step. Do you understand now? That is why we use it. One of my friends says, so bias is generated by a model to counter nullity of neuron if the case in the input are cancelling each other. Not cancelling or not. It does not know about this thing. See, listen. The bias is not an intelligent term. It's just a term that we have added up over there, right? And again, see, because a linear relationship cannot be just drawn with the slope, right? We need a constant term over here. Whenever you design a rope, whenever you design a line, listen, right? Whenever you design a line over here, see, this is a very important thing that you're asking. Very good question. That whenever you're designing a line over here, see, you cannot make a linear relationship until and unless you design its. So this is what your relationship is. Just give me 1 second. Yeah, here it is, right? So what is happening over here is, can you design a line? Tell me one thing. Can you design a line which is just made up of slope? No, right? No, you cannot, because then there can be infinite number of solutions that can go on. So you need two terms. You need a slope to tell the inclination, and then you need an intercept to stop it at an anchor of y-axis. Very good. So let's go back to our images that we were talking, right? So, okay. Any questions in this particular topic only? Please ask. In this particular topic, please. Right? So what I have done over here is that, let's say, assume a model with 2 input neurons and 3 hidden neurons. Definitely loss will also appear. And again, see, listen, right? Some of you might be a little bit on and off over here, that because things are not making sense to you. Do not worry. This is very normal. This is very normal. But once you'll get the whole picture, and I think just today only, when you'll get the whole picture, you'll understand this thing, right? Be with me. Just be with me. Okay. So what are the equations? Can I write down the equations very quickly? Can I say that H1 is nothing but H1 is W11 W11 I1. Let me say multiplied by I1 plus W21 multiplied by I2. What will be H2? Keep on saying what is H2. H2 is H21 multiplied by I1 plus, and this will be B1 also. And then W22 multiplied by I2 plus B2. Very good. Very good. And can somebody help me with H3? H3 is nothing but W31 multiplied by I1. This is multiply. I will and ampersand. I'll zoom in. Give me 1 second. I will just zoom in, but give me. Okay. See over here now. Do you agree with the statement? What I've done is I've written the equations for H1, H2, and H3 over here. H1, H2, and H3 over here. Do you all align with them that there are 6 unique weights and 3 biases? Do you understand this term? 6 weights and 3 biases. Weights are unique for every connection between neuron, right? And bias is common for a neuron in hidden layer. Do you all agree with this term? And I've written over here these 3 equations and then this particular term. See, how do you read this thing? See, let me tell you, how do you read this thing is W21 is actually W12. Wait. Okay, this is wrong. No. I'll tell you what is wrong. Wait. This is 1, 2, and this is 22. This is 23, and this is 30. Sorry, I corrected. Yes, my mistake. So how do you read this thing? See, again, this is just variable names that we have given over here, but how do you read this thing? Let's say if somebody says to you, no, why it is confusing? See over here. This is just a number that you have given. There are 6 unique weightages. You can call them anything that you want. W1, W2, W3. But how do you read them? See over here. There is a nomenclature of how do you read them. 31 means that you are going from first neuron to the third neuron. Right? This is how it is read. So let's say if you are let's say reading about W31 means W13 means that you're going from first neuron of the input layer. From here you are going over here. This is how you read them. How many unique weights and biases will be there? Listen why it is correct. See over here now. How many connections are we making? Connection 1, connection 2, connection 3, connection 4, connection 5, and connection 6. 6 weights are required. Everybody agrees, right? Everybody agrees with this statement, right? Now please tell me how many biases will be required. Now please see the previous equation and tell me how many biases will be required. No bias. Why no bias? No, there will be 2 biases over there. See, what did we learn in the last session? Sorry, in the previous connections, that the number of biases are nothing but the number of neurons in the next layer for the calculating layer. So in the calculating layer, how many output neurons are there? O1 and O2. So O1 and O2 will have their own individual biases over there. Do you understand this thing? I will say O1 is nothing but, let's say, a combination of H1 and H2 and H3. And O2 is nothing but a combination of H1 plus H2 plus H3. Now I will give them some weightages. Let me call them WH11, right? WH, why? Because they're the weights for the hidden layer, right? I'm giving them 1, 1. This one is what? This one is coming from 2 to 1, and this one is coming from 3 to 1. Correct? Do you agree? I have given the weight names as WH, so please don't get confused, right? This is just WH. WH21 multiplied, and just copy this same over here, and then we will have a bias also over there. Let's call them BH1 and BH2. What did I told you? I told you that, my friends, weights is nothing but, let's say, a connection between input and output. Correct? Right? What is weights? Weights is a connection that you are making between your hidden layers and the output layers, and everyone will be unique. Correct? Everyone is going to be unique. Weights is nothing but, let's say, a connection between 2 neurons, right? And it has to be always unique. It has to be always unique. But what is a bias? A bias is a term that is made for that particular neuron for which you are calculating this term. So we are calculating for what? We are calculating for O1. Now, how many weights are connecting to O1, or how many neurons are connecting to O1? 3 neurons. So we will have 3 weights, right? We will have 3 different weights over here. Wait a second. This is 1, this is 2, and this is 3, right? 3 weights are there. But for these 3 weights, we only want 1 bias, right? So O1 will have its only 1 bias. That's it. O2 will have its own 1 bias. That's it. Correct? Even if it has 10 hidden layers, 20 hidden layers, all of us can make the equations, correct? And we can reach to the final output, correct? Very good, very good. And now imagine, now what we can do is we can change this h1 to something else, right? We can change this h1 to the previous values, we can change this h2 to the previous values, and we can enter all these values, correct? We can, let's say, substitute these values of h1, h2 and h3, and we'll get the pure numbers. So what will be eventually be left with? If you notice, right, your output, let's try to do this thing, right? What is your O1? Your O1 is nothing but, let's say, WH11 into this H1, right? And can I get the value of H1? Yes, I can get the value of H1 over here. See, I don't want to, let's say, show you this complex, and it is actually not complex. This is just a simple mathematics, right? But I'm just showing you that eventually what is going to happen, your original numbers I1, I2 will be there, and then your random numbers that you have generated, those will be here, right? Can I say this thing, that the final output is nothing but a combination of multiplication plus and addition of nothing but your input layers with the random weights that you've chosen, correct? Can I say this thing? What I have done is, my friends, in this particular equation, O1 equation, I have replaced H1 with the previous values, right? Simple, nothing, right? Simple things. And if you notice over here now, if you solve this particular equation, right, you're left with nothing but, let's say, your random number, random number, random number, random, and these are your known numbers, correct? This is the known number, this is the known number, this is known, this is known, this is known, and this is known. Do you all agree? Do you all agree with the statement that the O1 is made up of nothing but our random weights that we have taken and the inputs, correct? Eventually inputs are being carried till at the end. Okay, now tell me very seriously, tell me with this seriousness, right, that you have taken all this random thing, right? Do you really think that this particular operation will generate the correct answer for you? This one, will it generate the correct answer for you? But I am saying no, it cannot. It can never produce the correct answer because we have taken everything random. It means you are saying that, Shivam, if we multiply any random number, right? If we multiply any random number to our inputs, can we get the data? Correct answer? No, it will produce random answers. Very good. It will produce random answers. One of my friends says we have an equation. What's the expected output pixels? But no, do you understand my question? I'm saying to you, you have your questions, right? You have your questions and you gave it to some equation, but with the equations, you're multiplying them with random numbers. Will it generate the correct answer for you? I think it will produce random answers for me, right? No way. Very good. Exactly. This is what is going to happen. And this is what, my friend, we come into the second phase. This particular phase that we did, my friend, when we are traversing from input to output is called as feed forward. This is called as feed forward. This is the first phase of your neural network. Do all of you understand this thing? Till now, what we have done is we have sent our input pixels to the output. This is called as feed forward neural network, right? Very good, fantastic, awesome, Abhi. But see, the problem here is that we have done all these things, but it is yielding us nothing. It is yielding us nothing, right? So then we enter into the next phase of the phase two. The phase two, which is called as what? Error calculation. Now, obviously, you have done all this random thing, right? Will it eventually end up to the correct answer? The answer is no. It will never give you the correct answer. So what is that? There is a kind of a small police, right? Who's standing there, and he'll say that, listen, friend, whatever you have done, whatever your weights, biases, whatever you've done, you have to calculate an error. And let's, for a time being, let's say that this O1 is nothing but, let's say, the Y predicted, right? What your model tried to predict, right? So there are two terms. There are two terms over here, Y predicted, and the other term is called as Y actual. Now, because this is the training data, you will have the labels, correct labels also with you. Say yes or no. Because the client has given you labeled data. So for every image, you will have its correct answer also, right? and you have a predicted answer also, whatever the model is trying to predict with the random values. Correct? Everybody understands this thing? So what is error now? Error is nothing but a simple thing which says y predicted minus y actual. That's it. A very simple term. Error says that, hey, listen to me. This is what it is, right? You are y predicted minus y actual. That's it. And then the model says, listen, my friend, you have done a lot of mistakes. And obviously this number is going to be very big. One of my friends says, do we always have labeled data? So my friend, you guys are coming from machine learning. Can you run any machine learning model if you don't have the output numbers? Can you ever run a machine learning model if you don't have the labeled, or let's say that if you don't have the y with you, or if you don't have the outputs with you? No, right? The same thing happens here also. The same thing happens here also, that you need labels. Correct? One of my friend is saying forecasting. So even for forecasting, my friend, you have the data, right? Correct? Okay. You need labeled data over here, right? You need y actual to be over here. Now see, listen now. Okay, tell me, there's a situation. There's a situation, tell me. Let's say you are the judge. You are the judge and you run your own court, and you are very angry because every day there are multiple cases that come up. There is this case one, very simple guy. He was in the emergency, and what he did is he did jaywalking, right? Simply just walked on the road when he was not allowed to walk on the road, right? And then this another case is this very serial killer, right? There is this serial killer who has done some, um, 20 serial killings that he has done, right? He's a very dangerous person. Will you give both of them the same penalty? Will you give them the same course of punishment? No. Why no? You should give them the same punishment, right? I mean, they both are guilty. They both have agreed that they have said they did some error in their life, but will you give them the same weight? Will you give them the same charges? No. Why? Very good, very good. One of my friends says that it depends on the error that they have done. All right, depends on the charges will be different based on the issues that they have done. Correct, right? Very good. This is exactly what machine learning also wants to do, or the deep learning wants to do. It wants to penalize the model. It wants to penalize the model, as one of my friends is saying, on the severity of the crime. Exactly, the deep learning also model wants to not just give you an error. It wants to give you a balanced error. If you have done a very small error, it will say it's fine. It's fine. Okay. I mean, thank you so much. You did all this thing, but it is fine. Right? Whereas if you've done a very big error, the model will try to penalize you at a very higher rate. Right? It is trying to penalize you at a very higher rate. And to justify this particular, let's say to give a penalty based on the severity of the error, there is one very important function that we always use, and all of you might have also used, and this particular thing is called as squared function. All of you remember this function, squared function? Remember, the graph is how? The graph is like this. The graph is somewhat like this. So one of my friends says mean squared value. No, I'm talking about only squared errors. It means, see over here now, I'll explain it to you. Wait. The graph of this particular thing is made somewhat like this. If I draw it only on the positive side, and if I show you, right, it is somewhat like this kind of thing, right? And a very interesting thing that you might have noticed is that if you draw a line y is equal to x over here, y is equal to x over here, and if you draw y is equal to x squared, you will notice a very interesting trend over here, that the line y is equal to x remains on top of y is equal to x squared for a certain period of time. And then later on it goes below it. And this particular point is called as 1, 1. Now what does this denote? This denotes a very interesting fact. It denotes that if that particular number is less than 0, see the fact over here. If you multiply, if let's say if you take a square of 6, what is square of 6? 36, correct? The number increases astronomically. Correct? The number increases astronomically. But if I take the same number, 0.6 to the whole square, this becomes what? 0.3. Is it increasing or decreasing? It is actually decreasing. This is what the concept of squared is. If somebody asks you, why do you take a square of the error? Now, do you know the answer? I know whenever I ask this question to a lot of folks, right, they always say that Shivam, to make it positive, right? If the error is negative, we want to make it positive. No, you can take an absolute of this also, right? Then you can use this y is equal to modulus, sorry, y is equal to absolute of x also. That can also make it positive, negative terms to positive. What is the correct way and why do you take it? Why do you take a squared error? This is the correct answer. Because on the balancing act of penalizing. Do you all understand now? This is what the power of penalizing it. That penalization thing says that if you're a very small error, if you're like a small error like 0.6, it's okay. It's okay. It's fine. You can go away. Even your error is 0.6, it will say that I will penalize you only 0.3. See now, it is actually it is actually increasing, right? It says 0.6, it's fine. It's fine. I will give you even less. I will give you 0.3 also. Correct? You can see over here in this particular chart. If the x is 0.6, it converts that number into 0.3. But if your errors are huge, if your error is 60, then your square becomes much more larger. It becomes 3600. And remember, this is not a linear relationship. It's a parabolic relationship, exponential relationship, correct? When you cross the boundary of 1, then it will increase. Exactly. This is what you can see over here in your graph also. That is why I always refer to my folks that please understand the depth of graphs. The graphs can explain you the nitty-gritty of everything, right? Graphs should be your best friends. Range must be 0 to 1 for error. Yes, if your error is less than equal to 1, then you will be either reduced or equal to. But the moment you increase to 1, you are now increased, right? So 1.1, when you square this thing, it becomes 1.21, right? Why is penalizing result in our neural network output? Because the model needs to teach you a lesson, right? The model, the error that you have taken by taking random things, my friend, the model needs to teach the lesson. The error, the second phase of our neural network will teach a lesson to our model that, hey, listen, whatever rubbish that you have taken is absolutely nonsense. Go, and I am slapping you with a penalty. Go and correct yourself. That is why we need a penalizing thing over here. Do you all understand that why do you take a square in your machine learning also? Don't try to now join the weights and error for now, right? Don't try to join it, right? Right? Let's do one more thing, right? And this is what it is. The next thing that I want you to spend some time on is single cell neural network system, right? Or it is also called a single cell perceptron. What does this mean? It means that, let's say, just think about it, that there is only, let's say, one neuron. That's it. Input I is coming. You have a W associated for it, and then you have a bias over here. And this is generating output for you. And this particular, let's say, thing is for, let's say, making your calculations much more easier, right? To make you understand. I think I might have recommended you a book called as Neural Networks and Deep Learning Chapter 1, right? If you go into this book also, right, they also start with a single cell perceptron system to make this thing, right? So what we are going to do is we are going to talk about this thing. Same thing happens, right? Same thing, whatever we have learned. It is just that now things are going to be a little bit trickier on the calculation side. So just to reduce that calculation burden, what we are saying is that we will take only a single cell neuron, that there is only one input that is coming in, only one weight that is required, one bias that is required, right? And there is one output which is there, correct? So can I say this thing that this O1 is nothing, this, sorry, this O1 is nothing, but let's say O1 is I1 W1 plus B, correct? right? And this O1 can also be called as Y predicted, right? This is the prediction that the model is trying to do. Your deep learning model is trying to do, right? And for every prediction, what will be there? There will be a actual term also, right? Because this is a labeled data. So for every I input, there is a YA, which is called as the Y actual. Do you agree with the statement? Right? That for every input I, there will be a YA, which is what? Which is nothing but, let's say, the actual answer of this thing. Correct? So let's say this was the phase one. This was what? This was P1. P1 is when you calculate the feed forward neural network. What is P2? P2 that we learned was error calculation. Error calculation means the error says that error is equal to Y predicted. I will write it down as YP minus YA. Correct? Do you agree? Do you all agree that error is what? YP minus YA. Now see, can I say that YP is nothing but, let's say, I1 W1, right? For a second, right, you can please forget about the bias, which is just an additive term. Just forget about it just for 2 minutes. YA. Do you agree with my statement? What I just simply did, I said that Y predicted over here is nothing but, let's say, this Y predicted was nothing but, let's say, I1 minus or I1 W1 plus B. Correct? I said this thing. A very simple term over here. Now, do you see over here who, let's say these are the 3 terms now we are left with, right? These are the 3 terms now that we are left with. Do you think who is responsible? I1 is the constant. I1 is a constant and it can never be changed. Correct? It is the pixel value of an image. It cannot be wrong. That's a constant term. Do you agree? The YA cannot be also wrong because YA is the actual answer. So who is responsible for the error? We are actually trying to find the culprit of this thing, right? We are trying to find that who's the culprit for this particular error. IA cannot be there because it is input. YA cannot be there because it is the output. So who is remaining? Remaining is this term B over here, right? This term B over here. This guy B, right? He is the one who's the culprit, right? Where is the bias? That is why I'm saying please pay attention. Okay, so W is the one that all of you think that is responsible. Do you agree? Right? W1 is the one that it might be the culprit, and it looks very similar that there are only 3 terms, 1, 2, and 3. 1 and 3 cannot be, let's say, culprits because they are the ones which are the real constant values. They cannot be changed. So it is 2, which is the way responsible for all these things. Very good. So let's now come back to the system. Let's write down again that E error is what? YP minus YA, which I can also write down as I1 W1 I1 W1 plus B. I will now write down what my friends were asking, and then YA. So there are 2 terms, W1 and this B. These are the 2 people who are responsible for the weights. Now tell me one thing, my friend. Tell me one thing. When you are doing this thing, what is your objective? Can I say that our objective is to minimize this number E? Can I say this thing? That our problems will be solved. Our problems will be solved if this term E is reduced to 0. Or eventually, I am trying to say that YP should become almost identical to YA. Correct? It means my model is saying whatever is the actual truth or close to what the actual truth is. Do you all agree? So the term E should become 0. Very good, very good, very good. And this is now where, my friends, the third phase of your neural network starts. The P3 starts, which is called as BP, back propagation. Right? This is also called as back propagation. Now, what is this BP over here? This back propagation says that, okay, understood. We have now 2 facts over here, that input is not wrong. YA, the output is not wrong. It is just the random weights and biases that we have taken, right? All of you agree? The first statement. And the second statement is that our life's motto is to make this error as close to 0 as possible. Correct? These 2 statements are true. Very good. Now see over here, what I will do is, my friend, I will try to draw a graph between error and the weight W1 over here. what I'm doing is I will, let's say, calculate that for each value of W1, my friend, what is the error, right? Let's say this kind of a graph comes up. Let's say this kind of a graph comes up, right? Now you tell me, my friends, which one should I take? Should I take this point called P1? Should I take this point called P2? And should I take this point called P3? According to you, my friend, which part should we focus on? Remember the two objectives of your life. The first statement that I said is that the one who is responsible for the error is W1, right? And the second is our life's objective is to minimize the error, right? To get as much low error that we can get. Now tell me, if I try to make a graph, a very simple graph, right? What I did is that I took all the values of W1 which are possible, and I tried to see what error is coming, right? Because W1 is random, I can take anything, right? And I have just plotted the across E, and you see that there are three major points: is P1, P2, P3. What do you want? Where should we go? We should go to P2. Why P2? Because P2 is the point where error is very much close to zero, not at P1, not at P3, right? P1, P3, it is not closer to zero. Where it is closer to zero? It is closer to zero at P3, P2, sorry, P2, correct? I'm taking a pause over here. Please sink in yourself into this thing, right? Does this make sense? First of all, minimize the error. Take the graph, try to make a graph between the error and the weights, right? And then using this thing, where do we want to land? We want to land at the point where it is P2, right? Closer to it. Very good. Now, how do we figure out P2? It's not that you and me are going to sit down and we are going to draw a plot for every weight, right? We will not do that. We need to figure out a way to do this thing, correct? We need to figure out a way to do this thing. How do we do this thing? This is where our friend mathematics is going to help us. My friends, in your high school mathematics, you might have learned this one thing called as derivatives, right? Or differentiation. This term called differentiation or derivatives, right? Now, differentiation is a term which says that, let's say, if you are trying to, let's say, there's a graph, right? Let's say there's any function, right? If there is any function, if you take a slope of it, right? If you, or let's say, if I just say in very simple terms, right? Not in a very mathematical term, I just say over here that, let's say, if you try to draw a tangent over here, which is perpendicular at that particular point, right? If you draw this thing, wherever it becomes zero, wherever that derivative becomes zero, that is the point of turn. That is the point of turn. So what I'm trying to say over here, please listen to me. Let's say that if we have a graph like this, and now, my friends, if I try to draw some tangents over here, like here, this point, sorry, I could not close it up very clearly. Let's say this point, very close. Let's say this point, very close, right? And let's say these points, this third point, right? Let's say this line is called line 1, this is called line 2, this is called line 3. So let's say if you start drawing these lines at the tangent, right? The line 3 is the line which will give you where the turning point it is, right? Or you can say slope is 0. Exactly. We need to figure out the place where the slope is 0. And this can be found by what? This can be found by differentiating that particular error with respect to weight and say that that point is equal to 0, right? See, I'll explain you again in two terms. One is the mathematical term, right? Mathematical terms means nothing, that we have to figure out the point where the graph is taking a turn, and this point we have to figure out where the slope is what? Where the slope is parallel to x-axis, where the slope is parallel to x-axis, correct? Right? This is where the graph is taking a turn, right? And how can we figure out? Mathematically, this can be done by doing differentiation of that particular function, which is error for us with respect to weight, right? With respect to weight, and we will say that is equal to 0. That is the point where it is, right? So if we go back to our, let's say, whole equation back where we were, so it means what you have to do, you have to go back. Yes, here it is. And we will say what? We will say that we have figured out the culprit. And who are the culprit? The culprit are weights and bias. So what we will do is we will find the differentiation of this error with respect to bias and weight. Listen to me one more time. I am saying to you that we know that the culprit is the weight and bias. The culprits are weight and bias. So we draw this kind of particular graph and we wish to go to the point P2. Correct? We wish to go to the point P2. Now, how can we reach P2? We can reach P2 by using differentiation of that error with respect to the weights and the biases. Now, what is going to happen over here? The thing that is going to happen over here, please again see now, just for 2 more minutes. Let's say you were here. Let's say you were here and you wish to move to this point, correct? Let's say currently you are at this particular point called T. Let's say that your weight is over here right now, right? And it is producing huge amount of error. You wish that you could go to the point P2, correct? Right? Based on this particular method, my friend, right? Based on this particular method, my friend, what we will do? We actually will change our weights now. Please listen to me very carefully. What we are saying is we will say that weights, listen to me. You have a problem. Please update yourself in such a way that the new weight is equal to old weight minus dE by dW. Sorry, give me 1 second. Sorry, I'll just draw it again. No worries. So where were we? We were saying error is equal to YA, sorry, YP minus YA. YP was what? I into W plus B minus YA. We figured out that the person who's responsible for this error is W and B, correct? So we said we will go to the third phase. Which is called as back propagation. And in back propagation, we figured out that we will calculate the gradients. These are also called as gradients. In some of the literature, you will read them as gradients, differentiation. Please do not worry. Both of them are same thing, right? These are called as gradients. And now listen to me, what I'm saying. I am saying that let's draw that graph also. This was the graph of error with respect to, let's say, weight. And we were saying that, let's say this is the graph like this. We want to achieve P2, right? And let's say currently we are at this point called T1. So now what we are saying to our weights, that weights, listen to us. Please update yourself. The new weights is equal to old weight minus dE by dW. And similarly for base also, bias new is equal to bias old minus dE by dB. What is going to happen now? We will take a small step towards P2. We have not taken the complete step, but we will slowly move towards P2. This is called as back propagation, and this moving of gradient slowly towards the lower point is called as gradient descent, right? I know there are a lot of terms I have said in last 10 minutes, but the basic, if I talk about it in very basic English terms, does this make sense to you? What have we done now? Do you understand now that why we have taken the random weights and now how are we optimizing them in such a way that our errors are reducing? How do we calculate dE by dW? dE by dW is a term. I will show it to you right now also, don't worry. dE by dB will be 0, isn't it? No. So see, we are not equating it to 0. We are just calculating dE by dB and then subtracting it from the original weight that we have taken and then updating it. So what is going to happen? Again, let me again specify this thing with more intensity over here. That please do not think that if you have done 1 minus, it will automatically come to this P2 point. No, it will take a small step towards P2. And you have to now keep on iterating this P1 feed forward, then go to again error calculation, and then again do a P3 back propagation, and then go back again do a P1 P2 P3, sorry, P1 P2 P3. So you have to repeat this P1 P2 P3 until the point either your error almost becomes zero, right, or at a point where your error is no more reducing now. Do you understand? I'll repeat one more time. What I'm saying is, my friend, that when you do this particular, let's say, weight updation, this process is called as weight updation that you have done over here. This thing is called as weight updation. You have updated your weights. So does this mean that you have reached to the point P2? No, you have not reached the point P2. What you have just done is you have taken a small step towards P2. So you will have to repeat this process of phase one of, what is phase one? Feed forward neural network, then error calculation, EC, and then BP, which is back propagation. And now once you have updated your weights, you will go back again to FF, then again to EC, and again to BP, then again to FF, EC, BP, FF, EC, BP, FF, EC, BP. Correct? And you will do this until and unless your weight becomes zero, or your error is not decreasing anymore. It means that you have been doing it for last, let's say, 10-20 times, and the error is coming out to be same. It means that is the most optimal that your model can become. Is this done for each weight in this layer? Yes, for each and every weight and bias that you have taken in your model, this step will be done. If your error is increasing, then obviously we are not doing it correct, right? So obviously you have to stop it. Correct? You have to update every weight. You have to update every weight. Every weight will be updated. So let's take an example that in your neural network you have three weights. Just an example. You have three weights. So all the three weights will be updated according to their old weight minus DE by DW1. Right? The error differentiation is calculated according to W1, and this will be updated by W2 minus DE by DW2. So we are updating each weight according to its own previous state and how much they are culprit for increasing the error. Correct? Okay. See over here now. This is feed forward neural network. Second, what we are doing is we are doing error calculation. Now, what is error calculation? Error is equal to, can I say, y predicted minus y actual to the whole square? Can I say this thing? Keep saying yes or no in the chat. I am taking a squared error. Correct? Now, those of you who know differentiation, very good. It's very good that you should know. Those of you who don't know, which is fine. It is fine if you don't know, right? Now, I want all of you. Okay. Can I say this thing? Can I say this thing now? What I've done is I have replaced the term by predicted by the input and output. Okay. Please tell me, if I take a differentiation of I1, W1, those of you who know differentiation, very good. I need your help over here. W1, B1 minus Y actual. Can you please help me differentiate this term with respect to W1 and a square of this thing? Can you do this thing for me? First of all, you have to solve for a problem. Forgot kya? You have to solve for a problem. First of all, you will say 2. Then you will say exactly like this. I1 W1. You have to write down as it is the whole thing. I1 W1 plus B1 minus YA. And then you will solve the inner term. The inner term that comes out to be I1. Correct? Okay, fine. Can I say that DE by DW1 is nothing but 2 times Y predicted minus Y actual into I1. Can I say this thing? Say yes or no. Is there anyone who does not understand? My friends, those of you who are not aware of differentiation, it is very simple, right? I mean, you don't need to worry about it. But let's say whenever you are solving for any differentiation, right? Let's say if you are solving for, let's say, any power, let's say it is x cube, and you are differentiating it with respect to x. what is going to happen? You have to solve it for the power first. So first of all, you have to bring the power into multiplication. So 3 multiplied by, then you will say x, and whatever is its power minus 1. So 3 minus 1. And then solve whatever is inside. So whatever is inside, it is only x cube only. So we will write it down as it is 1. So this becomes what? 3x square. Correct? That's how we have solved it. First of all, we solved for power. Power came over here multiplied by, and then what is the power? 2. 2 minus 1 is as it is, I wrote down. And then inside we went the term I1 multiplied by W1. So it is respect to W1, we will write down I1 as it is. Again, it is fine if you don't understand. Those of you who have studied this thing long back, this might be a revision for you. And those who have not studied, it is fine. It is fine. What is dE by dB? 1. Similar. What? 1. Right? So it is like this only. Correct? See, this is how you can do it. Right? So now what will be the equation? Now W1 is equal to what? W1 minus dE by dW1. And what is bias? Bias is B1. That is equal to B1 minus dE by dB1. And now again, we will go with these new weights. With these new weights now, let me write down W1N. N means new, right? I will also write down N is equal to new, right? So now what is going to happen? We will again go on the top. We will go on the top, and now instead of W1, I will use W1N, new one. And again, I will start this calculation. So this process will keep on repeating for feed forward, error, and then back propagation. This step is back, right? Okay. Do you know that dE, what is the sign of dE by dW? If somebody is saying that my differentiation, and those of you who know differentiation, what is the meaning of differentiation being positive or negative? What does this mean? Anybody? Slope what? Slope positive, negative. What does this mean? I'll tell you. See over here now. All of you, focus here. So let's say if you are here at this point, let's say this is your original W1 that you have taken randomly, and you need to reach at this particular point, right? You need to reach at this particular point. So at this particular point, my friend, your slope will be downwards, right? Your slope will be downwards, and that is why your slope will be positive over here. The slope will be positive over here, and you will be scrolling down at this point, right? You want to reach this point. So that is why we say W1 minus dE by dW, right? And eventually your W1 will decrease, right? Sorry, increase. Sorry, I said decrease. It will increase. Sorry. I'll repeat again. I said I said the wrong term. Let me repeat again. I said then in negative positive, I confused you. Sorry. See over here now. This is the point where you want to reach, right? This is your P2 point where you want to eventually reach. And let's say this particular point at W1, you are here, right? You are here at this particular point W1. Now tell me, if you draw a slope at this particular point, in this area, your slope will be what? Your slope will be negative. Right? Those of you who know, very good. Those of you who don't know, this will be a negative slope. Why it is a negative slope? See, remember, whenever you are going from this, like this angle, this is always positive. And whenever you're coming from top to down, that is negative, right? So what is happening over here? You have a negative slope, correct? Do you agree with my statement? My friend who asked this question, Bhaskar, right? So this is a negative slope, correct? Now tell me, if you have to reach to this particular point from W1 till P2, if you have to reach to this point, right, from W1 to P2, you need to increase your value, correct? The W1 will eventually increase because on the x-axis, this number has to increase to reach to P2, correct? So now see over here what is happening. What does our formula say? Our formula says that W1 minus, and then you obviously know that your dE by dW is also negative, right? Your slope is negative. So this is dE by dW. So this becomes what technically? Technically, we are adding up this thing. W plus dE by dW. And we are slowly adding some fraction to it, right? And it will slowly move towards down. So, right? It is slowly moving towards P2. Do you agree with the statement? Let's consider another scenario. Let's consider another scenario in which you are already, let's say, towards the left hand side. Let's say that now you are at a different position. Give me 1 second, I'll just delete all this off. Let's say in this particular case, my friend, fortunately you are over here. Your W2 is over here, right? So if I draw a line over here, your W2 is actually very big, right? And you need to decrease the value of W2. But if you draw a slope over here, this slope is going to be positive, right? This slope is going to be positive. So what is going to happen? You will say W2 minus a positive slope, So eventually your value is decreasing, DE. So your positive and negative is nothing, my friend. Your slope is controlling that particular thing. See, the minus sign is actually just a constant over here. The control is done by the gradient. The gradient knows this thing, that are you on the left hand side of the lower value point, or are you on the right hand side of the lower value point. Based on that, it will add or subtract. There are different optimizers that we will learn. One is called as gradient descent. One is called as stochastic gradient descent. Another one is called as batch mini gradient descent. So all of them have different techniques that, do we need to update ourselves after every one image, or do we need to update after some X amount of images, or do we need to update ourselves after seeing all the images? Based on that, we will decide. But generally, we divide it after some X number of images, which is decided by our batch size.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Introduction to Kiras. I am going to and use only pandas, right? We understood the concept of learning rate. We understood the concept of back propagation. We saw that if you take an error of squared error, how do you back propagate this thing? That was a very simple solution that we took of a single neuron system, but we made our own neural network, which gave us the understanding. It gave us an understanding of how things work eventually when a neural network works, right? We have understood that deep neural network is a concept, and we studied about the whole concept, how it got inspired by the humans, what is the math involved in it, and we understood the main concrete engine also, right? That how it works. It starts with random. It says that there are some random relationships, but the relationships can be altered in such a way that the distance between the predicted value and the actual value should be very small, correct? And then we went back. And then we collected those random weights, and the weights are now in such a way that they are predicting the values, correct? Then we talked about images. Then we talked about some concepts of activation functions. We talked about learning rates. We talked about optimizers. We talked about multiple things. But the main thing that I think most of you might still be asking is that, what will I do in my day-to-day life? Do you expect me to understand all this mathematics? Do you expect me that I am doing all these matrix multiplication with my hands on paper? So the answer is no, right? These big tech firms have already done for you, right? And I think we had again a discussion around what are the machine deep learning frameworks. So let's again today talk about a little bit deep learning frameworks. It means that whatever we did last time, do you remember whatever we were writing our own codes? What are the inputs? What are the how to take random weights, adding them, multiplying them, doing a differentiation? All that is handled by deep learning frameworks, right? All of that is handled by deep learning frameworks. So we are going to learn about those frameworks, that how with just one command like model.fit can this actually all happen, right? That's what today's job is. So these frameworks, there were multiple frameworks, right? So let's talk about erstwhile frameworks, frameworks which existed, which were like the OG frameworks in your language, but they are no more with us, right? The first one is Tefla, right? The second one is Cafe or Cafe 2, right? Theano. All these frameworks did existed over there. I should not write Tefla because Tefla was not as famous. So I will write down these two. Then there was a torch, right? But as of today, there are, let's say, two frameworks which rule the whole world. The first one is TensorFlow, and the second one is PyTorch. Correct. TensorFlow is controlled by Google or Alphabet, right? And PyTorch is controlled by Meta or Facebook. Correct. There are other frameworks like CNTK, which is controlled by Microsoft, but that is very less. Now, TensorFlow has a very good, let's say, depth in the industry, whereas Meta's PyTorch has a very good, let's say, hold in the research area. Generally, you will see this term being used simultaneously, right? Some people will be saying framework, some people will be saying library. It's a interchangeable word, but the context changes when you're talking about, different things. So let's say if you're talking about in the software industry, it might be a little different. If you're talking about deep learning, it might be a little different. We are talking about deep learning industry, so we'll talk about it, right? So see, libraries are, let's say, something which are which are made with an objective to achieve a particular thing, right? Like your scikit-learn libraries or your pandas, numpy are called libraries, right? Whereas framework is something which you already know, like how today all of you know that how to run a neural network, how to run a single neural network. But do you really want to, let's say, automate that process, right? You want to abstract of all of that code and you want to give it into functions. That is much more like a framework kind of a structure. Again, the term is used simultaneously over there. TensorFlow has an upper hand for us today. I am saying, because we are applied data scientists or applied deep learning engineers, right? We will not be involved, or let's say we will be rarely involved in researches, correct? Our job is to, let's say, apply deep learning to industry. So we are more inclined towards TensorFlow. PyTorch is gaining momentum very quickly, but still leads the research area. So you will see almost, I don't remember the X percentage that, Meta rules as of today, PyTorch rules as of today, and the maximum citations are coming from PyTorch itself. I have heard PyTorch is research and TensorFlow is for deployment. Am I right? That is what exactly I've written, my friend, right? TensorFlow is much more used in industry and PyTorch is much more used in research. But again, this is today's scenario. There are this might change going forward also, but I think TensorFlow has a very upper hand. It was released earlier also. It has more capabilities as of today. What is the difference between the two? Not major differences, right? Again, this is just like saying that there are two ways of, let's say, it means just simply say that you want to go to drink a coffee, right? Now you can go to Starbucks or you can go to Barista, whatever you like. Your choice will be dependent on what you want, but both of them are serving coffees, correct? Both of them are serving coffees, but each and every individual will have their own choices, right? Based on their preferences. That is what exactly we will also do. We will choose TensorFlow because we are much more industry oriented. Can Google or Meta view industry secured AI code? So see, again, there is nothing related to security over here. I'll tell you why. Because see, this is a open source framework, right? You can actually go there and look at the PyTorch GitHub, or let's say you can go and look at the Keras GitHub, or let's say you can go and look at the TensorFlow's code over there. See, now this is the complete code that is written over here, right? I can show you for TensorFlow also. TensorFlow GitHub. In my early days of life, I have also contributed to TensorFlow. When it was very new, I also wrote some code part of it. So there are certain functionalities which will, when you will go forward, I'll tell you that this is written by me or some, like, I had contributed to a smaller part. But that is how TensorFlow is. It is purely open source, right? Who will decide what to use, which is product-based scenario? Nothing to choose over here as of today. That's what I'm saying, right? Nothing to choose over here. Again, see, this is a, see, again, listen. This is again a framework, right? The core concept remains the same, right? Back propagation will still be done the same, right? Dots will do it in the same way, and TensorFlow will also do it in the same way. The results will be same, correct? It's not that it's like a like you might use TensorFlow and you will get, let's say, 97, and if you're using PyTorch, it will give you only 60%. No, it's not that like that, right? What is a wrapper? Wrapper means, I'll tell you the story again back, right? That in 2015 around, right? TensorFlow came in and the people were a little confused because Theano was highly used, and now people have to also learn TensorFlow. So there were two different kinds of frameworks that people had to learn about, right? Let's say if they are doing, let's say if they have to code on both the things, right? Because TensorFlow came out from Google and it was a big thing, right? That Google is open sourcing their own framework. So everybody wanted to use TensorFlow also. Now, so for that, what they had to do, they had to learn TensorFlow also, and they had to learn Theano also, which they were already using. So Kiraz, this person says that, hey, listen, you don't have to learn both the things. Just learn my syntax. I am not a framework. Listen, I am not a framework. I am just a front end for it. If you tell me, I will run it in TensorFlow. If you tell me, I will run it in Theano for you. I will do it for you. You just tell me in the language of Keras what you want to do. So let's say you want to make, let's say, a one hidden layer 3 neuron network. So what is going to happen? You just tell it, and Keras will either translate it into TensorFlow or it will translate it either into Theano, and it will run it for you. So what happened? It was acting as a big wrapper. The question comes up, why was the need of Keras, right? Why was the need of Keras over there? The problem is, my friend, that when TensorFlow was launched, right, it was still very heavily skewed for researchers. That, you can still do a very, low level kind of tweaking into it, right? People didn't want it. People wanted to avoid all these things. See, if people wanted to do these matrix multiplication, they would have done it at the very first place. They didn't wanted to do all this heavy lifting, and for those reasons they wanted a framework, correct? I'm sorry, they wanted a framework, but TensorFlow was not able to help them over there, right? TensorFlow was still giving them some low level things. So Kiraz said that, hey, listen to me now. You don't need to do all these things. I will take care for all these things, and I will make it very simple for you. I will make a very high level API for you. I will make it a very high level API for you. So Kiraz came into picture, and Kiraz became a big success. Kiraz was so simple to use, so simple to adapt, and the learning curve for Kiraz was such a linear curve that people started using Kiraz a lot. But unfortunately, in 2017, Theanos ended their support, and they said that we are not so much great anymore. We do not have the capacity to run this anymore. And TensorFlow is doing a good job. Let them run. So TensorFlow was discontinued, or Theano was discontinued in 2017, and Keras was now just supporting TensorFlow. People thought that now Keras is gone, because now Keras is not helping us to choose between Theano and TensorFlow. Now it is just TensorFlow. But people were so addicted to Keras that they never left it. And in 2017, they hired the folk Francois Cholet, this person who made Keras, right? They hired as inside Google as a developer over there. And now Keras, as of today, is the official API for TensorFlow. What does it mean? It means that TensorFlow says that if you are an applied deep learning scientist, then you should use our library Keras. If you are a researcher, then you should use the TensorFlow main core library. Or if you are doing something very customized, then you should use the TensorFlow APIs. Otherwise, you should use Keras only. What is the API? API means just understand that you are using their functions, right? You are using their functions and not directly TensorFlow's functions. So see, whenever you are calling something, understand this over here. Let's say if you're writing something, let's say like this, Keras dot function. Now you are thinking that you are calling Keras function one, but actually eventually it is calling TensorFlow only. But the way in which the Keras, let's say the whole Keras package is written, right? It is very much intuitive and very much clear in the sense, right? As I told you that, let's say if you want to do something very customized, right? If you want to do something very much customized, it is out of the world, or let's say you are a researcher, definitely you should go and use the TensorFlow APIs. But let's say if you are an applied scientist like me, somebody who applies the already done research in industry, that is, for that person is called as applied deep learning engineer. If you are somebody like me, we will focus on Keras.
Let's have a quick quiz question, guys. And the question is, which of the following is an example of supervised learning? And your options are training a chatbot to generate responses, or teaching a self-driving car to navigate using sensors, or clustering similar documents based on their content, or extracting patterns from unlabeled data. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
How do you first of all install TensorFlow? That's the first question, right? So the answer is very simple. Before installing, you will check if it is installed already or not. Check if TensorFlow is installed or not. So how do you check this thing? Pip show TensorFlow, but not like this, like this. And if I run this thing, it is going to connect to my Google Cloud instance, give me a Docker machine, give me some resources, and you will see that I have TensorFlow. It is taking much more time, but TensorFlow, some version it is installed. I think 2.4. Okay, so 2.11 is installed. 2.11.0 version is installed for me. Those of you who are on your Jupyter machines, this number might be a little different for you based on the Conda versions, right, that you're using, but it is fine until and unless it is 2 point some number, it is fine for us, right? There will be some minor shifts here and there, which I will take care for you. Don't worry, right? Okay, so this is about TensorFlow. And as I told you, now Keras sits inside TensorFlow, so you don't need to explicitly install TensorFlow or Keras, correct? But those of you where where TensorFlow is not installed, you can say install TensorFlow like this. Pip install TensorFlow, correct? It is not installed on my machine, my friend. You can write it down like this: pip install TensorFlow, correct? And it will work for you. See, import TensorFlow as TF. If I do this thing over here, you will see that this TensorFlow is imported for us, and I can show you the version over here, which is 2.11.0, correct? Now, as I was telling you, Keras resides, what, my friend? Keras resides in TensorFlow. So see, you can check it like this. You can see the Keras version is also 2.11.0. Until I think 3 or 4 months back, this version would, you can see some of your versions might not match, right? The TensorFlow version and the Keras version might be a little different, which is then fine. Keras is a wrapper, right? Then how can it be inside TF? That is what I told you, right? That Keras used to be the wrapper, but now what has happened? Now, because there is no more the Theano, Google hired this Keras folk, and they said that now Keras is our official API for TensorFlow, right? Okay, go back, and we saw that there is Keras something. Now, okay, Keras, I if I just asked you, right, we could have directly imported Keras also. See, my friend, as I told you that Keras used to be a wrapper, right? So we will not use Keras independently. We will use the Keras which is inside TensorFlow. Please understand this point. We could have imported Keras. The answer is yes, but will we? The answer is no. We will not use. We will use the Keras which is inside TensorFlow. Okay. So so now what you should think about Keras, right? As of today, what you should think about Keras? Keras is nothing but, let's say, all those big functions, all those big functionalities that we used to do, that we would have done for making our neural networks, they are now condensed into these functions, and those functions are nothing but Keras, right? Okay, let's now talk about MNIST. MNIST is Modified National Institute of Standards and Technology Database. What does this mean? This is the department of US which is responsible for making sure that what are the standards, what are the technologies that we will use across industries. Correct? So they are the one who says that if what is the relationship between a kilometer and a mile, right? A pound and a kg, right? What measurements should we use? All those kinds of basic things, basic measurement things this particular firm designs and defines. Correct? So what happened is, now this is a very good story that all of you should see. The story is that in I think in 1990s, what is happening is that the US Postal Department is now facing issues. So what they are doing right now is that they have to manually read the pin code on the letter, and then they have to classify it. That okay, if this is some 3459 pin code, put it over there. If this is some 65692, put it over there and there and there. So manually, the department, US Postal Department, is manually reading those pin codes, and they are manually categorizing these pin codes such that they can be sent to the respective cities or respective regions. Now this problem became so big that they were now compromising on the speed of the delivery, right? They are now compromising on the speed of the delivery. Their postcards are getting delayed. So what they do is they ask all these computer folks. They say, hey guys, listen, you're very smart folks, you're doing something, something, something. Can you help us? Right? Can you help us in understanding this thing, that is there something that your computer science can do over here, right? Something that you can identify this pin code automatically and can help us. Yan Li Kun, our friend, do you remember? One of the three musketeers, or let's say the three godfathers of Yan Li Kun. He says that, okay, listen, I can do something. My university is doing something around the same thing, right? We can help you with this thing. We can help you with this thing. So what happened over there is, he said that, okay, what you should do is, okay, this is closed now, this particular website, but okay. So what they did is they said that yes, we are working on something called as computer vision, and we can actually help you. So now what the problem is? The problem statement is to identify what digits are written on the postcard. Correct? This is a simple problem that they have to make a image classification problem where, let's say, a image will be entered and the corresponding digit on that image should come out. Do you all understand? Right? That's the simple equation. So what they did is they decided to work on this thing. The biggest challenge that came in front of them was data, that they didn't have data. So what they did, Yan Li Kun actually sat down and he said that, okay, let's design this data set and let's ask people to write down 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 on a paper. And they literally went down to students in the universities, the postdoc in the universities, to folks in the Canadian Quebec region. They went out there over there and they asked people to fill this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is what they did. They figured out this data set, they made this data set, and today this is called as MNIST database. Well, technically, the name MNIST is by the National Institute of Standards and Technologies. But whenever you talk to somebody in a deep learning field and you say MNIST, MNIST actually means a data set which contains 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 written over there. And this is the first problem that everybody solves whenever they join deep learning. This is the toy data set for deep learning. And there were 60,000 people who wrote it down. So as of today, let me tell you what is MNIST. MNIST is handwritten, and this is handwritten digits from 0 till 9. These are images, single channel images. Remember, single channel images with size 28 cross 28. It means 28 height and 28 width for each digit that they have written. As of today, the data set that is available to us, the subset of it contains 60,000 digits and around 10,000 test digits. Does this make sense? Do all of you understand now what is MNIST? MNIST is a 60,000 combinations of these different digits written over here: 5, 1, 1, 0, 9, 3, 4, 2, 1, like this. 60,000 they give you for training and 10,000 they give you for testing. What is the objective? Is this clear to all of us? That there will be an image which will go into your deep learning model, and the model has to predict the digit. Correct? Everybody understands the problem very clearly? So the first thing that we'll do is, my friend, we will download the data. Download the data. It's a multi-class? Yes, it is a multi-class. Digit recognition model? Yes, digit recognition model. How do we download this thing, my friend? So Keras was such a genuine library. It's such a beautifully arranged library that it gives you almost everything. Keras says that, hey, listen, I already will give you all these things, right? Do not worry. You don't need to go anywhere. I will give you all these libraries. Now, it will return you like this format. Actually, let me show you the function so that all of you can understand what it is going to do. It is going to download the MNIST data for you. It is going to download the MNIST data for you. This is the same URL that we were trying to link, but somehow this is now protected. I don't know why. So you can, as all of you can read over here, that loads the MNIST data set. This is a data set of 60,000 28 cross 28 grayscale images. Do you all read this thing? It is a 60,000 images of each size 28 cross 28, and they are grayscale in nature. Grayscale means a single channel in nature. So when you will load this thing, the shape of the image is going to be only 28 comma 28. That's it, right? There will be no comma 3. It is not a 3D image. So as you can see over here, it says 28 cross 28 grayscale images of 10 digits. Very good, because there are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. More info can be found over here. What does it return now? See, when you run this particular thing, it returns you a tuple of NumPy array, which says X train, Y train, X test, Y test. So let's write it down. We will say that, hey, you are going to return us a tuple first of all for train and then for test. Correct? Now, can you tell me, for this particular problem, what is X and what is Y? Let's say if X is input. Let's say if X is the input. What is the input for this machine learning model? What is the input of this machine learning model? Images. And what is Y? The output of this particular model? Digits. Very good. Digits, or can I say labels also? Labels or digits, whatever, the same thing. Yes, correct. And that is what exactly it is saying over here. It says that X train is nothing. X train is nothing but, let's say, NumPy array of grayscale image data with the shape 60,000, 28, 28. It is 60,000, 28, 28. How this shape became, I will tell you, don't worry, right? Containing the training data, pixel value ranging from 0 till 255. Do I need to explain this line? Pixel value ranges from 0 till 255. No, right? Because this is the constant thing for any image. The pixel value, if it is a normal loaded image, it is going to be 0 till 255. Very good. Now, what is Y train? It means that what is the Y or the output for the training data? NumPy array for digit labels. NumPy array for digit labels. It means for these corresponding images, their correct labels are also given to us. Do you all understand this thing, right? That for machine learning, we need the correct answers also. We need the Y actual also. Remember, when you have to calculate the error, you require Y actual minus Y predicted, correct? And this concept is same as your machine learning also. This is not very different. The same concept in machine learning also, right? That you need your input and output both to train the data, correct? Okay. Now, what is X test? X test is nothing but the same images, but this time they are only 10,000 images, right? They have given you 10,000 images for training also. And similarly, you have their labels also, correct? Okay, let's run this thing. The moment we will run this thing, it says that it took some 0 seconds to download this thing. And if I check this now, first of all of us are clear, right? What is training step? Training step is the step which this data will be used to train the model, right? And testing data is what? This data will be used by the model to test its accuracy. Now, training data will have two things. One is the input. Now, all of you said that Shivam, input is nothing but images, right? Now, see over here, all of you see over here, what is the shape of X train? It says 60,000, 28, 28. What does this mean? This means that there are 60,000 different images stacked one over each other, right? Stacked one over each other like this. This is first image. Then on top of it, there is second image, then third image, and then fourth image, and then fifth image, and then sixth image, right? You have stacked these multiple images over here, right? And each image is of 28 height and 28 width, right? And there are how many images? 60,000 images. This is why the array shape is 60k, 28, 28. Do you understand this thing? Do you all understand this thing? That why the shape of X train is 60,000, 28, 28. Because this actually means number of images, height, width. Correct? But grayscale images will only have two images, right? Yes. So did I told you that this is an image? This is just one image. No, this is multiple images. Multiple images. And I will teach you also how can we extract these images. Even if it is a single channel image, 3 channel image, or 4. Okay, let me ask all of you a question. All of you, I have a question for you. If this is a single channel image or a 3 channel image or a 4 channel image, will it matter, or let's say, will the pixel value change now? Is it not going to stick to 0 till 255? No, right? They're going to be constant. The images are always going to have the pixel values in the range of 0 till 255 only. Very good. This is your X train. Similarly, for your X test also, if I show you, you can see over here that this is 10,000 comma 28 comma 28. What does this mean? This means 10,000 images with 28 height and 28 width. Let's say there are 50,000 images and each image is of the height 100 comma 100 and it is a it's a RGB image. So what would be the final shape of the array? The final shape of the array will be that how many images are there, comma, what is the height, what is the width, and then because they are RGB images, they will have a 3 over here. Does this make sense? Anybody who has different opinions over here? That last time when I told you that a image is like this, I said this is a image. This is a image, one image, right? This is one image. And today, now we are no more dealing with one single image. We are dealing with multiple images. So they had to pack it in some way, right? They had to pack it in some way. So they have packed this into a numpy array, and the numpy array says that the number of images, comma, height, comma, width. Do you understand this point? Can you explain why does it take only 10K images? Why? What is the question why? Because they have given the data set, right, my friend? There is no why in this thing. They have given the data set. They made the data set in such a way that 60,000 you can take for train and 10,000 you can take it for testing. Simple thing. Okay. Now let me actually show you. Wait now. Let me actually show you the images, right? Then I think much more things will help you. So see now, let's say that there are 60,000 images. 60,000 images are present in X underscore train, correct? We should pick, actually not, let's not say we should pick, let's say, let's pick the first image from array. So what I will say sample image is equal to X train 0, like this, correct? And sample image dot shape. One of my friends says, what is the height and width measured in what unit? Pixels. It is no more centimeters or no more centimeters or meters for us now anymore, right? These are pixel values, or in very simple terms, these are the number of rows and columns in your data, right? Now, please, all of you, stop thinking your images in such a way that you're visually seeing them. Whenever somebody says you a image, you should always think of it as an matrix. Now, what is the unit of a matrix or an array? Very good, yes, array. What is the unit of an array? Array is nothing but a combination of multiple rows and columns, correct? So when somebody is saying to you that my image is 28 comma 28, it means that there are 28 rows and 28 columns. And all of you can see it over here. See, if I let's say print this over here, this is how your array looks like. And please understand, this should be your understanding of images. The moment I say a image, please forget about those multicolored images in your mind. Every time I say an image, an array should pop up in your mind. Those of you who are getting error, please stay with me for some time. I will explain you and we'll debug it together, correct? But I think let's not break the rhythm, correct? I'll explain. Okay, so all of you can see over here now, this is that one image that I have extracted from that 60,000 array, and I just, let's say in front of you, I just displayed it, right? And if we ask our IAMShow, plt.iamshow sample image, this is a 5 over there. This is number 0. No, why? I mean, I don't know if it is a 0 or not, but when I printed it, it looks like a 5 to me. I tried to guess. Okay. It's a 5. I think so. And we can know the correct answer also. How can we know correct answer? Because we have the correct labels also. So what I can do is I can ask Y-train. Hey, listen, my friend Y-train, can you tell me what is at the 0th position? What is the image at the 0th position? Because you Here also you took the first image, right? The 0th image, correct? Let's make it the 100th image. Let's make it the 100th image. So you all can see over here. Or if we were talking about the 0th image over here, the problem has given, see the data set, the Yanli Kun person, right? He gave you a data set. Let me write it down. Data set is divided in two parts, right? And they call it trained with 60,000 samples, and other one is test with 10k samples, right? And now listen. If you think this 10k is less or that 60k is less, you can any day do your own sampling also. But Yanli Kun thinks that 60,000 images for training should be the best, and 10,000 for testing. Now, if you don't like this thing, you can definitely change this one, and you can move images on the top, make it some 80,000, 65,000 and 5,000, or you can make it 50,000 or 20,000, whatever your point. Second, my friend says that means we have to feed 60,000 images to the network. Yes, yes, the answer is yes. Which means 60,000 inputs? No, the inputs will be 28, 28, right? But there will be multiple 28, 28. I'll explain it to you. Don't worry, this question I'll come back and I'll explain to you. These are grayscale images. These are single channel images. These are not three-dimensional, three colored images. That is why it is just 28, 20. There is no 3 over there. Should we import Keras also when we use Keras? As I told you earlier also, we will be using Keras resides in TensorFlow. So we don't need to import it. But you said they had a data set of 60,000 images in total. Okay. Then how can X-train be 60K and X-test be 10K? No, I said that they have a corpus of 60,000 training digits and 10,000 test digits for you. I never said that they had a totality. Again, also, I'm not saying there are 6,000 images. There is actually a bigger data set, right? So the data set that is given to the toy data set has 60,000 images, but the original one had more images into it. But they had some issues with the quality of the images, so they have given us the best of the best. My friend is asking this question. My friend, we talked about this very much in detail last class. I would highly request go and revise that particular class, right? Why did we get y train equal to 0 as 5? Because this is an image of a 5. They have to give us the, what did I ask you? I asked you, if you have to train a machine learning model, my friends, what are the two things that you require? If you have to train a machine learning, forget about deep learning, machine learning, input and output, correct? Now, I asked you a very simple question earlier also. I am again asking, what do you think for this particular problem is the input? Images. And what is the output? Digits. So to train this particular model, you need to have these original answers also, correct? Same concept as your machine learning. When I say X train over 0 here, I mean, give me the first image. I never said it, give me the 0th image. Or sorry, I never said give me the 0 image. Please understand this thing over here. Some of you, okay, listen. I can understand the theme over here. Now, please listen. First of all, let's stick to the question part, right? Some of you are going way north, way south. Listen, stick to the deep learning part of ourselves. Second thing, I think some of you are getting confused that, listen now, whenever you trained a machine learning model, my friend, let's say you remember Boston dataset, house price image dataset, the house price. All of you have used the dataset, the house price dataset, right? What that dataset was? That dataset contained some independent variables and one dependent variable, correct? Or can I say this was y, this was x, or I can also say this was input and this was output. And what was that in your case? These were the features for your input parameters, like, how many bedrooms are there, how many parkings are there, right? Number of bedrooms, number of parkings, right? and at the end they gave you output, which was what? Which was the price of the house. Correct? Do all of you agree with the statement that the data set gave you both the things? Say yes or no. Now, if there in machine learning you took both the x and the y, you took both the input and the output, why would the same thing not happen in deep learning also? In deep learning, my friend, if we are training a deep learning neural network, I require both my x and my y. You might also call it as input or output. And for this particular example, input is going to be images and output is going to be digits. Is this thing clear to all of you? Very good. Now, one more thing, right? One more thing that I wanted to tell you is that, okay, if these things are going, right? Now, let's make a function over here. You need to understand that they have given us some random 60,000 images, right? They have given us random 60,000 images. 60,000 images with their correct label. Please understand this thing that they have to give the correct label also, because this correct label is nothing but your y actual. Do you all remember this term y actual? Where was this term used? This term was used in error calculation. How will you calculate the error if you do not have the correct label? Do you agree? Digits as in the font, as in the numerical, yes. I'll show it to you also. Let's make a function. Why it is not increased from 10k to 60k to higher? Okay. Why it is fixed to 60k? Okay. Why is my salary fixed, or why is this session fixed to 2 hours only? Why this day has only 24 hours? Right? See, there for every data set, my friend, right, there is a limitation, right? They cannot, they had to actually ask folks to fill in this manually, and then they had to do their quality control on top of it, right? They had to scan these images, so they had an upper limit on how much data they can provide to you. So that's why they have given you 60,000 images. Is this a true statement, my friend, that the y is always given to you in validation? Is the y not present in training also? Is the output not given to you in training also? No, never. For training of data, you require their actual labels also. For training the Boston house pricing data, my friend, you had the prices also. Remember this thing. Now, what was Titanic dataset? Titanic dataset told you that what is the ticket number, what is the passenger number, what is the passenger's class, what is the passenger's embarkment, right? Where did they did on this thing? And at the last, at the very last, they told you one thing, that whether they survived, yes or no. Correct? Do you all remember this data set? Do you all remember this? Very good. Now, what was the objective of this particular data set? The objective of this particular problem was that if we give you these input parameters, if we give you a input parameters of that particular passenger, can you detect or can you predict that whether that person will survive or not? Do you all remember this data set? Now, when you trained that data set, my friend, was this survival yes or no available with you or not? Was this column available to you or not? In the training data, it was available. But do you all remember, right? This was available to you. And this is exactly, if you remember your machine learning format also, you used to call this particular thing as your x train. Remember, you used to call this as x, and you used to call this particular column as y. And you would say model dot fit, whatever model you are using, you will say model dot fit x comma y. Remember? Do you all remember that while you were training the data, you had to give it both the input and the output? Correct? Very good. That is exactly the same that we will do over here also, my friend. that we will have the images, and for each image we will have its corresponding label or the numerical digit also. I will show it to you in more into details, right? Let me prepare as a function for you, that why do we have digits and labels together. Very good. Okay, so let's do one thing. Let's plot images, plot digits. So what I'm going to do is, my friend, I am going to prepare a function. This function will generate, or let's say generate, not generate, this function will pick up images from train data set and plot the image, and display, or let's say print the correct label. Correct, right? So I'm just simply making a function which will take in, let's say, which will randomly pick up a image and draw it, and will also show you the label corresponding to it, right? So what I'm going to do is, I'm going to say random image is equal to x underscore train, and then that random. Correct. So what is going to happen? There are 60,000 images. We will randomly pick up any image, right? And we will say plt.im show random image, and cmap equal to gray, and we will say print y underscore train and random number. Now one thing is that this random number cannot be greater than 60,000, correct? So random number is greater than equal to greater than 60,000, then we will say return value average, or let's say let's simply say uh, train data set has only 60k images, right? Okay, so what I've done is, I have made this over here, and now I can just randomly put some number here. Again, please do not think that this random number, actually let me not put it like this. This random number is what? What is this random number? This random number is the index. It means I am asking, give me the 100th image out of those 60,000 images. That there are 60,000 images kept like this. There are 60,000 images kept like this. So what are we saying? When I say 100, I'm actually asking the 99th image to pick it up from that, right? There are 60,000 images in total, and I'm asking this 99th to come up. Okay, let me ask you a question, my friend. Let's say you have two phones in front of you, and if I ask you, give me three phones, can you give me three phones? You have only two phones with you. If I ask you, give me three phones, can you give me? The answer is no, you cannot give me, right? That is exactly what is happening. If this data set has, let's say, 60,000 images only, and if you're giving me a number which is, let's say, a position which is greater than 60,000, how it will work? It will not work, right? So see over here now, it generates a random number and it shows over here. What I can do is, instead of writing this 100, I can actually, let me 9 over here. Okay, let me do one thing. Let me just say digits, and let me say np.random.rand int 0, 60,000, 1 and 0. So see now what is going to happen. Okay, now it is going to randomly choose the number. I don't have to write them. See now here, can you see this image and the corresponding label on the top? All of you can see the label also, right? Let me just put a F string over here. Can you all see now? This is what these images are, my friend. This needed to be segregated first. So my friend, right now we are not solving for pin code, rather we are solving at a digit level. So we are saying that, let's take an example that let's say the pin code is like this 3, 5, 6, 2, 4. What we are saying is that rather than tackling this whole image, we will, let's say they will break this image into, let's say, multiple parts like this, and they will individually detect these images that, okay, this is 3, this is 5, this is 6, this is 2, and this is 4. Rather than completely, let's say they're saying like this, that 3, 5, 6, 2, 4, they are going to say it like this. Can you print multiple, or let's say plot multiple images? So the corresponding y test is y actual, and here is where we calculate error y actual and y predicted. Please confirm the same goes with the images. So the only last sentence that you have written. So here corresponding y test is y actual. The answer is no. The error is calculated for training data. The error is calculated. The back propagation, before the back propagation, the error calculation is done on training data. We do not wait for testing data. Testing data is for final answers. Does everybody agree to the statement? That the error calculation that we do, before the back propagation and after the feed forward, that is done on training data. Testing data is not even shown to the model. It is not shown to the model. Once the model is trained and it is completely ready, and once we say that, okay, now I need to test how correctly my model is predicting to find the overfitting and underfitting things, right? Then we use test data, correct? See, it does not matter if your image is in AutoCAD, PDF, PNG, JPEG, JPEG, TIFF, PNG, does not matter, because deep learning want images. Deep learning does not understand your AutoCAD. So if you can extract images from AutoCAD, the answer is yes. TensorFlow will not extract AutoCAD images for you, right? You have to extract these images and give it to the model. If that is over there, you can do it, then yes, it will be. See over here, my friends, TensorFlow library says that yes, we will work with arrays only, but we want to make these arrays a little bit smarter and give them a little bit flexibility, right? And for that, what do? Is they say that we will convert all our NumPy arrays into tensors only. So just understand, tensors are nothing. Tensors are nothing but, let's say, you're Spider-Man but wearing the suit, whereas a array is the same Spider-Man but not wearing the suit, right? That's the thing. So tensors are nothing but, let's say, an internal data type that TensorFlow uses, correct? And PyTorch also uses. Please draw this kind of a structure where I have all the 0 images over here. 10 0 images. 10 0 images over here. Then I want 10 1 images, right? And then I want 10 2 images. I want you to create this kind of a structure for me. All of you are very much aware of Matplotlib. All of you are very much aware of images. You know everything, right? Please draw this kind of a thing for me. I will take a break for 2 minutes now because I'll drink some water for myself. And in the meanwhile, I'm here only. You do this kind of Matplotlib grid for me. Create this grid for me. You all understood the question, right? The question is that you have to plot 10 0 images, 10 1 images, and 10 2 images. I think the very first problem that all of us need to find is that where are all the 0 images? How will we figure this out? Let's say I am asking you that give me 0 images. How will you find the images which are 0? All the X train image in the X train, right? So see, where are all the X images? Go to Y train and ask for digit 0. Is it correct? Can I say np dot where x underscore train is equal to 0? What is this giving me? What is this number? 1, 21, 34. What is this number? Can somebody tell me? Indexes. Indexes for what? Indexes where 0 images are present. When I say 0, I mean the 0 digit. Correct? Very good. Now I want only 10 images. So can I say it like this? Can I say 0 images? Similarly, can I say 1? And similarly, can I say 2? Do you agree? Right? Okay, now you will explain me what is this. Give me 1 second. Okay, so what is this? This is a tuple. Okay. So what I do, I need to do? I need to do it like this. Okay. Give me 1 second, just 1 second. Very good. BLT dot subplot 1 comma 10 comma I. And what is the length over here? 1 second. What is the length over here? Okay, done. What is this now? Okay, length of 0 inches is 10 only, right? Mistake over here is done. Small mistake. Okay, correct. I'll explain it to you what I'm doing. Just give me 1 second. Oh, what does this? Oh, correct. Now what happened? I am correct. Okay, see, this is the problem that. Oh, what am I doing? Here it is. Sorry, my mistake. I plus 1. Okay, here it is, and I will call it that. My mistake. Here it is. Now what is the next thing? What is not happening over here is the invalid shape for image data. Oh, see, these are just indexes, right? Oh, see. Here. Okay, I don't know if you can see it or not, but I will just say plt dot. So these are different types of zeros that you can see over here. And similarly, not just this, I can actually make it like this. And you can see 1 over here now, and similarly I can do 2 also. Correct? C map equal to gray. Yes, I can do C map equal to gray. But actually, let's focus on just one part of this thing because I want to show you one more important aspect over here. Let's see, not every digit is same, right? See over here now, 2 is written like this, 2 is written like this, and 2 is written like this also, right? Everybody has their own way of writing this thing. They are not constant. Correct? Now, can somebody tell me how can I figure out that how many that is my data balanced or not? Do you remember that in machine learning you had a problem of class imbalance? It means you had to make sure that how many categories of data that you have, right? How many possible outcomes of your machine learning can have, and are those categories equally balanced or not? So my question for you is this data set class wise balanced? Count the image of each label from Y train. Very good. And how can I say that thing? I can either convert it into a pandas data frame, right? And then I can just simply say value count, correct? Y underscore train, right? And can just simply say value underscore count. You can say not all the digits are equally present over here. One has the highest samples, 6,742 samples are there for one. 5 has the least sample, right? 5 has the least sample, only 5, 4, 2, 1 samples are there. So this data is almost equally balanced, we can say, right? I mean, it's not a huge difference, but it is not, I mean, it's not a small difference also, but it's not even a huge difference, right? Very important thing, the same aspect you need to follow in your machine learning aspects also.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
So this is where we see, right? We can generate these random images over here. And right, and all of you understand now, right? That if I have written 1, 2, 3, what this 1, 2, 3 is, what this 7 is, and what this 7 is. Correct? This is the image. This is the correct label. This is the correct label or the correct answer, or you can also show that this is also called as the Y actual. Remember, in our loss function, we had a variable called as Y actual. This is actually nothing but the Y actual part. And this 1, 2, 3 is what? This 1, 2, 3 is the index number. Why do we require an index number, my friends? Because all these images are stacked in a NumPy array like this, one after the another, right? One after another, these images are stacked into something called as X train, right? And the shape of this X train is 60,000, 28, 28, which means there are 60,000 images with 28 height and 28 width, correct? Right? Now, what is this 123? This 123 is nothing but out of the 60K, I am saying give me the image which is stacked at 1, 2, 3 location, right? I can say this has also 512 here also, correct? How will the organization create a data set extract? They will never create a array for you. They will give you a folder. Companies, they will give you a folder like this. They will say this has all the images, right? They will not do the pain of making these for you. And labels, yes, they will give you labels. The answer for labels is yes, they will give you yes. But the first part of your question, that will they make a extrain for me, the answer is no. And in the later part of this particular exercise, right, I will also tell you that, see, it's not that every time you will get a extrain, right? We will also work directly with Kaggle competitions where you have to download the data and convert the data into extrain. So now what is the first thing that we should do? Please show the above code. Okay, this one. Okay. Okay. So now what do? We want to make a model, correct? We want to make a model. Now, what is the first thing that you will do? How do you define a machine learning life cycle? What is there that you work on while you're making a machine learning model? How do you start your machine learning journey? Okay, is the very first thing EDA? Nah, right? I don't think the first thing is EDA. Read the image, data cleaning, null value check. Okay. Deep learning project life cycle. The first thing is to understand the problem. Please do not zoom out of the picture. The first thing is to understand the problem, right? But have you understood the problem on? The second thing is formulate the solution, or let's say the problem actually, not the solution. Formulate the problem. And first of all, try to understand the problem. Try to think about rough sketches, rough things that you will do in your mind, right? Second thing is, see, I am preparing you guys for how to ask to clients, right? How to deal with clients. Do not please directly jump into the solutions that, okay, I want to do this thing, I will do, and I will just quickly do EDA, all those things, correct? First of all, your point is to understand the problem, right? Understand the problem. What might be the next thing? Let's say you are trying to understand the problem, you are trying to formulate this thing. There will be multiple problems, right? There will be multiple questions that you might have. So the third thing is ask relevant questions. Again, this is not a deep learning thing, right? Especially about data and process. I think one of my friend was currently in the chat. I think he was saying that Shivam, if let's say we have a client who wants to detect whether a car is a defected car or not, I think something like that, right? So the first thing is that how do you define a defect, right? The biggest thing that I would have asked, like, see, you guys would have gone into the question of, what are images, what is the label, how many images, how many labels, right? I would have asked the question that what is a defect, right? Define metrics. Always remember data is raw and dirty. Always remember data is raw and dirty. So your questions might not be just revolving around the processes. They might also be revolving around the data, right? Now, what will you do next? Let's say you have got all the metrics. I will also write down define success. At what point will you say that I missed one point, right? At what point will you say that, yes, I will not go beyond and this problem is solved? Define success, KPIs or metrics. Correct? Next, let's say we come to the data part. You might say that the data is raw and dirty. What will you do now? Let's say you have filtered out the data, not filtered out, but let's say the data is raw and dirty. You asked about the question, you did the data cleaning. What else? Data cleaning, right? Then what next? Data QC, okay. QC cleaning, okay. What next? Filtering data, okay. Filtering data for validation and actually training, validation and testing. See, if you are thinking that your client is going to give you training, testing, and validation separately, no, that is not going to happen, right? It is your job to make sure that you divide the data into relevant parts and relevant ratios. See here, because this is a toy problem, this is the first problem, right? And we don't want to focus more on the data side. But not generally, no client is going to give you X train or Y train or X test or Y test, right? They will not divide the data for you into 60 or 10, 60,000 and 10,000, correct? It is your responsibility to make sure that if the data has been delivered by the client, that data is divided or let's say filtered into three parts, correct? Training, testing, and validation. All of you are very much aware about all these three things, right? One of my friends says converting 2D data to 1D. Why would you do that? 2D to 1D? Data flatten, why? for neural networks. Okay. Randomized or stratified? Yes, randomized or stratified based on the classic problem that you're solving, right? Based on that, you will do. What next will you do? Pre-processing, feature engineering, very good. We're working with deep learning, so feature engineering might not be a big aspect over here, right? Image generators. What are image generators? Resize would come under the pre-processing part, right? Then what next? Let's say you have done cleaning, pre-processing, feature engineering. Then what next? What is the step? Modeling. Modeling is the most important part. Correct? Next part. Hyperparameter based. Uh, Actually, not hyperparameter based. Validation based hyperparameter tuning. Correct? I can say this thing right that why are we doing hyperparameter tuning? Because our validation results are not correct. See, till this step we are not talking about testing data. Do you all agree? Right now we are just using validation data. If the data is not performing on validation data, we are hyper tuning it. Correct? Do you all agree that till this particular time test data has not come? I can also say validation based iterative hyperparameter tuning. Then once your let's say iteration is done, then your things are done. Then what? Testing. Very good. Test your model on test data. Correct. Very good. Then what? Ship to production. Correct. Correct. Inferencing or predict is like the same thing, right? Inferencing or ship to production. Correct. You will take the 97 and you will put it into production. The point is after that I will also look at my look at the model errors. Where does our model fails so that we can sorry so that we can create a fail safe point. Correct. Very good. Model drift. Very good. Model drift. Now it goes into the machine, the MLOps part of this thing, right? MLOps part of this thing where you say that I will monitor it, right? I will monitor it. I will look for data drifts. There is nothing very fancy that I wrote over here, but this is just a simple guideline that I have in my mind based on my experiences, and I just wrote it down. And I think all of these things are same for machine learning also, right? There's nothing new which I mentioned over here. But do you all agree, right? See, I know most of you are thinking, what is this? The first 5 steps are very stupid. They make no sense. But believe me, they will make sense, right? They will make. Okay, so what should we do now? Should we start our modeling also? Should we start our modeling? Yes, okay, because we understand the problem. What is the problem? Let's write down. What is the problem? Problem is detect, or I would not say detect, I would say recognize the digit in images. Correct? Formulate the problem. Formulate the problem is we will create a baseline DL model to recognize these digits. Correct? What is success for you? Getting Y actual. Okay. Accuracy. Now, what do you think? What kind of a metrics will you use over here? What is your metrics over here? Okay, first of all, tell me what kind of problem is this? Is this a classification problem, regression problem? What problem is this? Classification. Very good. All of you are confirmed. All of you agree with the statement, right? It's a classification problem. Okay. So now what is the matrix for a classification problem? Confusion matrix. Okay. Confusion matrix. What else? I mean, will you use confusion matrix to precision recall? Okay. Before that also, accuracy should be your first thing, right? And then you will say that, okay, I want to go deep dive and I will do a recall. I will do precision. Correct. And I will do F1. Very good. As you are saying, I will also make a confusion matrix. Very good. Do you all understand the matrix? Correct? Very good. Okay, so data is raw and dirty. No, in our case, it is not raw and dirty because it is already pre-processed for us, right? So in this, we are very fortunate. Do I need to filter the data for training and validation? It is already done, no problem. Pre-processing and feature engineering, right? Feature engineering and pre-processing. So forget about feature engineering right now, because remember I only told you that deep learning will do all the feature engineering for you, which is partially true also, right? Because all the image extraction is done by, sorry, all the feature extraction is done by deep learning also. But what is pre-processing? Do you think that is there any kind of a pre-processing that is required for us? Any pre-processing that you think is required for us? No pre-processing. Okay. Auto extraction, back propagation, image sizes, scaling. Okay. Others, image sizes. Those of my friends who are saying image sizes. So my friends, we are very fortunate. The data set has all images in data set are 28x28 size. What else? Scaling. What is scaling? Now see, okay, what is deep learning? Whatever you have learned today, what is deep learning? What are these particular cells doing? Let's say this is hidden layer, let's say this is input layer, this is let's say output layer. What is happening at these cells over here? Let's say if I1, I2 are let's say two inputs which are going at this particular place called H1 neuron. What is happening at this H1 neuron? H1 neuron is doing nothing. It says that add yourself to a random weight and then multiply it with the input and then add the second input, correct? And then a bias over here. Do you all agree? This is just nothing but, let's say, a multiplication and an addition, right? And then you will apply some activation function and all those things. But what is this affine equation? This affine equation is nothing but, let's say, a set of multiplication and addition, correct? Now, if all your features, let's say if I1, I2 are not on the same scale, if let's say I1 and I2 are not on the same scale, let's say I2 is very big number called 200 and I1 is a smaller number, let's say 1 or let's say 5. What is going to happen every time, let's say a number is multiplied to 5 or multiplied to 200 and then added something, this I2 will always generate a higher number. Do you agree? Even if I multiply both of them with the same number, let's say called Z, and let's say add a T, I2 is always going to generate a higher number, right? And the output O will always have a higher I2 fraction. Do you all agree? The weightage of I2 is always going to be higher. That is what we don't want, right? That is what we don't want. We don't want any value, input value, to be judged on its number, because the pixel value can be in the range of 0 till 255, correct? So some numbers will be very heavy, some numbers will be very small. But do we want it to happen? Do we want to, let's say, give higher weightages to 255 or let's say 254? No, that's not right. All should be treated equally. Do you all understand? And that is why, my friends, we will go with the scaling factor. Now, all of you gave the correct definitions and the correct functions. That scaling is nothing but a method of bringing your complete data into some range, right? Into one range, correct? Now, there are multiple scaling techniques that you can use. How many scalars have you learned? Does anybody remembers? I think some of you are saying min-max scalar. Second is standard. Very good. What is standard? Standard scalar is x minus x mean divided by the standard deviation, right? And min-max scalar is x minus x minimum divided by x max minus x minimum, correct? These are two things. Now, I am saying we will do a very simple, let's say, scalar. I want all the pixel values. A pixel value can be in the range of 0 till 255. I want all the pixel values to be in the range of 0 till 1. How can this happen? I want all my pixel values which are in the range of 0 till 255. How can I arrange them into 0 till 1? Let's say if there are three numbers, 5, 10, and 15. My question is what should I do with them so that all of these numbers are between the range of 0 till 1? This should not go beyond 1. This should not go beyond 0. Or let's say I want this maximum number to be 1 and minimum number to be close to 0. It cannot be 0, but let's say close to 0. It will be divided by the maximum number. Divide this by the maximum number. Pick this up, divide by the maximum number. This will become what? 0.3. This will become 0.5 and this will become 1. Correct? This is a very simple scaling technique that we will use, and we will say divide the x train by 255.0. Correct? Now see, I am going to say x train is equal to x train divide by 0255.0. Remember, please do it by a .o, because if let's say the internal numbers are integer, and if you divide by an integer, it will not generate a decimal for you. And how many integers are there between 0 and 1? How many integers are there between 0 and 1? Infinite. 0. There are no integers between 0 and 1. So what is going to happen? All your numbers will either become 0 or either they will become 1. That is why please put a dot after O. It means you are saying that I am doing a decimal division, and please return decimal numbers only for. The moment we run this thing, most of you are thinking you have just messed up with the images. Correct? You have messed up with the images. But to your utter surprise, the images are still the same. The images are still the same. But if I show you the X train 1512, this now is no more a integer. See, it's no more a 0 till 255. It is 0 and between 1 integers are there. We divide it by 255 because, my friend, now what is going to happen? All the pixel values will be in the range of 0 till 1. Rather than 0 till 255, I have now narrowed down this range into 0 to 1, which is more compact. You see, the image is still showing the same. Obviously, the numbers are gone. Now, what is happening over here? How can this happen that if we have changed the image, how does it appears like this? It should have changed accordingly. See, the problem is the answer is no. Because what is our image? What is the value of this pixel? It is nothing but the ratio between the next principal. I'll just show an example to you. Let's say there's an image like this, right? The ratio between these pixels are still the same. The brightness ratio, let's say this was 10, this was 20, and this was 30. Correct? Let's say there is an image which is like 10, 20, and this is 50, and this is 200, and this is also 200. And let's say 200 is the biggest number. So what is going to happen? This image, if let's say if I divide it by, let's say 200, what is going to happen? It is going to become something like this. This will become what? 1. This will become 1. This will become 0.5. This will become 0.5. This will become what? Can someone quickly tell me? 0.05. This is 0.1. This is what? 0.2. This is 0.225. Okay. Now what has changed? This is totally different from this particular image. Correct? From this particular image. This is totally different. But what if I say to you that no, these two images are still the same images, because the ratio between the pixels is still the same. See, what is the color? Why are you seeing this yellow color? Because there's a difference between this purple color in the background and this yellow color, right? There's a stark ratio. There's a stark difference between the ratio of these two colors. Do you agree? The same thing is still intact. The same thing is still intact. That is what is happening over here also. So you have changed the pixel values, right? You might have narrowed them down, but the relationship between them still exists, right? The ratio between them still exists. Only the magnitude is changed by dividing. Correct? Very good. Understood? Okay. So what we have done now, we have taken our, let's say, x, and we have divided it by 255. What should we do now? We have done the pre-processing. We have done the pre-processing also. What next now? It says modeling. Should we start the modeling? Yes. Yes. Okay. Now, is the pre-processing only done on the independent variables? Is it not done on dependent variables? Tell me. My question is, in machine learning, you have two types of variables, right? Independent variables, which are also called as the x or the input, and dependent variables, which are also called as y or the outputs. Correct? So in machine learning, my friends, do you only pre-process the inputs, or have you ever done pre-processing of output also, or the dependent variable also? No, no, only inputs. Yes, there's one person who says yes. What? Can you please care to explain? What is that pre-processing that you have done? Nulls. Okay, that is the part of data cleaning that we have already done. I'm talking about any kind of standardization, scaling, any encoding that you've done. Yes, we have done pre-processing of output. Care to please tell me what? One hot encoding. Very good. I said the answer also. Any kind of encoding. You guys, very good. One hot encoding. Do you remember what is one hot encoding? What is one hot encoding? What is, remember? Okay. Those of you who remember, very good. Those of you who don't remember, okay, first of all, tell me how many types of output will your model generate? This particular model. How many different type of answers it can say? 2. Very good. It will say what? It will give you 10 different answers. Please. MNIST model has to yield 10 different outputs. Correct? All of you agree, right? There's nothing but 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These many outputs can be generated, right? A digit can be either 0, either 1, either 2. Correct? All of you agree? Very simple statement. Now, do you remember your machine learning days when, let's say, you have a multi-class problem, and let's say the classes are ranked like this, let's say A, B, and C. Can your model yield an answer A, B, and C? The model can never say A, B, C. It has to be encoded into numbers. Correct? These are already numbers. We don't need to convert them into numbers. The category A, B, C still makes sense, that, the model cannot say A, B, C, but the model can say 0, 1, 2, 3, 4, 5, 6, 7, 9. Correct? The model can say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Correct? No, it cannot. Listen over here. They are looking like to you as a number, but they are not number. They are categories. They are categorical in nature. Understood? They are looking like to you as numbers. Please don't see them as numbers. They are actually labels. These are actually categories. Correct? They are categorical variables. Do you agree with this statement? You might have done this kind of thing in your machine learning also, my friends. When you are dealing with classification problems and you have numerical outputs, you convert them into categorical. I mean, not convert, they're already categorical. Correct? Now, what we have to do is we have to convert this categorical variable, right, into a one hot encoded value. Now, what is one hot encoded value? See over here. Let's say if you have 3 categories called A, B, and C. And let's say the output looks like this, that the first answer is A, second is also A, third is also A, but B, then C, then A, then B, then A, and then B. So how will you convert this into one hot encoded? You will say that now I will make what I have done is I have coded these, that okay, whenever there is a 1, we will say 1, 0, 0. Why? Because how are one hot encoding working? That we will call wherever the unit is present, we will put it as 1, and the others will become 0. So what is the first label? The first label is A. So it becomes 1, 0, 0. The second is again A. We will again say 1, 0, 0. The third is again A. We will say 1, 0, 0. Next time it is a B. So we will say 1 and then 0, 1. Correct? Because this is the B1 which is activated, and this one B is activated. So we'll say it like this, right? This is called as one hot encoding, right? Now there are multiple ways to do. How can I do one hot encoding? Wants to shed some light on one hot encoding? How can I do it? But we are working with our best friend. His name is Kiras, and Kiras says, "Why do you want to go to all these different libraries? I will give you all the things. There is something called as pandas.kiras, tf dot not pandas, sorry, tf.kiras.utils dot. Do you see what happened over here? The first thing in the train is a 5. So what should be the answer? The answer should be tf.kiras.utils.to categorical, and if I give it y underscore train, and if I show you only the 0th one, this is, can you see? 0, 1, 2, 3, 4, 5. This 5th one is the one, correct? What is the label? The label is 5. So the 5th 0 is a 1 over there. If I show you the first label, which is actually a 0, so the first value is 1. If I show you the second one, it is actually a 4. So 0, 1, 2, 3, 4. tf.kiras.preprocessing.text.onehot. Do you all understand what is this? What is happening over here? What we have done is we have taken the train variables and rather than converted into one hot encoding. I should not say it like this. I should say it like this. And you can say now this is of the shape. What should be the shape of this thing? 60,000, 10. Because now for each answer, there are some 9 zeros and 1 1. Correct? Can I say this thing? That now each answer will contain some 9 zeros and 1 1. If the output level has int as d type, is the encoding still required? You only tell me, right? If this is a categorical problem, let's say if this is a categorical problem, the answer will always be one hot encoding. All of you are sure, right? All of you are sure that what is label. Am I sure that all of you know what is label encoding and why you have done this multiple times in your machine learning? Correct? Why not label encoding? Because here you have multiple categories, my friend. You don't have labels already over there. So let's start the modeling part. Can I say we can start the modeling part? So here in deep learning, majority of your things are detection, recognition, which are classification problem and not regression. Okay, so modeling part, right? See, in Keras, there are 2 types of modeling. One is called as sequential in nature, and the other one is called as functional in nature. We are going to use sequential, right? What is sequential model now? See, please explain sequential. And wait, Baba, wait, I have not moved here talking about over here data. What is the meaning of sequential and functional? We'll talk about this thing. Wait. I'll explain you. So see, there are 2 types of modeling. The first one is sequential in nature. The second one is functional in nature. Sequential in nature means, as the name is saying, that every layer has to connect to the next layer only. This layer will talk to the next layer only. This layer will talk to the next layer only. This layer will talk to the next layer only. There, and what we have studied till today is we have studied the sequential type of modeling only. Remember all those bubbles that we used to make and we used to connect them? Did we ever connected any bubble to the next layer, to the next layer? Sorry. Did I ever say that this will connect to this one, or let's say this will connect to this one directly? No. We always said that everybody is going to respect the next layer only. That's it. But there are certain types of functions that we will study later, certain types of topologies, right? Where one layer might not just talk to only the next layer, but also talk to the layer in front of it. Might talk to layers in front of it. That is called as, those models are created using functional APIs, right? Sequential APIs are much more simpler to make, much more easier to define. Functionals are a little difficult. See, what have we studied till date? We have studied that this neuron will only talk to this, and this. Have we ever drawn a diagram where this one talks to this directly? Skip connections. These are called as skip connections. Is anything that we have studied till date? No, right? But these kinds of connections also happen, right? We will study a model called as ResNet, where we will study over there that you actually can do one thing, that you can transfer the knowledge of a layer to some next layers also, right? So there we will study those things, which is called as skip connections. But today we will use a sequential layer. Sequential layer is a very simple modeling is very simple. It says that if you have declared a layer, it will only talk to the next layer. Later on, we will see we will make models using functional also, right? We will make functional ways of doing things only. We will leave sequential and we will use functional only. Functionals are much more advanced, right? They give you more control of the model, right? You can design that it can have multi. So let's say there are certain models where you have multiple inputs also. So right now, what is happening is, let's say that you have an image only as a input, right? It might happen that there are certain problems like image search, right? Like image search, where the input are two images together simultaneously. So in that particular case, you will have its input layer different, you will have its input layer different, and then there is a hidden layer which talks to this, this one talks to this, and then later on they connect to each other, right? So there are those things also, right? And again, don't worry. This just looks scary. This is not. See, I'll show you ResNet model so that you are more comfortable. ResNet. This is a very simple ResNet model. Can you see? Very simple model. Please read it like this from here. You have to rotate your neck, or let's say the laptop machine. And this is a 330. It's a very small ResNet model. This is only a 34 layer residual over here. And you can see it goes down, and you can see that it is not simple like this model on the first place. On the first place, this model is very simple. It connects only to the next layer. See, only next layer, next layer, next layer, next layer, next layer, right? Whereas this one is connecting to the next layer, but also skips the connection and then talks over here.
Let's have a quick quiz question, guys. And the question is, what is the Turing test used in the context of AI? And your options are to assess the computational power of a machine, or to evaluate a machine's ability to exhibit intelligent behavior, or to test the accuracy of a machine learning algorithm, or to benchmark the performance of a neural network. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Okay, so we are talking about sequential model. I can write down sequential is what? How to get sequential? We will say model is equal to tf.keras dot model dot sequential. Now see, notice over here how beautifully Keras is designed. How beautifully. See, you are making a model, you want to make a sequential model, just simply say tf.keras.model.sequential. So what we are doing over here is we are creating a model type. What we've done over here is we have asked Keras that Keras, listen. Keras, listen, I want to make a sequential empty model. It will say, okay, I will make a empty model for you. Empty, nothing is there. No layers, no neurons, nothing, right? Just simply create a model. Now, do you remember that this was our initial skeleton? Remember? You would connect all these layers over here, these like this, and do like this. Correct? Do you notice that we have to make this kind of structure over here? Correct? So what we said that Kiras, we want to make a sequential structure, and Kiras said, very good, sure, go ahead, make it. Now, do you see a problem over here? The input are lined up like this. Input 1, input 2, input 3, input 4, input 5, input 6, and they are like a one kind of a box structure. Can I say it's a one column kind of a model? Input, sorry, not model, input. Can I say it almost looks like a one dimensional thing which has only rows, correct? But our images are like this now, correct? My image is like this, which has 28 cross 28. So what do I do now? I have never taught you anything where you can feed in directly a 2D image. We have never talked about this thing, right? We have always talked about that, you will have a image in this 1D kind of format, and then you will send it. Some of my friends are saying reshape, but how do I reshape? I mean, how do I send this thing? Okay, first of all, everybody understands, right, that this particular image is a 28 cross 28 image, and 28 cross 28 image means that it is nothing but a 784 pixel value. Can I say this thing? That 28 cross 28 is nothing but, let's say, 784 pixel values are there, correct? And each value is in the range of 0 to 1. Okay, understood. Everybody understands this thing. So it means there will be I1, I2, I3, I4, and at the end there will be I784. Does everybody understand? There will be 784 inputs for one image. But again, the problem is this is a 2D image. 2D image. How do I send this 2D image over here? This is asking me for 784 pixels. How can I send this 784 pixels like this? This is why we have a concept called as flattening. A concept called as flattening, which will convert this 2D image, still a 2D, it will be created like this. How? The question is how? How can you convert this 28 cross 28 image into a 784 image? Correct? Is this question running in your mind also, that this 28 cross 28 can be converted into 784? The answer, I think most of you are saying it correct. Yes. I will do nothing. I will just, let's say, slice this into 28 parts. Column 1, column 2, column 3, column 4, column 5, column 6, column 28, and I will place them one over the other. One over the other, like this. This step is called as flattening. This step is called as flattening, that you open up that image and then flatten it up. Is the flattening reducing the number of dimensions, or it does make the image dimension equal to 1? No, it is not reducing the dimension. If you notice, right, this dimension is still the same. I mean, the image is still the same, right? But we have divided that image into multiple parts and just tagged it over one over the other, such that our neural networks that we have learned, now they become compatible. Should I repeat again? See, the problem is, I'll explain you. The problem is very simple. The problem is that there is this structure that we learned at the step A. We learned a structure like this, where we will send all these input, correct? And then what we did, the problem is now that this image is a height cross width image. I have no way to send this into this model. So what I'm doing is, I'm tearing this image into multiple columns, and then I'm stacking those columns one below the other, and then I'm just putting it over here. It becomes now 784, and that's it. Now, how do I do this thing? The answer is very simple. I will not do this thing. I will ask my friend Kiras. Kiras already knows this thing that Shivam, you have learned that neural network model in that way where it is taking it into a 784 format, but your images are 2D. I know this thing. So you can send me, you can actually make a layer inside. Rather than sending it to an input layer, send it to a flattening layer. Correct? So what I'm going to do over here is, my friends, I want all of your attention over here now. Please, for 2 minutes, no chat, no questions, no answers, please, just for 2 minutes, right? So I made a empty model now, and now because this is a sequential model, what I can do is I can say model.add. It means that add the layers for me. And as I will add the layers, they will automatically stack themselves. That okay, this is layer 1, this is layer 2, this is hidden layer, this is output layer, because this is a sequential model. Everybody knows that it has to connect to the next layer. Correct? And I will show you now. The first thing that we will do is model.add, and you will say model. First of all, you will add now layers inside it. Correct? Do you remember? What we used to do is we used to make these layers, right? These fancy layers, input, hidden, output. So what I'm going to do is I am going to add a layer. Again, tf Keras is very simple. It says tf.keras.layers and .add input layer. Now what are we doing? We are saying that, hey, I want to add a input layer which has a shape of 28 cross 28. Add the first input layer and specify the input shape. Correct? Now, as we were discussing, that this input layer cannot work, right? It cannot digest the main neural network cannot digest the 28 cross 28 format. So I will say tf.keras.layers.flat. I will say that, hey buddy, can you please flatten these images for me? Let's write down, and actually it's already written over there. I will just copy. Very simple. First of all, we created a model. We said that we want a model, my friend. I want a model. Then I said that I want to add a input layer. We have to specify. Sorry, we have to specify that what is the data coming in, right? What is the data that is coming in? The data that is coming in is 28 cross 28, right? The shape of the image that is going to come inside is 28 comma 28. Then we said that whatever that image is coming is, I'm sorry, but it is not compatible. So please convert it and flatten this image. Please convert that 28 cross 28 image into a flatten. The flatten will convert it into what? 784. Then what comes after input layer? What comes after input layer? What have we made over here? Hidden layer. Very good. Hidden layer, my friends. Hidden layer, all hidden layers, right? Or they are also called as dense layers over here, right? Dense layers. Model.add tf.keras.layers.dense. Now, what is the one unique thing that you see over here that you need to tell to the model that once you are making a dense layer? I'll repeat my question again. I am saying that let's say you are designing the hidden layer, right? What is the one thing that you have to keep in the mind? Nodes. Very good. Nodes, or do you mean neurons, right? That how many neurons are fitting inside over here? How many neurons are here? How many neurons are here? Correct? Shape of the dense layer. Exactly. The same question. What is the shape of the dense layer, or what is the neurons inside it, right? So let's say I am going to put it 100 over here. I will explain you why I have taken 100. Don't worry right now. I will tell you later on. Please, right? Let's say we are telling that, okay, very good. We have now a flattening layer. Let's say, sorry, this is the input layer. And input layer is how many neurons? 784 neurons, right? How many I am taking in between? I am taking in between hidden layers as 100 neurons. I am taking 100 neurons. Now, what is one more thing that I have to remember over here? See, when you are defining a dense layer, you have to just tell it that how many neurons do you want. It will automatically assign the weight. It will automatically assign the bias. You don't have to worry about it, right? You just need to tell it that how many neurons do you want inside it, right? The weights and biases will be taken care by the network itself because they are random in nature. It will automatically decide them. You don't need to worry about it. But there is one more thing that you have to decide, that what is the activation function that I should use over here. Activation function, right? Relu, okay. As all of you are saying relu, I will add relu over here, right? I will add relu over here. What is the next layer? What is next that we should add now? Let's say we have added output. Very good. The output layer is also called as dense over here, right? A dense layer is nothing but, let's say, a layer which connects to every other neuron in the next layer. How many neurons should be there in the output layer? Can somebody please tell me? For this particular problem of MNIST, how many outputs should be there? 10 different outputs. Very good. 10 different outputs. And then activation function. What activation function will I use? What activation function should I use? Sigmoid, softmax. Do you remember we talked about it? That I will explain you what is softmax. I didn't explain you softmax, but I told you that in categorical problem at the output layer, we will use softmax. Correct? Let me say output layer with 10 output. Correct? I mean, it's right. How many outputs can be there? How many outputs are possible? Can you tell me? For one particular image of a digit, how many possible outcomes are there? 10, right? 0, 1, it can be 2, it can be 3, it can be 4, it can be 5, it can be 9, correct? So 10 different outputs. Why only one hidden layer? Why only one layer, right? One hidden layer. And second question, why 100 neurons in hidden layer? If you have these two questions, please park them. I will answer them a little late. Right? So, my friend, till now we have only done something called as feed forward neural network, right? We have just done the feed forward pass, right? We have not done the error calculation. We have not done the back propagation. Correct? We will do it. But before that, see this thing. Does this thing make sense to you? What I did is I asked my model that can you please print your summary? Can you please print your summary? So this is how your model looks like as of today. This has 784 inputs. Then it dropped to 100 inputs. And then it dropped to 10 outputs, right? I will write down the number on the top so that it is not confusing. These are 10, these are 100, and these are 784. Does everybody agree to these numbers over here? And does it make sense? That it starts with the input layer, then at the hidden layer they drop to 100, and then it is the output layer which is this 10. Correct? Okay. Do you understand that these are the layer names? And these are the corresponding shapes of the data that are present in that particular layer. Correct? It is actually telling you that how many neurons are there. So in the first layer, in the flattening layer, 784 neurons. In the hidden layer, it is 100 neurons. And in the output layer, there are 10 neurons. I have a question for you now. All of you, please listen to my question. It's a very simple question, but please listen to me. This term called parameter, it means that the number of things will be updated. Listen to me. Things which will be updated It means how many things will be updated when you are doing a back propagation. This is the answer for this particular layer. Can you tell me why this happened? I will repeat my question again. Parameters are nothing, but it is the value of the number of things, or uh, the number of things that will be updated while you are doing back propagation. Can you please tell me the mathematics of 78500? For your reference, this is how your model looks like. This is how your model looks like. Please tell me the maths. If there are 784 neurons in the input layer, and if there are 100 neurons in the hidden layer, and they have to make connections, how many connections will be made? And everybody has to talk to everybody else. Can I say that weights will be 784? Weights is what? Weights is nothing but how many connections are made between the two layers. Can I say 784 into 100? And how many biases are there? Biases are there, that how many neurons are there in the hidden layer? 1, 2, 99 and 100. Do you all understand the mathematics? Weights is equal to neurons in last layer multiplied by neurons in this layer, and bias is neurons in current layer. I should not call this current layer. So 784 into 100 plus 100. Correct? Do you all understand? Agree to this point, that these many number of weights and biases will be updated when you do the back propagation. Correct? And 78500 plus 1010, if you add up, it just becomes what? 79510. Correct? Very good. Very good. You guys are very, very, very smart. Very smart. Fantastic. Fantastic. Okay. So now what we have done is, we did one feed. We have told the model that, hey, listen, model, you have to make these many layers, these many neurons, and you figure out the weights, you figure out the mathematics, you figure out the biases, you figure out all these things. I have told you the feed forward. Correct? We will now define the loss. Can I say the loss function that is equivalent to error, and also what optimizer to use for back propagation. Now, before that, moving right, let me also talk about softmax. I know I have always said that I will explain you later on, but today is the later on. Today is that later on. Okay, so this is your image of neural network over here. Correct? Very simple neural networks in front of you. Very fantastic. Right? Very good. And just get rid of these things also. And also this one, Okay. Now, my friends, let's say there is an image of a 7 which is going. There is a image of a 7 which is going over here. And I'll actually do one more thing. I'll actually make 10 neurons so that it is easier for us to understand. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Correct? There are 10 neurons in the output. There are, I will say, 10 outputs. So what is happening over here is, see, every neuron is representing a digit. Do you agree? every neuron is representing an image. This is representing 0, this is representing 1, this is representing 2, this is 3, this is 4, this is 5, 6, 7, 8, and 9. Correct? Now, what do you think is going to happen? Let's say if there is an image of a 7 over here. You will flatten this image first of all. It will go from the new input neurons. They will fly over here at the hidden weights. Correct? They will have some weights. They will have some biases. They will do some affine equation. Affine equation will then do what? Affine equation, you will apply an activation function over there, and then you will connect them over here. Right? You will connect them to all these neurons. Now, these neurons will also perform their own, they will have their own weights, they will have their own biases, and they will try to, let's say, predict some number. Correct? This particular output number will predict a number. Correct? All these outputs will predict a number. Because it's simple mathematics, right? What is the mathematics? We are saying summation of input into weights plus bias. Correct? This is nothing but a mathematical equation. Don't get confused, right? I have written it in that way, but this is what it is, right? I1 W1 plus I2 W2 plus bias. This is just a simple mathematical equation, and you have put it under an activation function. So these outputs are going to yield something. Correct? They will yield some numbers. Now, and let's say the training is complete. Let's say the training is, working on or let's do one thing. This is the first time it is happening. Now, because there are random weights and random biases, right? They will predict what they will predict. The Y predicted. They will predict something called as Y predict, right? YP. And what is this YP going to be? If you have, let's say, put up a activation function like relu, they will regress a value in between 0 and positive infinite. If you would have put up a sigmoid, it will yield values which are in the range of 0 to 1. And if you would have put up a tan x, then it would have yielded value from -1 to 1. Correct? But that's not what you want. What do you expect from these outputs ultimately? What do you expect? Okay, let's say if the model is trained completely, what do you expect? How will you identify that this is a 7? See, the model cannot say SEVEN, right? No, it's not going to say. It is neither going to say 7. So what do you expect from the model? We are expecting, listen to me now, we are expecting from the model that everything else should be 0. This all things should be 0. And the model should say 1 over here and all 0 again. Those of you who do not agree, this is exactly what is your Y actual for an image of a 7. Remember, you have done a similar kind of encoding. You have done a similar kind of encoding for 7. So this is what you are expecting. Remember the term, expecting from your model. You're expecting from your model to say 0 for everything and 1 for 7. Can I say this is nothing but, let's say, the percentage probability that it thinks what it is? It thinks it is 0% 0. It thinks it is 0% 1. It thinks it is 0% 2, 0% 3, 0% 4, 0% 5, 0% 6, and 100% 7. Can I read it in this particular way? So now, my friends, what I want is, I want to design a kind of a softmax function, activation function, which should not just bind my answer into 0 to 1, right? I want a activation function which should not just bind my numbers into 0 to 1. Activation function which first of all should bind my numbers into 0 to 1, but it should yield the probability. It should yield the probability. Now, obviously, if a number is between 0 to 1, we can say, Shivam, it is a probability, and I am okay, right? But the problem is, okay, decide now. Which answer will you take? Let's say there's an example in which you have to decide that is the answer A, B, or C. And the probabilities are like this: 0.9, 0.9, and 0.9. Decide now. Which one is the answer? Which category is the answer? Is it category A, category B, or category C? No, we cannot do, right? To decide somebody, that, let's say if you have a competition between somebody, right, you need to make sure that everyone is on the same base. This is where, my friends, your activation function softmax comes in. Softmax says, I will do a third thing. I will make sure that if you sum all the probabilities, sum of all the probabilities will now be equal to 1. It means that earlier that number which was coming up, right? Let's say, all of them are yielding these random numbers A, B, and C. Let's say they are yielding some numbers like 37, 54, and let's say 69, 63, right? So what is going to happen? 50, this is 54, right? So what is going to happen now? Softmax is going to first of all convert them into such a way that they are between 0 to 1. They are probabilities, and also all of their three sum is equal to 1, right? The sum of all the three numbers is going to be 1, and this, let's say, becomes your 0 0.6, this becomes your 0 0.3, and this becomes your 0 0.1. Can you now detect which is the answer? Percentage probability. The answer is C. That is exactly what softmax does. The formula for softmax is e to the power x divided by summation of e to the power minus x, and this is also minus x. Softmax says that I will take all these numbers and define them in 0 to 1 in such a way that they yield probabilities, and if you sum up all these probabilities, they will be equal to 1. This is what softmax does. This is what I was trying to delay for you. That is why we have applied the softmax. So now what is going to happen? The output of this particular model is going to be the probability. So let's say even if the image is a 7, even if, right? Even if, let's say, the image is a 7, there will be output for all the model will try to say that this is also a 4, this is also a 2. See, it cannot happen that it will always say you. So what is going to happen? Let's say if you are sending a image 7, now your model will say that the y predicted number is not just 0. It will say that this is 0 0.00001, and this will not be now a 1. It will be 0 0.928, and this will, let's say, this is 9.2. This is again 0 point some 1. This is, let's say, 0 0.2, and this is again some numbers over here 0 0.0. So what will you do now? You will pick up the number which has the highest probability, simply. Correct? So what we have done over here is, my friend, we have defined that, hey, listen, my friend, this is what your feed forward is going to look like, but we have still not decided on the what loss function and what let's say optimizers we have to use. So what we're going to do is, we are going to say loss function. So we are going to say model.compile. Now Keras is such a simple thing. It says that, hey, you don't need to do all these things differently, just come and say to me in just one line. So let's see, the first thing that it is asking you is that what is the optimizer that you want to use. Optimizer is nothing but the same let's say it's the same function that will do the back propagation for you, right? So we are saying, hey, that we know one. What is the name of our optimizer that we have studied? We have studied the algorithm called gradient descent. So see, my friends, in Keras it is called as SGD. SGD means stochastic gradient descent. It is nothing but a flavor of gradient descent only, which works in a stochastic manner. Stochastic, the term is random, right? It means a random gradient generator, gradient descent algorithm over here. And most of you are asking me, Shivam, where to write learning rate? There, see, Keras is very smart. Keras has already done this thing for you. I'll show it to you. If you go inside tf.keras.optimizers.sgd, and if you run this one, you will see it says there is a term called as learning rate. Do you see over here? Let's read this one. It means a tensor floating point value. It means a floating point value or a schedule, that is a schedule over here, or a callable that takes no argument and returns the actual value to use. The learning rate defaults to 0.001. Those of my folks who are saying that, Shivam, who defaults it to 0.001? This is the answer, right? So the SGD learning rate is by default taking it 0.001. You can change it to whatever you want. This is a hyper parameter. This is a hyper parameter. You can change it. I will leave it by default as it is right now. I will not change it. And I will say learning rate is 0.001. How to change it? How to change it? This is a function. Pass it the argument and you can change it. You can change it to 0.005 over here and it will change. Okay. So actually we have defined optimizer first. We should have defined the losses first, right? That what kind of a loss function are we looking over here? Loss, right? We are going to use something called as tf.keras.losses and we are going to use categorical cross entropy. Categorical cross entropy. Now, I know most of you are thinking, what is this categorical cross entropy and why are we using this thing? I will explain you as I told you. Give me some time. Right? I'm going to run this over here and run this thing. So what has happened now? I have told my model, hey, I have made a model, a sequential model for you. This is the input, this is the hidden layer, this is the output, this is the loss, this is the losses, this is the optimizer, and this is what accuracy I want. That's it. And it will automatically do all those things. Do you remember we were when we made our model from scratch, we had to write our own DE by DW. We had to make our own losses. We were storing it inside a list. Then we were displaying it, right? All of these things will be taken care now by Keras. Does it make sense? I will explain you in detail what cross entropy is and why are we using over here. Don't worry. I can explain you right now also, but I just want to show you first of all that the model, how it runs. Model.fit. And here comes the magic. You all are aware of this fit thing, right? Machine learning folks. Fit. What is the X? What is the X for this particular problem? What is the X for this particular problem? Images. Images are stored in X underscore train. Very good. What is the Y for this problem? The Y is Y train, which is the one hot encoded things that we have given, right? And now we will define epochs. Epochs means that how many times do you want to do feed forward, error calculation, backpropagation, feed forward, error calculation, backpropagation. How many times do you want to do this thing? One epoch means that all the 60,000 images have gone inside the model. They have done the feed forward. They came and did the error calculation and then they went back to do backpropagation. One epoch means one, let me write down. One epoch is all data has gone through FF, error calculation, and BP. One cycle of all data has gone through this. If I run this thing, you will notice magic. It says that I am going one epoch and it prints the loss for you and the accuracy also. Fantastic. You can see 79% accuracy already done in the second epoch. Third time the data is going feed prop. 83 accuracy. Fantastic. 85. Very good. 86. 87. And I have just run it for 10 times only. And as all of you can see, how did you determine 10 epochs? I just wanted to run over here right now. Epoch is also a hyperparameter. And you can see the model is almost done. It took almost an average of 6 seconds to run one epoch. And this accuracy is over there. How is it calculating accuracy without Y test? My friend who is saying that there are true labels not given. Can somebody help my friend? Where have we supplied that these are the correct labels? Using Y train. Very good. This Y train contains the original answer to that particular image. So the error calculation was happening what the model is saying versus what is the actual answer. Do you remember the classes? Correct. So what we have done is we have trained our model. Now, I remember we were talking about test, validation, and train, validation, and test. So what is going to happen is Keras is such a fantastic guy. Keras, what you can say is you can ask Keras that Keras, brother, I forgot to bring my validation data. Can you please divide my Can you please listen to me? Can you please divide my training data and give 90% for training and let's say 10% for validation? Listen to me now. I'll repeat again. I am saying, Kiras, my brother, I'm sorry, I forgot to bring the validation data with me. I have only 60,000 images. What do I do now? Rather than me making it separately, can you please divide my data into 90 and 10 split? It means give 54,000 images for training and the remaining 6,000 for validation. It will say no problem, done over here. And you can see over here now. First of all, it runs on training, then it runs on validation. Can you see now? Validation loss and validation accuracy. So first of all, it trains it on the validation, training data, and whatever weights are adjusted based on it, it calculates the validation accuracy and validation losses. Does this make sense to all of you? That how validation data is being used? And you can see over here, this is a very interesting thing happening over here. The model is trained. The model is almost gone to validation accuracy of 92%. One of my friends is saying, is the model not overfitting? So what is the definition of overfitting? Can somebody please tell me? Or how, or let's say, don't tell me definition. Tell me, how do you identify that this model is overfitting? How do you identify that the model is overfitting, my friend? It is already at 92. So it means any model which gives above 90 is overfitting. So how do you identify? Can you compare the validation, let's say, accuracy and the training accuracy? Are they not in the same range? So I would not judge this that this is overfitting, but I would definitely look around for it. I want to quickly show you how to use the model now. See, we have made a model. A model has got some 91%, around 91% accuracy. Let's try to test this model, correct? So let's pick up one random image from the test data, correct? So what I'm going to do is I am going to take this image. 1, 2, 3 is my favorite number, right? Let me first of all show you what this image is. All of you can see that this is the image. Okay. What we are doing is we are going to pass this to the model. We are going to say def predict image. First of all, what we have to do, we have to resize that image. Remember, before sending the image, you have to make sure that you are resizing the image, because all your training data is trained on resized image. Sorry, rescaled image. Sorry, I said resized. Sorry, rescaled images, right? So I will rescale this image. Also, do you remember that your model has actually a habit of taking images in this format? What is this none over here? Does anybody can guess what is this none over here? So the none over here represents that the amount of images, number of images multiplied by h multiplied by width. Now see, a model can have any amount of images, right? You are bringing 60,000, somebody can bring 10,000, somebody can bring 1,000 only, somebody can bring 1 only. So the model has a none parameter over here. It says whatever you want to fill, I don't care. I know that I have to keep it, right? It is the number of images. So what I am going to do is I am going to say image is equal to np.expand dims. I will explain you what this is happening over here. But let me first of all show you the magic that all of you have been waiting over here. This is what I have converted. Then you will say model.predict, and then I will say image. I will save the result, and then I will say return, or let's say print f model predicted, and then I will say np.argmax result. This should work. We will send the image test 1, 2, 3. See, this is the image that we have used. Test 1, 2, 3. I will explain you all these things. Don't worry. Don't worry. Model predicted 6. Correct. We'll also do one thing. We'll print the correct label y underscore test and num plt.im show x underscore test and then num. Okay, so now we can I would need to pass this thing. See now, now we'll pass this. Model says 9, correct label is 9. See, fantastic. 15th image. Correct. I am passing some random images from the test data. Remember, test data. And I am showing it to you over here. Correct? Do you all see the magic now? Can you all understand what is happening over here? You can see over here what is happening is that the model is saying 1, whereas the correct answer is 7. Right? Okay. Let me show you one more thing. Confidence of, and then you will say result. See over here now. The model said that it is 88%. It looks like as 1, whereas this is 7 over here. Right? So it's not that every time the model says the correct thing. The model has, sometimes it miscorrects. It does not correct correctly. Why? Because see, this is a very tricky one, right? And let me show you MNIST wrong labels. See over here now. I don't know if you can see this or not, but you cannot see obviously. Let me one image. I'll try to zoom into this image and then I'll show you what I'm trying to say over here. Right? These are all the wrong labels, or let me actually show you the difficult labels. See, these are the difficult labels over here. Can you see now? Can you detect these things? As a human also. So the black one is the correct labeling and the red one is the what the model tried to say. Difficult, right? So sometimes it is not just the model which is wrong, right? Sometimes it is the data also which is not correctly done. Also, our model is not even 100% accurate. It's just 90-91.
Just a quick info guys, Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
How does it correct itself is based on the gradient, if you remember, right? Based on your gradient descent equation, we were able to find out that, I'll just show you the example over here, based on this thing, right? What we did is we found out first of all the culprit. All of you remember the error was what? The error was, let's do a quick revision. What was the error? The error was y predicted minus y actual. That whatever is the actual answer, how far is the prediction from it? Correct? How far is the prediction from it? So we said that what is yp? Yp was nothing but, let's say, the input, which is x into w plus b, correct? Minus ya. Now, can you tell me how many out of these 4, who are the culprit for this error? Out of these 4 values, who is the culprit for this error? See, because ya cannot be the ya cannot be the culprit, because ya is a constant. That is the original answer. That's the correct answer. X being the input can also not be a culprit. So we are left with 2 culprits, that is W and B. And obviously, you know that W and B were random at the very first point. Remember that we talked about that W and B will be random at the very first position. Correct? So that is what we have done over here. We figured out that W and B are the ones who are responsible. Now let's say if I try to draw a graph, between error E, and the weight W, and let's say this kind of a graph is made. What is the point where you want to settle? Point P1, point P2. I am exactly writing the same coordinates also that we did in last class also, or point P3. Where do you want to settle? P1, P2 or P3? Why P2? You want to settle at P2 because P2 delivers you the least error. This value of W is giving you the least value of error, correct? Do you all agree with the statement that this W value is giving us the least error? So we will pick up this W rather than picking it up randomly. Now we have a motive, we have a direction, correct? So now what is going to happen? Let's say if your current W is over here, you have to move it and bring it towards this path. You have to change that random W to this particular W where it settles at the minimum error, correct? Now how do you do this thing? For doing this particular thing, right, we figured out that how to find this lowest path. For this, I think our friend mathematics came into picture. I mean, maths has always been there, but I think geometry came into the geometry thing came into this, graphs came into action, and they said that, hey, listen, if you want to figure out this point where the particular point is delivering you the minimum point, it means that your slope to that particular line should be 0, or can I say it should be parallel to the x-axis, correct? Any point where it is delivering you the minimum effort, where it is delivering you the minimum value of x, right? Or wherever the direction of the slope, direction of the graph is changing, that particular point will always deliver you a slope which is parallel to x-axis, or I can say slope is equal to 0, right? So what we are doing is we are saying that, okay, we will calculate dE by dW. And in mathematical terms, in calculus terms, this is called as differentiation of error with respect to W. Differentiation of error with respect to W, right? And this will now give you, what is this dE by dW? This dE by dW is nothing but a small step taken towards that optimal W, which will deliver a minimum error. Understand? This dE by dW, or also called as the gradient, or also sometimes called as the differentiation of E with respect to W, is nothing but that one small step that this W, the old W, is taking, where it might go and sit where it is going to deliver you the minimum E error. Do you all understand? Right? So what do we say? We say it over here that W, the old W, the new W will be old W minus dE by dW. You tell me now, what was your role in linear regression? Were you the one who was setting down and settling the slopes? Or let's say in the decision tree, were you the one who were making the trees? In the random forest, were you the one who were making trees and doing the ensembling of them? No, right? It was the machine learning which was doing for you, right? It was the mathematics which was doing for you. But now there comes a very good question, that what is my job? See, your job, it looks very easy to you as of today. Your job is not that easy, because a lot of hyperparameter tuning will be required for this relationship to exist between error and this weight W, correct? A lot of these things, like I think majority of you are still asking me this question, that how many hidden layers are required, or how many neurons in a hidden layer is required. That is a very big hyperparameter. Nobody knows this thing. Secondly, which algorithm to use? One of my friends says PhD people make algorithm. Obviously they make algorithm, but which algorithm to use? Will you use a CNN? Will you use a FCNN, right? Will you use a RNN? Will you use a CNN with multi-chunk model? Or will you use a model with multi-con, multi-chunk model? This is a job that you will do, right? See, PhD folks that I think you were saying that, their job is to make algorithm. No, their job is to make generic algorithms. Their job is to make generic algorithms. And you as an applied scientist, your job is nothing but, let's say to make sure that these generic algorithms can be applied to your custom data and can be optimized for your custom applications. Does it make sense? What is your job? Please don't think that your job is just to write code. No, your job is very much primal over here. It's not trivial, right? You will be the one who is responsible for making all these algorithms and doing the changes. Okay. So coming back to this particular thing, right? Very good. I'll draw that particular game again, right? That this neuron game. 2 inputs, 3 hidden neurons, and let's say 2 outputs. We had a very good life connecting all these things. Can somebody quickly tell me that how many weights are there between the input layer and the hidden layer? How many weights are there between the input layer and the hidden layer? 6, because there are 6 connections. And how many biases are there? 3 biases. So now how many weights are there between the hidden and output? 6 again, and then weights are 6, and then biases are 2. Very good. Not 3, 2 this time. Very good. Now see over here now, my friends. I told you something called as affine equation, right? We were doing something called as affine equation, and affine equation says that if a hidden layer is there, our hidden layer is nothing but, let's say, the input x1 with a weight w1 plus a input x2 with the weight w2 plus a bias. Correct? Right? Very good. This is a very simple term over there that we used. This is called as affine equation, and through affine equation, we are creating a relationship, right? A linear relationship. Learning rate, or also commonly in a short form called as LR. LR. Now see, learning rate, let me ask you a question over here. Let's say that you are descending from a flyover. Let's say this is the flyover, you are descending over here, right? And you have to perfectly stop at this particular point, right? Because let's say this flyover is again going up. Let's take an example that this is the flyover. It is coming down, you're driving your car, and this flyover goes up again. It connects to another flyover, and you have to stop exactly at this particular point. Let's say this is a good cafe over here, and you want to have a coffee over there. It's a cafe and you want to go there coffee. Now let's say you're driving your car over here, and you have been driving your car with a good acceleration, right? The speed has been very good. You're driving. Now what is your instinct over here? What will you do over here now at this particular point if you have to stop at this cafe, which is exactly at the lowest point of the flyover? What will you do now? Okay, let me ask you 2 questions. There are 2 options: that you will remove your, let's say, your foot from the acceleration, right? From the gas pedal, you will actually take your foot back. Second option is you'll obviously do that, but you'll also apply the brakes. Option A or option B. You'll apply both the things, because what is happening is, even if you slow down the speed, my friend, because of this coming down on a slope on a flyover, your speed will actually increase. Correct? Because of the momentum, your speed will actually increase even if you are not, let's say, applying any extra gas. Am I correct? So you have to actually apply a opposite force, right? You have to apply now brakes, so that you can go against the momentum also and take a complete halt at this particular point. Do you all agree? Simple basic physics, right? If you have to stop at this particular cafe point, what you have to do is you have to exactly you have to actually go against the gravity, against the momentum, and press brakes over there. This is what exactly happens, my friends, when we are using the gradients, right? Whenever we are using the gradients. Now let me just draw the same graph, but instead of a car, now we are talking about a gradient, right? Let's say this is our weight W, right? Which was sitting over here. Now we said that, hey W, go down, right? Hey W, go down and take a step of dE by dW, right? What we are asking it the same thing, correct? What we are saying W, please change yourself in such a way that we will minus a number from you called dE by dW. And dE by dW, if you know the basic mathematics behind it, right? dE by dW is nothing but the slope, right? And the lower you are going, the higher the slope is going to be, right? At this point, this is going to be higher, correct? Right? And this is taking steps over here. Now, if I do not control the speed, my friend, if I do not control the speed, what is going to happen? This will go over here, this will go over here, this will go over here, and then it will go at this particular point, but it won't stop, and it will go to this point. And then it will go back again, and then again. It will never settle at this particular point, or it might happen that we might go on the top and miss the valley point. This thing is also called as the valley point. A very simple concept which says that, hey, listen, when you're driving your car and if you have to stop at the lowest point, you have to apply brakes also. Otherwise, your car will go back on the top. This is where the term called as learning rate comes into picture. Now, learning rate says that, hey, listen, we will do all these things for you. I will modify this formula a little bit. And now I will say that W is nothing but W minus alpha into dE by dW. We are multiplying this dE by dW, our speed, with a constant term over here called as LR, or learning rate. This particular is denoted by a symbol called alpha, and this is called a learning rate. Now, what this learning rate is doing is, this learning rate is a number very less than 1, right? It is almost 0.001, right? This is almost 0.001. Now, do you all understand what is happening over here? The influence of dE by dW is now getting multiplied by 0.001. So what is happening now? We are taking a very small steps now. So dE by dW is going very slow, correct? And now, because these are very steps, it will stop over at this particular point, right? What is learning rate, and how learning rate is actually helping you to make sure that you do not go way past of that particular origin, correct? This is called as learning rate, my friends, right? So LR is a hyperparameter. Listen to me. LR is a hyperparameter, and there are multiple things through which you can do, right? I made a sheet for my last batch folks to explain them, and let me show it to you over here. Give me 1 second. You can see over here now in this particular sheet, I'll show you that how I am using, let's say, a graph, and then you can see the same gradient flowing over there, but basis on the learning rate. So see now, if this is where learning rate is equal to 1, what is happening, right? I took a particular function called as v square, and I took this thing, and you can see now, if it is the learning rate is 1, it does not even go down, right? When you take a learning rate of 5, see what happens. It suddenly goes down. If you take a learning rate of 0.2, see how it goes down. 1, 2, 3, and it stops over here. If you take a learning rate of 0.001, you can see now it goes over there. But now you can see the steps are going very small. Can you see all these things? The steps have reduced dramatically, correct? Why? Because learning rate is minimizing dE by dW now. So you can see in this very particular example, the first step is very big. But then eventually, as and as you're getting closer to the valley, your steps are getting very small. Learning rate is a hyperparameter. You will always choose the learning rate based on the graphs. You will first of all see your graph of error, right? And let's say this is a graph, and right now you won't understand the term called epoch, but let's say you have a graph like this. Whenever you are training your model, you have a graph like this. Epoch means iterations, that how many iterations you have done. So one epoch means that your data has gone from feed forward, done a error calculation, right? And then done a back propagation. That is called as one iteration or one epoch. Okay. Understand now, what is one epoch? One epoch is that when your data completely did a feed forward, done the error calculation, and then based on that error calculation, you have optimized your weights. That is called as one epoch. So what is going to happen now, my friends? You will notice that when you are drawing a graph, when you're plotting a graph between, let's say, your epoch versus error, right? You will see this kind of a point, right? Your error goes down and then suddenly it increases. This is the point where your model should have converged and gone over here. This is the point where you have missed the valley point and the graph has gone up. Through these kinds of graphs, my friend, we will anticipate the value of learning rate. That should we decrease it more? It might sometimes happen that you might have taken a very slow learning rate. Now, very low learning rate also have disadvantages, correct? Because with very low learning rate, your converging speed will be very slow, right? Slowly, your error will come down. Let's say, make you 3 scenarios over here. One, where the learning rate is very high. So the graph will be like this, and it will never converge, and it will go up like this. This is very high LR. The second case is when you have a very low LR. So it is going to take, let's say, centuries for you to go down. It will take you some 1100 epochs to actually reach the minimum error. Right? This is very low LR. And let's say if you take your optimal LR, which will be like this. This is the optimal LR. Do you understand? My friend was asking this question. The disadvantages and advantages of keeping a low and a very high LR, right? Very low LR will take you ages to converge, and as you can see in this gradient sheet also, right? When I took a very small LR over here, what 0. Actually, I didn't pull it up again. Yeah. If you see in this particular graph, right? When I took a very small gradient, you can see over here that I wrote a particular function also, which said that, yeah, see over here with 0.01 with 0.01 epoch 0.01 LR, right? And the epoch gradient could not reach the minimum also, right? With that number of epochs, right? And then I had to increase the number of epochs, and you can see now it is like this goes very small, like ultra dead, right? But if I keep it 0.05 and if I give 30 iterations, see it reaches here in 30 iterations. But here with 0.01, I had to take 100 iterations, 3 times more. Correct? Does it make sense now? I think this is more intuitive, right? When you can see this thing, very good, very good. And you can see in this particular graph also, see now, in this particular graph, the model was trying to, let's say it was going over here, it was stuck, then it actually went down. It went down, but then it went back again. Which point do you think is more optimal for it? This point called P1 or P2, or this point called P2, which is more useful for you? And the graph is between the weights and the error, not P1, right? P2, because P2 is much, it is delivering lesser error, correct? So that's the whole point, right? And you can see now if there is no, let's say, optimal weight over there, you can see now it skips it. But if I give it a 0.01 learning rate, see now how quietly it goes down and then goes in there. P1 is local minima, yes. Is there any chance we may miss P2 and by picking P1? Obviously, see, this is what happened, right? In this particular case, the gradient settled at P1, which is not the optimal case. And I had to now lower the learning rate over here, and now this settles over in this particular part. Gradient is what? Gradient is the derivation of error with respect to weight. And every time the weight is changing, right, the dE by dW will also change. I'm sorry, it is. The dE by dW will also change, right? Biases also have a same impact, right? We also optimize biases also. But see, again, right, I mean, weights are the main persons who are doing this thing. They are the one who have a multiplicative effect with the input. Biases are just additive, so they optimize themselves very quickly, and weights are the one who are the bigger problem for us, right? If we choose P1 instead of P2, what will happen? You will have a much higher error as compared to somebody who chooses P2, right? So your model will not be as accurate where the error is P1. One of my friends is asking that, Shivam, what is going to happen if we have P1 and P2? If I choose P2 as my valley point, and if, let's say, my model is stuck over there, then obviously your model will, let's say, have lesser accuracy as compared to mine, right? Because there is much more optimization. There's still some growth potential over there to minimize the error, correct? So if, let's say, I made a model where I chose P2, my accuracy will be a little slightly higher as compared to yours. How to choose learning rate? As I told you, my friend, it is a hyper parameter. But do not worry, I will I will teach you in detail about that, why learning rate is later going to become a problem for you, and you will choose an optimizer where learning rate should not be applied. I will talk about it. Don't worry. It may happen neuron may not fire. In such case, learning will stop. Neuron will not fire. It may happen neuron would not fire in such case. Neuron will always see what is the job of neuron. The neuron's job is very simple. It has to give its answer, right? Neuron's job is nothing but to give answers, right? Let me go back. See, neurons are nothing. Neurons are nothing but, let's say, the answer kept, right? Do you all understand, right? The main game is played by weights over here. Neurons are nothing but just, let's say, a placeholder where they are saving whatever the weights are multiplying with them. Do you all agree? These red colored neurons are nothing but, let's say, a placeholder where they are saving this thing where it says that x1w1 plus x2w2 plus bias. Weights are the major people who are playing the role in defining even the neurons. So you will need to make sure that how you're optimizing your learning rate. How will we know? You will always do experiments, right? You will take your data and you will run like how I did, right? In this particular sheet, like how I did. I took multiple learning rates, I plotted them, and then I came to know, is this a luck? No, correct? Let's now talk about the next learning. So all of you understand, right? Learning rate is nothing but, let's say, that our formula for updating the weight has now changed a little bit. It now says that W is equal to W minus alpha into dE by dW. Do you all understand that W is now not W minus dE by dW? W is W minus alpha into dE by dW, where alpha is a constant term that you can take and it is always less than 1, right? So that it can de-accelerate the value of dE by dW. Now, let me tell you a very simple thing. In machine learning, we have to figure out the features. Do you all understand? Right? We have to figure out the features from the data. We have to figure out that which features are important, which are not important. How do we make polynomial relationship between the data? How do you find linear relationship with data and all these things? Correct? In machine learning, you are the one, the data scientist is the one who is responsible for generating or extracting the features. Correct? Very good. Now, the moment humans come into picture, they have a problem. And please listen to me very carefully. I'm going to say a term over here. Please listen, right? Humans have a problem. What problem? Humans have a problem that they cannot interpret or they cannot visualize something above 3D. We as human can only understand length, right? It means the height, width, and the depth. We cannot understand 4 dimension, 5 dimension, forget about 50 or 100 dimension. Do you all agree? Right? That is why humans love something called as dimensionality reduction, and they want to bring everything into the scope of dimensionality, right? Everything into the scope of 3D.
Let's have a quick quiz question, guys. And the question is, what is the primary purpose of neural network in AI? And your options are to simulate human neural activity, or to process and analyze visual data, or to enable machines to reason and make decisions, or to learn and extract patterns from large data sets. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Correct? Okay. Now give me a second. I will show you a image. And then you have to tell me. Give me 1 second, right? Give me just 1 second. 1 second, right? 1 second. I have a very important image over here that I want to show you. Okay. Humans are smart? No, definitely they are smart. I'm not declining anything, right? I am one of the Homo sapiens, and I'm very fortunate about it. But I'm telling you that why machine learning and deep learning have a different aspect and different thinking, right? Okay, let me. I wanted to show you this image. Give me 1 second. Okay. Very good. So what I have done is, my friends, for you guys, first of all is learning rate. That's the first thing that we understood. And then we said what? We said W is equal to W minus alpha into dE by dW. Correct? This is one thing that we learn, and now we are learning about something called as dimensionality. Very good. Now I will now load a picture over here, and I just loaded a picture over here. Hope you all can see it. Right? I'll just zoom it out. Okay. So this is a data in front of you, right? This is two dots. Let me tell you, there are two types of categories over here. This is called as red dots. This is called as red dots. This is one of the categories called category A. Let's say red dot category A. And the other one is category, this is called as blue. This is the triangle, right? And this is category B. I am asking you a very simple question, that please provide a linearly separable solution over here. Should I repeat my question? There are two categories over here. One called category A, which is red dots. One category is called category B, which is blue triangles. My question to you is, please provide a linear solution which can separate this data. Okay, I will give you 1 minute. Think about it. Think about it. This is the x-axis, this is the y-axis. These are here. These are almost concentric circles. Provide some solution. Straight line. Poly feature need to be extracted using dimensionality reduction. Okay. So this data is already in 2 dimensions. You want it to reduce into 1 dimension. I'll just upload another image over here, and I'll just show you what happened. Image is not loading. No loading. Okay, so this was the first image, and this is the second image. This is the same images, right? What I have done is here over my friend, I added one more dimension to the data. I added one more dimension to the data. And I said that earlier you were watching this data from a top angle view. You were watching it from the top view, correct? And now I introduced the third dimension called as a depth inside it. I added the third dimension depth into it, which is the Z. And you can see now very easily, I can draw a particular hyperplane over here. I can draw a hyperplane over here, and I can say that this is linearly separable. This particular blue board is now separating the data. If you go above, it will give you red dots. And if you go below, it will give you blue triangles. Do you all agree that this is a linearly separable solution? Now, there are two things which come into our mind that Shivam, first of all, that is adding dimensionality to the data gives you better solution. The answer is yes. Adding more dimension to the data opens up more field of view and opens up more spaces to find the decision boundaries. I will repeat my statement again. That adding more dimensions, it can be confusing also. Why? See, for us as humans, if let's say I ask you to make it a 4 dimension, obviously this will be a very problematic thing. But for machines, it is not. Machines, NumPy can, all of you know, right? NumPy cannot just produce 1D, 2D, 3D. It can produce 5, 6, 7, whatever dimension do you want. Correct? Right? Now, please listen over here. Right? This is where machines will take over. No. So the point here is that for machines, it is much more easier to evaluate things. And the more dimensions that you add to the data, right, the more features you're adding over here. Right? The more features you are adding over here. Right? So what I'm saying to you is that I'm saying you 2 things. Please listen, right? What I'm saying is 2 things. The first thing is that if we add more dimensions, we get more clarity about the data, right? I get more, my field of view of cutting the data through a decision boundary becomes much more easier for me. Do you agree with this statement? Right? The second thing that is very important is that now I can linearly separate my data. I can linearly separate my data. Now, all of you are coming from machine learning background, and all of you agree that linearly separable equations are always better as compared to polynomial equations, because in polynomial equations you have a chances of overfitting the data. Do you all agree with the statement? Polynomials are very good. I am not declining the role of polynomial equations or 3-degree, 4-degree equations, but the problem is they are very prone to getting overfitting over there. Correct? Whereas a linear equation is much less prone to much less prone to a overfitting. Correct? One of our friends says output machine learning solution is linear. Very good. So I am asking you two things, that I will always prefer a linear solution, which is fine if I have to make my data into multidimensional. Listen to me now. I am saying that I want my answer to be linear. I want my answer to be linear in nature. But for them, I am okay to compromise my input data, right? I am okay to compromise my input data and make it multidimensional, right? Multi-dimensional. Do you understand these two terms over here? That I want my answers to be baked in the linear format, for which I am okay. I am okay to convert my input data into multi-dimensional data, and sometimes even non-linear format also. I do not care about my input data if I move it non-linear, if I am getting a linear solution to it. In this particular case, the data is a 3D data, correct? Every red dot can be represented, has to be represented by Y, X, and Z level, correct? Do you all agree with my statement? That in this particular graph, I converted the red dot, which was in a 2D format, I've converted into a 3D format. But by that one compromise, my friend, I have got a very simple hyperplane linear situation, correct? Our friend says means first expand to polynomial and then reducing the higher dimension to 2D, maybe PC other method. No, I will never do a dimensionality reduction over here. Didn't we just change the point of view or perspective? Yes, as a geometry point of view, you are correct that you have added a perspective to it. But if you see, right, it's nothing. You just change the field of view, right? Is this also called feature extraction? Very good point, right? So in terms, right, this is what deep learning is doing, right? Deep learning is figuring out more dimensions, right? More features to be extracted in this particular way. I will explain you each and everything. But do you understand my main concept over here? I told you 3-4 concepts. The first one is that in machine learning, you learn about reducing the dimensionality. Why? Because humans are not capable of viewing something that is 4D or 5D, correct? Because in machine learning, we have to do our feature extraction of our own, correct? So we cannot see a multidimensional data. We cannot visualize or let's say interpret multidimensional data. But here in deep learning, because this has to be done by our gradients, this has to be optimized by our gradients. I am saying to you that let them do it multidimensional. I don't care. I as a human don't care. Let them do it multidimensional way. I don't care. The only thing is I want a linearly separable answer, right? My answer should be simple, right? I don't care about what you're converting this input into 3D, 4D, 5D, whatever you want to do it. And see, we are working with images. Images are already 3D. A static image is already 3D in nature. Do you all understand? So what we're doing over here is we are doing simply two things. One, that the input will be now into multidimensional, or simply I can say it has now become non-linear in nature. And this particular solution is going to be linear. So the first question that I think most of you might be thinking, how will I increase dimensionality? How do I increase this dimension? Where does this z-axis come from? Right? Correct? That's the first thing that is coming into your mind. That how will I automatically bring this third dimension into my data? How do I, Shivam, very good, you just randomly said that, introduce dimensionality, or let's say introduce non-linearity. How do I bring it? I don't know. Correct? So to answer your question, one of your friend is already there, and his name is activation function. Activation functions are your friends. Activation function says that, listen to me now. Let's go back to our original OG image. Here it is, the OG image, right? So, so your, give me 1 second, right? I'll just add some space over here. Okay. So this is our image over here. And now what this particular activation function says to you, activation function says that, see, listen, there are two problems. The second problem is, there's one more problem. That what if this random number W becomes very high, right? One of the random where W becomes very, very, very high. So what is going to happen? This neuron will yield a very high value, correct? Let me take an example. Let's take an example that this particular one, let's say this H1, that let's say this H1, this is H1, this is H2, and this is H3, correct? Let's say the weight over here, this weight W1 becomes supremely high, right? Some 10 to the power 27 something number, right? So obviously this H will also become very high. Why? Because H is what? H is nothing but a product, a sum of product between the weights and the weights and the input, correct? If I increase that random W, the H will also increase. Now what is this O1? This O1 is also nothing. This O1 is also nothing. This O1 is nothing but, let's say, some H1 multiplied by a weight called, let's say, H1 1, and then this multiplied H2 multiplied, let's say, by weight 2. I'm just randomly writing the number, don't quote me. And then this H3 multiplied by W33, and then some bias over here. Do you all agree? So let's say if this H1 value is also very high, this O value will also become very high, right? And this O, this particular O will always be heavier than this O2 over here, right? So we want somebody to normalize these values. We want somebody that this H1, H2, H3 and should be in the same range. And I think this is not a very new or alien concept to you. All of you have done this in your machine learning, also called as scaling, right? Right? Scaling. All of you have done this thing. All of you, before sending the data to machine learning, all of you have done one or the other kind of a normalization or scaling. Do I need to tell you what is standard scalar, min-max scalar? What is min-max scalar? 0 to 1. Okay. Min-max scalar is x minus x minimum. X minus x minimum divide by x max by x min. See, I am saying to you, don't memorize the formulas, but at least to run the concept also, you should know these things, right? X minus x min divided by x max minus x min. What is standard scalar? X minus STD is Z score. Standard scalar is Z score. Sorry, x minus mean, right? Or x minus x cap. X cap is also known as the mean divided by the standard deviation. So these are the just two small simple normalizations that all of you might have done in your machine learning classes. We also have now two problems in us. One is that we want to increase the dimensionality of the data, and second, we also want to make sure that our data which is coming out should be in the range. So we have two problems. Do you all agree with the problems? That the input data has to increase its dimensionality, has to become nonlinear. And the second thing is the output which is coming out, this H1, H2, H3, we need to make sure that this output is actually in a certain range. And this is where your friends AF come into picture. Your friends AF come into picture, which are called as activation functions, right? We'll go to the activation functions now. There are a family of activation functions over here. We'll talk about them one by one. Wikipedia is the best page that I have ever gone for, right? It has this table format which tells you. Now there are multiple activation functions over here. I will tell you one by one what each of them. Can you please repeat active? No, I have not started activation function. I'm starting now. But I just said two terms over here. That one is that you have to make sure that your input is increase the dimensionality, and the third thing is to make sure that the output of that particular function is bound under the same thing, right? The x1, x2, x3 have to say the answer in the same thing, right? They cannot just randomly say any very big number or a very small number, right? This normalization is inherently taken care by the back propagation. Not. We have to take care of this thing. Okay, so let's talk about one by one these activation functions. First of all, before even I talk about this thing, right, let me tell you where these activation functions are applied, right? So activation functions are applied at this particular point, where whenever this is outputting an answer, we will bind this particular function into a activation function, right? So now your affine function, your h1 is nothing but, let's say, it has to go through a activation function. Whatever your x1 w1 and x2 w2 is saying, it has to go through the activation function. This thing has to go through activation function. Now activation functions are of multiple types and natures, right? As you can see over here, the first one is identity activation function. Identity activation function is nothing but, let's say, a very simple thing which says that whatever comes in, the same thing goes out. It does nothing. So it is doing nothing. Neither it is increasing the dimensionality, neither it is bounding your answer, right? Whatever goes in, goes out, comes in, goes out. The second thing is called as binary activation function. Binary activation function says that if you are a number which is, let's say, less than 0, if you are a negative number, let's say input is coming as negative, we will convert you and we will make you 0, right? We will not take any negative number, we will convert you into 0. And if you are a positive number, we will convert you into a 1. We will convert you into a 1. Now, if you notice very carefully, my friends, this function has done both the things for you. It has converted your data into a non-linear data, and it has also bound your output. Correct? Let's talk about one by one. Let's talk about the input first. Do you notice now, this is actually no more a linear function. If you see the graph of a binary function, it will be like this. That, let's say, if you are a negative number, you will become what? 0. And if you're a positive number, you will become what? 1. Do you all agree? Do you think that this is a linear function? Is this a linear function? Please say no. Very good. This is not a linear function. Very good. Also, the output coming out this binary function, the answer will always be bound either being 0 or being 1, right? So can I say that we have controlled the output? Very good. Very good. But these types of the binary activation function has a problem, right? Because it only yields 0 and 1, right? So it's acting like a logic gate for us. Do you all agree? It is not giving me interim answers, right? So my answer h1, h2, h3 are always going to be either 0 or either 1, which might not be the case if I am trying to consider and if I am trying to run a race between them, that who is more important and who is less important, right? So I do not want a black and white picture. I want an answer on a gradient scale. Do you all agree? This is a race that where h1, h2, h3, who will win, right? Based on that, we have to decide. So we cannot just take 0 and 1. We have to find an answer between 0 and 1. And this is where sigmoid function comes in. Sigmoid, or a soft step, a very simple equation which says that whatever is coming in has to go through a exponential power. 1 divided by 1 plus e to the power minus x, right? And the graph is somewhat like this. The graph is somewhat like this, that if you are less than, if you are negative number, sorry, let me draw it again. If you are a negative number, then you will go till 0.5 on x-axis. And if you're a positive number, you will go like this. So this particular thing is 1. This particular point is 1. And this, where it cuts it, this is 0.5. And if you are negative infinite, then you are 0. If you are positive infinite, then you are 1. Please see this graph very carefully. What you are doing is this a graph linear? First of all, say yes or no. Is this graph linear? No. Also, have we bound the output into a range of 0 to 1? Very good. Do you understand? I know a lot of my non-mathematical friends will be scratching their head. They're saying, what is this? Do I need to remember all these things? No. But understand the concept that why these functions came into picture. They are solving two of your problems, right? That if some of the weights, they might go rogue, right? We can control them. We have a measure to control them. Now see, a weight might go as big as it might be. Let's say if a weight says that I am 10 to the power 27, something, something, something. It's fine. I mean, it's fine. The moment I will apply activation function on this particular thing, the value of h1 cannot go beyond 1. Do you all agree? And now I can compare it to other h2 and h3 also. The third type, I think this is the most major one. This is the most major type of activation function you will see. The second type of activation function that you will also notice is this is called as tanh, and this works like this. Again, not a linear function, and it bounds the data between the range of 1 till -1. A very simple equation, e to the power x divided minus e to the power minus x divided by e to the power x plus e to the power minus x. You don't need to remember the equation, but it is fine if you learn it. Right? Now, in this particular one and the sigmoid one, what is the difference? Most of you might be thinking they are the same, right? I mean, logistic and hyperbolic tangent, tanh and sigmoid are both same. The answer is that sigmoid does not give you a negative result. So in some of the problems, you might want your gradient to flow in the negative also, right? You might want your answers to flow in negative also. Whereas tanh says that go, you're free. If you want -1, I'll give you -1 also. And the fourth one is ReLU. Now, ReLU is a very interesting and a very simple activation function. It says that, see, if you are negative, I don't care about you. If you are negative, go, you are 0. And if you are a positive, I will let you go as it is. I will let you go as it is. I will not stop you. Go as and when you want to go. Now, first of all, is this a linear function? Is this a linear line, right? It's a linear line, correct? This red line is a linear line, correct? No, this is not linear. Any line will be linear if it is a straight line. Do you see this as a straight line? No, this has a bend at 0, right? It has a bend at 0. This is not a linear line. Please remember, ReLU is a non-linear activation function, right? The only thing which it does not do is, the only thing which ReLU does not do is that it does not bound the upper cap. It has no upper cap that where can we go, where we have to stop. So ReLU are actually majorly used in images, and you will notice that whatever functions we will make, right, we will use ReLU because we are dealing with images. So negative answers we do not want, and we will be working with positive gradients only. So we will be using ReLU over there. One of my friends was asking what to use, what not to use. Don't worry. We generally use ReLU in our cases. But again, sigmoid softmax may have their own use cases. Okay. So let's now do one thing which I think might be, you might be interested in this thing is that is actually, let's change not it to, let's call it as NN from scratch, right? We are going to make our own neural network from scratch, right? Now, please, all of you, I want your attention over here. Let's say that there is a equation, right? There is a equation. Now, what we are going to do is, my friend, we are going to build our first neural network on whatever we have learned in it, right? Whatever the 2-3 concepts that we have learned, we want to build an answer for it, right? So the first equation is what? The first equation is y is equal to, let's say, 3x1 plus 4x2. Let's say this is a particular equation, right? Now, for this particular equation, can somebody tell me if I take a x1 and x1 as, let's say, 3 and x2 as, let's say, 2, what will be y? Y will be what? 3 times 3 plus 4 times 2, 15 plus 2, 17, correct? Now, can I say this thing that for any deep learning problem or even for say machine learning problem, this is how the data is organized, that they give you the input and they tell you what is the output going to look like. Please find a relationship between input and output. Am I correct? Is this the correct thinking? I'll repeat again. In any machine learning problem or deep learning problem, you are given the data like this, that there are two inputs called x1, x2, and there is their correct answer called y, which is 17. And we have to figure out a relationship between input and output. Correct? Right? We have to figure out the answer between them. Now that is what exactly we are going to do now. Right? So let's now quickly start. What does our neural network say? Let's say if we want to make a single cell, let's say neuron, what will we say? That let's say there is this one neuron called input, let's say x1, and this another input called as x2, and we will make a output called as y predicted. Now what will be the equation of y predicted, my friends? Can somebody please tell me? I will import matplotlib also. Matplotlib.py plot as PLT. Can somebody tell me what is the equation of yp as of today? Yp should be x1. First of all, let's declare x1, x2, x3. We have not declared. Let's declare x1 as 3, x2 as 2, and y as 17. Correct? Is this all correct? And instead of y, I will call it as ya. Ya is nothing but y actual. Right? Okay. So see now, can I say that my y predicted is nothing but, let's say, x1 multiplied by some w1, which I don't know, and x2 multiplied by something called as y2, which w2, which I don't know. Correct? Now, what is w1 and w2? What is w1 and w2? Random numbers. Very good. So what I'm going to do over here is I am going to import some random numbers. I am going to say np.random.randint, and I'm going to say give me some random numbers between 1 till 10 and give me only one number. Similarly for w2 also, I will say np.random.randint, give me any random number between 1 till 10 and w2, sorry, and then give me one number. All of you agree to this point? It is going to give me an array, so I want a number. I will say this thing, right? And I can show you they are totally random. I am not controlling this number. Do you all agree? I have taken them random over here. Now, can I say this thing that WP is nothing but x1 into w1 plus x2 into w2? As of today, I am not considering any bias over here, and we will not use activation function also as of today, right? Because to keep it simple, and also because our relationship is linear over here. We know this thing, right? So we'll not take very simple things. What if we have no y actual? See, okay. Is it possible that you are doing a machine learning, let's say supervised learning thing, and you don't have YA? Is it possible that you are using a supervised machine learning problem and you do not have the Y labels with you? Is it possible? No, right? For every supervised learning, you will have a Y actual with you. So see now, what I'm doing over here, I am doing a feed forward neural network. Can I say this thing? This is feed forward neural network. This is feed forward space. And you can see over here, your YP is what? Your YP is coming out to be 22. What is the next step that we do after feed forward neural network? Error calculation. Very good. Error calculation. So what I'm going to do is, my friend, I am going to say error. Error is what? Can I say error y predicted minus y actual to the power 2? Correct? This is what an error is. Error is nothing but, let's say, the square of yp minus ya, right? I will run this thing and you will notice that the error is over here, right? But can I also say that error is nothing but, let's say, x1 into w1 plus x2 into w2 minus ya? Can I also say this thing to the power 2? Now, who is responsible out of these 1, 2, 3, 4, 5 variables in this particular, let's say, equation, right? How many do you think are responsible for the error? X1, X2, and YA are constant and they are the data set. They cannot be wrong. So who is wrong? W1 and W2. So I should calculate the gradient with respect to what? dE by dW1 and dE by dW2. Am I right? These are the two people who are responsible for the error, W1 and W2, and I need to calculate the error corresponding to them. These are the people who can help me to reduce my error. Now, if you can, somebody can quickly do the differentiation, and we did it last time in last session also, but if somebody can do it again for me, dE by dW1 will be what? dE by dW1 will be 2 times yp minus ya. First of all, you solve it for the power. You solve for the power. The power here is 2. And then you solve it inside, right? So yp minus ya, and then when you go inside, you will say x1, and then everything else is what? Similarly, when you do the same thing for dE by dW2, if I do this thing over here, this thing will be what? 2 times WP minus WA. Sorry, not W, I'm saying Y. YP minus YA into X2. Very good. Can I say the same thing over here? To my non-mathematical friends, my friends, please do not worry. Please do not worry. I will show you that how you can do this in Keras or let's say in TensorFlow with just one line of code. This is just to tell you that what is happening under the hoods. So can I say now like this, that YP minus YA into X1, and similarly the 2 into YP minus YA into X2, correct? If I show you dE by dW1 and this is dE by dW2, these are the two values. Now we will do back propagation. I think we have actually started the back propagation over here. What will we do next? If we have figured out the gradients, what will we do next? We will update the weights. Very good. We will say what? The W is equal to W1. W1 is equal to W1 minus dE by dW1, correct? And W2 is what? W2 is W2 minus dE by dW2, correct? And you can see over here that now the value of W1 and W2 have changed. Earlier they were 2 and 8, and now they have reduced to minus 22 and minus 12. 28 and minus, right? But I need to repeat this whole thing again and again and again and again, right? See, one iteration is not enough. One feed forward, error calculation, and one back propagation is called as one epoch. So one epoch is not going to help us. We have to run multiple iterations or multiple epochs, right? So what I'm going to do is, my friend, I am going to rewrite this whole thing, and this time I'm going to rewrite this thing into a loop format, right? So that it can run for multiple times. Now see over here, I want all of your attention over here. I'm going to again, let's say, define the functions quickly. X1 was what? X1 was by default 3, and X2 was what? X2 was 2, right? YA was 17, right? And W1 was np.random.randint, and 0 till 10, and I want one number. And W2 is what? np.random.randint 0 till 10, 1, and I want the first number out of here, right? So I've declared all my variables, and now I'm going to say that, hey, give me, I'm going to run a for loop. I'm going to say for epoch in range. Let's say I'm going to run it for 20 times, right? Y predicted will be what? Y predicted will be X1 into W1 plus X2 into W2, right? And then you will notice that what is error? You will find error over here. Error is what? ERROR is y underscore p minus y underscore a and to the power 2, right? And what is the value of dE by dW1? We just calculated 2 times yp minus ya to the power, sorry, multiplied by x1. And similarly, dE by dW2 is nothing but 2 times yp minus ya into x2. Correct? Do you all agree? Simple thing that I've written. Now we will do BP, back propagation. That W1, please change W1 to W1 minus dE by dW1 and change W2 to W2 minus WE W21. Correct? Now what is going to happen now? See, this is running a for loop, right? This is running a for loop over here. This is running a for loop over here. It does a feed forward, a error calculation, a back propagation, and this for loop will again start. But this time the values of W1 and W2 will change. Correct? So let's do one thing. Let's store all these into a list also. Correct? Let's prepare a W1 underscore list. Let's prepare a W2 underscore list. Let's calculate a error list, right? And also let's calculate a y predicted list, right? Because this is the most important thing. We need to make sure that y predicted is equal to yp. Okay, right? And I am going to run this thing. Similarly, w2 underscore list dot append w2, right? Actually, let me write down this at the starting of the sheet so that all the things are recorded. I will say y pred underscore list is equal to, dot append y pred. Correct? And I will similarly, I will also say this is not y, this is yp. Okay. And similarly, I will also take my error list dot append and I will append my error inside it. Correct? And this is also not y, this is yp. Correct? I've done a very simple thing over here. This is not bp, this is b. Correct? Okay. Now we are going to, very good. Thank you. Thank you. Thank you. Any other issue? You are saying, can we print this formula? Actually, we are saving this into YP list, right? Okay. See, the moment we run this thing, it gives me a error. Long scalars. Okay. See what has happened over here. The model has already started us giving some errors. Now, what is the error? The error says that, see, that your W1 list, if I show you, right, it has become very, 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 very big. If I show you your W2 underscore list, this has become very big. It means that your speed, your car of the speed is not controlled. Your car is going at a very, very, very large direction. So what should we do now? There was one of our friends, remember? His name was learning rate, a very intelligent guy. His name was learning rate. Let's make learning rate 0.01. And what we have to do, we have to just say that now learning rate will be multiplied to you. Right? That's it. A small change. Nothing else. Just a small change that we have done over here. And this is exactly what we are saying. Correct? And if we see now, it says LR not defined. First of all, so I have to run this thing. And if I run this now, you will notice that your weights are almost in the range.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Artificial neuron. What happens to an artificial neuron? the artificial neuron is essentially this. These are basically your dendrites, your input layers. If you see, there are some inputs which are coming into this particular node. Think of this as a neuron. And what happens is there is an input coming in, lot of inputs which are coming in. There's some kind of an aggregation that happens here, some kind of computation that happens here, and there is an output. There is some kind of a function that is applied and there is an output generated. Okay, there are inputs, there is some aggregation, and there's an output. This whole thing is basically one of this purple these purple circles that you see here. There are inputs, there is a computation, and there's an output. Does the hidden layer contain ML algorithm for computations? No, the hidden layer doesn't contain a machine learning algorithm. The hidden layer basically contains a small mathematical function like a summation, something as simple as summing up values. Okay, so let me give you a small insight into what do I exactly mean by a hidden layer. So here we go. In your introduction to one of your first few deep learning models, or let's say your first perceptron model, we call it as a perceptron model, but we'll learn more about it. So let's take, for example, a traditional machine learning problem, right? So let's say you're trying to predict sales based on two features, x1 and x2. So you're essentially trying to predict sales. So you're saying sales is equal to some function of x1 comma x2. So if you apply a linear regression model on top of this, how would this look like? This would look like sales is equal to some 10 times x1 plus 5 times x2 plus 3, something like this. All of us are okay with this? Yes, this is linear regression. Simple y is equal to mx plus c. Yeah, nothing really complex. Now carefully look at this. So there will be numerous points over here, 1, 2, 3, 4. Let's say they have 100 data points, and I'm going to pass these 100 data points, and I'm going to learn this equation from that complete thing. Okay, now what we're going to do is I'm going to simply transform this problem into a neural network representation. Take a look. So what I have, x1 and x2, right? I have two inputs, x1 and x2, and what I'm doing here, right? I'm passing x1 and x2 into a particular hidden layer. This is my input layer. This is my hidden layer. And then I'm passing this to another output, let's say. This is my output. So for in all fairness, because I'm not doing anything here, instead of actually having multiple, I'm simply going to say this is my hidden and output layer in this case. I don't really have a hidden layer. Let's assume that I don't really have a hidden layer in this particular case. I just have an input layer and an output layer and nothing else. Let's not worry about the hidden layer for now. Hidden layer is basically some more layers in between. So I have x1, x2. Now, this is, let's say, the value over here is, let's say, some kind of a w1, some kind of a weight, w2. So every time I pass a value x1 into it and x2 into it, what I'm saying is that don't just pass the value x1 and x2 as it is, multiply it with w1 and multiply it with w2. Multiply the input value here with x1, multiply the input value here with the value input x2 with w2, and then pass it to my output layer. This is, let's say, my output layer. So what will be the value here, anyone? If let's say I have a summation symbol over here, anyone, what will be the value here, anyone? This will be x1 times w1 plus x2 times w2, right? Because I have x1 coming in from here and x2 coming in from here, and this is nothing but my weight or my coefficient. Instead of w1 w2, let's say instead of w1 w2 over here, what would happen? I would have, let's say, 10, and let's say if I have 5. So this whole thing would then basically look like, this whole thing essentially is going to look like 10 times x1 plus 5 times x2. And if I, let's say, have a bias term over here, another bias term, ignore the 3 for the moment. Let's not worry too much about the 3 for now. So now my output, my sales, is equal to 10 times x1 plus 5 times x2, which is exactly the same as my linear regression model. Does that make sense, everyone? So my linear regression, I've essentially converted my linear regression into a neural network type representation. This is not fully a neural network. Almost there. We're almost there. We'll get there as we go along. But in a lot of ways, if you think of it, my neural network is not very different from a linear regression problem. This is referred to as a perceptron, or a neural network with no hidden layers is what is simply called as a perceptron. Or a perceptron is also nothing but your linear regression model in a lot of ways. Now, so now the question is, in the case of your linear regression, what were we trying to do? Because at the end of the day, I would want to make a prediction. I would want to predict my sales. But to predict my sales, I need a linear regression equation. So when I require a linear regression equation, so this whole thing is essentially going to look like this. So my historical data would be, let's say I have money spent on ad, right? And number of stores. And my final, let's say, is I want to predict sales. I want to predict the sales of my business as a function of ads and the number of stores. So let's say across various years, year 1, 2, 3, 4, across different years, I've captured, let's say, the money spent on ads, money spent on the amount or the number of stores that I have, and the sales. And now I've come up with this equation. So to come up with an equation that will predict sales, I've applied linear regression, and my sales would look like sales is equal to some W times beta naught times some beta naught, or rather, just for simplicity's sake, some beta 1 times, let's say, ads, money spent on ads, plus beta 2 times number of stores, plus a constant. Let's not worry about the constant too much for now, right? So plus some constant. Let's not worry too much about the constant. For now, let's basically say that this is the equation that we would want to come up with. So when you solve for a linear regression problem, what are we trying to compute? When you apply a linear regression technique, what are we trying to compute? We are trying to compute beta 1 and beta 2, because beta 1 and beta 2, from my historical data, I'm essentially trying to compute my beta 1 and beta 2, because if I compute my beta 1 and beta 2, if I know what my beta 1 and beta 2, I'm going to say sales is equal to 10 times money spent on ads plus 5 times number of stores. So on any given day, if I know the value of ads and the number of stores, I can always compute my sales. Always understood? Sorry, are we all on the same page here? Do we all agree with the fact that we are trying to compute beta 1 and beta 2 with a linear regression problem? Now that we want to compute beta 1 and beta 2, we just go about our technique, right? We apply whatever kind of techniques that are required, and then we come up with the beta 1 and beta 2 approach. Exactly the same way, even in the case of your neural networks, we are trying to achieve the same thing. So I have my inputs. This is x1, or rather in this particular case, money spent on ads and number of stores. And here I'm basically performing a summation. This is beta 1 and this is beta 2. I want to compute the right values of beta 1 and beta 2 in such a way that whenever I multiply the value of ads and the number of stores, I get the value of sales. I want to identify what that value of beta 1 and beta 2 should be in such a way that whenever I perform that kind of a computation, I get the right value of sales. Does that make sense, everyone? So these values of beta naught and beta 2, they are called as weights. In the case of linear regression, we call them as coefficients. In the context of perceptrons, we call these as weights. This is basically how one can actually solve a simple linear regression problem with the help of a neural network. But now the question is, how do I actually solve for beta 1 and beta 2? How do I get the right values of beta 1 and beta 2? I need to find out the right values of beta 1 and beta 2 such that my sales are the best. I can actually come up with the right values of sales. Whenever I pass the value of ads and number of stores, I need to find the correct values of beta 1 and beta 2 such that this summation, whenever I do, which is beta 1 times ads plus beta 2 times number of stores, will always give me the exact sales. So I need to know what that exact value of beta 1 and beta 2 should be. So I need to learn beta 1 and beta 2. How will I learn beta 1 and beta 2? Just like how we've kind of learned beta 1 and beta 2 in the case of linear regression, similarly, we'll have to learn beta 1 and beta 2. So for all you know, the linear regression algorithm that you folks have learned all these years or all these months is in a lot of ways the simplest implementations of a neural network model. Okay, now let's learn how does a neural network model actually learn from here. I mean, this is great, this is all wonderful, but how do you actually solve for beta 1 and beta 2 in the context of neural networks? How are you going to actually find the values of beta 1 and beta 2? We'll learn that in the next couple of in probably the next couple of classes. We're going to learn how beta 1 and beta 2 is going to work. Do we use neural networks to identify the values of beta 1 and beta 2? So we are going to use certain techniques within deep learning neural networks to find out beta 1 and beta 2. This is a neural network, Puneet, but it's just that this neural network is not very large. It's a very small, simple neural network. Now, let's go back here. In a lot of, see, if you see a perceptron is a linear model. Now, in a lot of ways, I can actually, what we can actually do here is, instead of solving for a linear regression problem, I can also solve for a classification problem, same as the one that I mentioned earlier. So let's say I want to predict if somebody is going to churn or not. Churn prediction, which is basically somebody is going to quit or not. And let's say based on the bill amount and I don't know, number of calls, I want to predict if somebody is going to churn out or not in a telecom company based on the amount of bill and the number of calls that they make. And this is basically a 0 or 1 prediction. 0 means the person won't churn, 1 means the person is going to churn. Now, yeah, cool. Okay. So now coming back to the bill amount and the number of calls, let's say I historically capture all possible information. So bill is let's say 200 rupees or dollars, whatever, and the number of calls is let's say 50 calls, and the person hasn't churned. Similarly, somebody's bill amount is let's say 1500, and then the number of calls is let's say 100, and then let's say the person has actually churned, and whatnot, and all of that information basically. Okay, so now what we're going to do is, just like how we've trained a linear regression problem, we can actually train a classification problem. How can you train a classification problem? Same, two input one input layer with two nodes, this one for bill amount and this one for number of calls. And what's going to happen is these two are then going to come here, and because it's going to come here, remember, this time I want a prediction that is going to be between 0 and 1. If I want this prediction to be between 0 and 1, what do I need to do? And I just cannot do a, this is going to be W1 and W2, just weights, but it just cannot be that, because I want the prediction to be between 0 and 1. What do I need to apply over here? Anyone? I want my prediction to be a probability which is true, not the probability threshold. So Shira, I have to perform something, not scaling, something like scaling. No, not the log transform, not the log transform, Tom. Guys, come on, you all know this. No, you have to apply a simple sigmoid transformation. Sigmoid, exactly. You'll have to perform a sigmoid. 1 by 1 plus e to the power of minus. Logit, exactly, Diksha. You'll have to apply a logit transformation. Because at the end of the day, I'm solving a classification problem, not a regression problem. So if I want a classification problem, I want my output to be squashed between 0 and 1. So all that I'm going to do is just to kind of give that out as an output. My output will simply be, instead of just a summation, I'm going to apply a sigmoid transformation over here. So my output will then be 1 by 1 plus e to the power of minus W1 times bill amount plus W2 times number of calls. That's essentially what my output is going to be. Yeah. So what I've done here is, instead of just adding, in the case of a linear regression, what I just did a summation. But in the case, because I want to solve a classification problem, I just don't do a summation. I actually applied a sigmoid transformation. So I just didn't, if I were to simply do a linear regression, I would have just done stuff inside. But because I want a classification, I've essentially applied a sigmoid transformation over here. So the sigmoid transformation would make my prediction to look like that, or make my outputs to look like that. It'll always give me the values between 0 and 1. And Hina, absolutely right. This is nothing but a logistic regression, right? So this is exactly like a logistic regression. If you observe, there is no difference. So a single layer perceptron or a neural network with one single layer is no different from A logistic regression with a sigmoid transformation is no different from a logistic regression. What is going to make this different and complex is when the hidden layers come in. So when the hidden layers come in, this will look very different. The same sigmoid instead of directly performing sigmoid, what I'm going to do is I'm going to have two layers. I might have something like this. So this is going to be bill amount.
Let's have a quick quiz question, guys. And the question is, which of the following is an example of unsupervised learning? And your options are training a spam filter to classify emails as spam or not, or teaching a computer to play chess by analyzing historical games, or segmenting customers into different groups based on their preferences, or predicting housing prices based on historical sales data. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
And this is going to be number of calls. So I'm going to pass these values into everywhere. So now think about it. So now what's going to happen? This node, the value in this particular node is going to be a linear summation of values that is coming from this node and something that is coming from this particular node. Similarly, for this one, the value that comes from here and here, so on and so forth. So things get a little complicated when you have a hidden layer. But when you don't have a hidden layer, we'll come to hidden layers in more detail later on. But when you don't have a hidden layer, this is as simple as a linear regression or a logistic regression. I hope that makes sense. The reason it's called as a hidden layer is because the hidden layers are not exposed outside. You have an input layer and an output layer. The input layers are exposed outside and the output layer is exposed outside. The hidden layers are basically squashed in between. That's the reason we call it hidden layers, because those layers are not exposed anywhere else and nothing else can impact them. Secondly, I think the more relevant question there would be, why do we need a hidden layer? I mean, if I am able to solve a classification problem and a regression problem just like this, then why do I actually need a hidden layer is the question. What hidden layers basically do is hidden layers, if you don't have a hidden layer, let me just go back to that PowerPoint. So if you look at this particular image, right, if you did not have the hidden layers actually help in capturing more and more intricate patterns from our data, more complex patterns from our data. If you do not have hidden layers, and if you just had like one layer, then you wouldn't be able to capture more complex patterns like from here, because these patterns are very generic patterns. If you have more hidden layers, that means more complex patterns can be captured. More complex patterns meaning better predictions. So more hidden layers essentially will help us build more complex algorithms or more complex prediction solutions. But for now, at a high level, at a 10,000 feet level, that's basically an answer. Through neural networks, we can do everything. Why don't we use neural networks for everything? Great. Don't we use neural networks for everything? Because we don't know. Neural networks are not very easy to train. Once trained, neural networks are super powerful, but neural networks are not very easy to train. So the manual labor that it takes to train a neural network is very, very high, because you will have to identify what should be the right size of the network, how many hidden layers should be there, and all of that. That makes neural networks extremely complex to train, extremely difficult to train. So that's one of the reasons why it's not easy. Why we don't use neural networks for everything. Okay, we only use neural networks for complex problems where you can really spend some time and you really want good amount of accuracy. That's where you actually use neural networks. Else there's no point in using neural networks, especially if you're getting good amount of accuracies with traditional algorithms. Then there's no reason for you to go to neural networks, because neural networks require a lot of manual labor. Cool. Okay, So going back here again, let's go back here. Let's actually try to learn from a small example, and then we can. So if, for example, let's say you have a small network neuron, and let's say you're getting inputs from two sources, and let's say the weight over here is 0.5 and the weight over here is 1 point is, let's say, 1, and this is x1, this is x2, and let's say you have a for different values of x1 and x2. If you observe for different values of x1 and x2, so for example you have x1 and x2 over here, and then let's say you pass x1 and x2 through this particular network, we can quickly compute what will be the output from here. So whatever the output is, you can actually compute the output. Can someone tell what will be the output here for each of these values? And let's say this is a summation, just a simple summation. So the value that is going to come out from here is, let's say, 0.5 times x1 plus 1 time x2. So for the first value, the first one is 7, absolutely right, because it's going to be 0.5 times 10 plus 1 times 2. 0.5 into 10 plus 1 into 2, which is going to be 7. What about the second one? The second one is also going to be 7, because it's going to be 8 times 0.5, which is 4, and 3 plus 1 is 3. So 4 plus 3 is 7. And the last but not the least is going to be 17.5. Spot on. Perfect. So 2.5 plus 15, which is going to be 17.5. Brilliant. So right now, what we've been able to achieve is what is referred to as a forward pass. So knowing the weights, what we've been able to do is we've been able to do a forward pass. That means I've basically passed my values of x1 and x2 through the network, and I got the values as an output. I passed my values of x1 and x2 through the network, and I got an output. Great. Now, what would happen if in the case of what would happen if I were actually using the similar network to solve for a to solve for a regression problem? So imagine, go back to the same example that we had a while earlier. I have two inputs, and I have one, let's say, layer over here, and this is a summation. This is, let's say, I'm trying to predict sales. This is y hat prediction, and this is my money spent on ads, and this is, let's say, whatever you call your number of stores that you have. And let's say this is 0.5 and this is 1. Very, very similar. So this is money spent on ads, this is number of stores, and this is, let's say, my sales. This is historical data, guys. This is historical data, right? So what I've done is, over the years, I've gone back and I've captured what is the sales, and what is the money spent on ads, and what is the money spent on number of stores. So let's say this is I have spent 10 units on ads, and let's say I have 15 stores, 5 and 8 and 10 and 12. And let's say my sales historically have been 25, 12, and let's say 15, right? From where did we get these values? We all understand how we got this, because this data is historical data. This data we will already have from the past. Oh, from where did we get these? So right now I'm assuming that these are a value. I don't know what those values are, which is exactly the whole problem. I need to find a way to compute these values. I don't know how these values have come from and where these values have come from. Right now I'm assuming that it is 0.5 and 1, right? But in reality, I will have to compute exactly what these values are meant to be. So let's go through one round of forward pass again. Let's actually come up with some predictions, right? So what will be my predictions? So in this particular case, quickly, what will be my predictions over here? So 10 times 0.5, which is 5, plus 15. 15 plus 5 is 10. sorry, 20 in this particular case. What will be my prediction here for the second one? Anyone? 5 times 0.5 is 2.5, and then plus 8 plus 2.5 is 10.5. What about the third one? 10 times 0.5 is 5, and 12, this is nothing but 17. Brilliant. Now if you observe, this is my actual y, this is my predicted value y. Do you see an error between my actual value and the predicted value? We see an error. So can we compute the error over here? So if I say error y minus y hat, error is nothing but y minus y hat. So this is going to be 5 units, this is going to be 1.5 units, and this is going to be minus 2. Perfect. So this is the actual value, this is the predicted value, and I have my error. So the total error for the 3 data points is how much? The overall error, if let's say, is I can always sum up, or I can square and sum up. Don't just do a direct add, guys. Remember, whenever you're talking about errors, you don't simply add the errors, you do a mean squared error or a root mean squared error. Exactly, you do a mean squared error or you do a root mean squared error, RMSE or MSE. Okay. So you will basically do a square, and then you'll basically add them. You can come up with a basic value, whatever your value is, RMSE. Now, the whole point of doing this is that I need to come up with a model. So basically there is an error in my model. So with the values of 0.5 and 1, I came up with a particular set of predictions which result in some amount of error. But right now, I want a model which results in a 0 error. I want this to be 0. If I want my results to be 0, or if I want my error to be 0, what do I want? I want to make sure that my predictions are correct. If I want my predictions to be correct, what need to be corrected? What needs to be corrected? If my error, if my exactly my weights have to be corrected, my coefficients have to be corrected, spot on. My W or my beta values have to be corrected. So something has to happen to my 0.5 and something needs to change for 1. Something has to happen here and here. What should happen? Should this increase? Should this decrease? What should go up? What should go down? Something has to go up and something has to go down. Now, you and I can break our heads and we can do a hit and trial approach over here and try out probably 100 different combinations before we can come up with 100 or 1000 different combinations and search for it in the dark to find the best possible values for this whole thing. And for all you know, I might never be able to get to 0 error. I might be able to minimize my error, but I might never be able to get to a 0 error at all. Does this make sense, everyone? Yeah? Are we all on the same page here? Cool, good, brilliant, very nice. So I want my error to be 0. If I want my error to be 0, I want my predictions to be correct. If I want my predictions to be correct, that means weights have to be adjusted. But if my weights have to be adjusted, how do I adjust my weights? It might take me an eternity to come up with the right kind of weights. That's exactly where we will have to employ slightly more sophisticated techniques to find the best possible values of these weights. Exactly, Mahesh. That's where we are going to leverage techniques called as back propagation. We will learn about back propagation and gradient descent. We learn about something called as back propagation and gradient descent, where we will learn the approach towards correcting these weights. We will find the best possible way to correct these weights. So what will happen is, for all you know, maybe this might go down a little. This might become 0.8. The moment this becomes 0.8, then I am going to run my whole algorithm again. Then I'm again going to get an error. I will see if the error is large or not. If the error is large, then again I'm going to go back and correct. So there will be a back and forth that will happen. But which weight has to be reduced? Should the 0.5 be reduced, or should a 0.8 be reduced? Should it actually be reduced or should it be increased? All that will be driven by these techniques called as back propagation and gradient descent. That way, with the help of gradient descent and with the help of back propagation, we will know what should be the weights and how much the weights have to be corrected. That way my learning becomes faster. Rather than just searching for these weights in the dark, rather than trying to find the best weights in the dark, I will find a more efficient way to find these weights. Does that make sense, everyone? Are we okay? Wonderful. Now, the larger question is, okay, this is a very simple network right now. There is no complication here, nothing whatsoever. All that we are doing is we're basically solving for a simple neural network, right? We are essentially solving for beta 1 and beta 2, or rather your Ashok, you're absolutely right. We are solving for beta 1 and beta 2. This is beta 1 and this is beta 2. No, at the end of the day we are going to solve for them. So I just assumed a few values here just to kind of give you a sense of how this whole thing works, but in reality I will never assume. I don't know what these values are going to be. We've randomly initiated these values. In reality these values are going to be completely different. Yeah, cool. I would always want to build a model that could give me a least possible error. That means I would always want a model that can predict the sales perfectly. But for me to predict the sales perfectly, or to have a very, very low error, I need to make sure that my predictions are correct. If my predictions have to be correct, one thing that I have to correct is these weights. So the whole process is to learn these weights. The whole idea is to learn these weights. Very, very similar to that of your linear regression problem, right? Even in your linear regression problem, we're learning the coefficients. In what combination of coefficients can I actually get my when I multiply my input features, I'm going to get my output. That's exactly what we're doing here as well. Simplistically speaking, this is a linear regression problem, and this is also a very, very simple perceptron model. But then, of course, more complex neural networks are not going to look this simple. They're going to have much more. They're going to have more complexity involved in them, and we learn what makes neural networks more complex and more sophisticated as we go along. We also told ourselves that in our today's session we're going to learn a little bit more about hidden layers, and why hidden layers are really that useful. We also spoke about how we're going to get introduced slowly to backpropagation and gradient descent in our today's session. Brilliant. So, we all have kind of learned that at the end of the day, a simple network looks something like this. You have two inputs, and these two inputs sort of you can essentially multiply these two inputs. Two inputs in this particular case, it doesn't always have to be two inputs, guys. It can be more than two inputs. It could be 10, 15, 100, how many ever, depends on the number of features you have. We are taking only two inputs for the purpose of this particular example. That's about it. So I have, let's say, x1 and x2. So this is ads, and this is number of stores, and then I'm predicting sales. So technically I'm saying sales is nothing but some function of ads and number of stores. This is essentially what I'm saying. So what I'm simply saying is that somebody can actually predict sales just with the help of ads and the number of stores. So now, when we sort of built our linear regression model, back in the day when you all were learning simple machine learning or straightforward machine learning, you kind of learned that uh, you know a model that basically looks like this: sales is equal to 10 times ads plus 5 times number of stores plus 10. This is basically a simple linear regression model, which is of the form y is equal to beta naught plus beta 1 x1 plus beta 2 x2, where x1, x2, x1 and x2 are your features, beta naught, beta 1, beta 2 are your coefficients, and beta naught is nothing but your intercept. This is what we all have learned back in the day. Similarly, this was called as a linear model, and then we learned something called as a decision tree algorithm. We learned a decision tree algorithm where we said that, hey, look, you know what, this linear regression models can be built using this. Essentially, when you build a linear regression model like this, what you're saying is that if the model basically looks like this, beta naught plus beta 1 times x, then what you're saying is that this is y and this is x. If you have your points like this model is simply trying to basically fit a line. And if this is basically this kind of a model, then in 3 dimensions, you're essentially trying to fit a plane. So this is y, this is x1, this is x2, and this plane that we're basically seeing is nothing but your y is equal to beta naught plus beta 1 times x1 and beta 2 times x2. So these are linear models. they assume that your input features are, or your target variable is linearly dependent on your input features. But when you talk about decision tree algorithms, we suddenly say that, hey, look, okay, decision tree classifiers, the same holds good even for your classification problems as well. Classification problems, like for example, in the case of a logistic regression, all that we are doing is we're basically trying to find a line that can cut through these two data points and classify the x's from o's. This is logistic regression. But in the case of a decision tree classifier, things are a little different. In the case of a decision tree classifier, what we are saying, or a decision tree regressor as well, what we are essentially saying is that, hey, look, your data points might look like this. We're not going to try and fit one single line. Instead, we're going to draw many lines could that could separate my x's from o's. So you essentially draw one line like this, another line like that, and then by doing so, what you've been able to do is you've been able to successfully separate the x's from o's. You tell me, between your decision tree classifier and your linear regression or logistic regression classifiers, linear regression models or logistic regression classifiers, and your decision tree algorithms, which of these is more complex? Is decision tree more complex or your linear models more complex? Okay, I do see majority of y'all saying a decision tree. There are a few who say that the linear models are more complex. Mayank said that the linear models are more complex. The only point that I'd like to make here is that folks who believe that the linear models are more complex, just understand that your linear models only assume a linear relationship between your input variables and input features and your target variable. They say that I can simply explain my target variable just with a single line, right? Irrespective of how my data looks like, I can basically separate my data with a single line, is what your linear models will assume. But decision trees, on the other hand, don't simply build a single line. They actually end up building more complex spaces. Though each line is is linear, at the end of the day, the kind of decision boundaries that your decision trees create are non-linear in nature. When I say non-linear, they're not a single line. They're much more complex. I hope um, that kind of adds some kind of a thought. So think of it, more non-linearity can be captured with the help of a decision tree algorithm than a simple linear or logistic regression algorithm. I hope that that clarity persists in your mind. So as your models become more and more complex, when I say more complex models, what we essentially mean is that your models are able to capture more and more non-linearity within the data. If I want a model to capture, let's say, for example, I have my X's and O's distributed like this in the case of a classification problem, I cannot draw one single line that can separate my X's from O's. I will require a very, very complex boundary to separate my X's from O's. I need something like this. I need something like that to separate my X's from O's. This cannot be achieved by a line. This is a curve. What a decision tree can try and achieve is it can try to approximate that. What a decision tree tries to do is decision tree says, okay, I might not be able to create a line, but what I can do is I can probably try and create many more spaces like these. I'll try and approximate that kind of a space, right? So it'll basically try to create that kind of a space for you. So your decision trees are more complex than your linear regression models or your general linear models. Okay. So when I say more complex, what we are saying is that your decision tree algorithms can capture more non-linear. I hope we're all of the same opinion. Cool. Brilliant. Thank you. Now, once this exists, or once you establish this kind of a thought process, now let's take this one step ahead. Now you tell me, between a decision tree algorithm and a random forest algorithm, which is more complex? Random forest is more complex. Why? Because random forest is again a combination of many such decision tree algorithms. So thereby your random forest algorithm can capture much more non-linearity than a decision tree algorithm. And between a random forest algorithm and a gradient boosting machine algorithm, your gradient boosting algorithms is more complex because it can capture far more non-linearity. The point being that from one model to another model, from linear regression models to decision tree to random forest to boosting models, the reason why we call certain models are more complex or more accurate is because of the ability to capture more and more non-linearity within the data. when there is more complex, when the data is more is sort of entangled between each other, especially with the classification setup. If you have the positive and negative observations entangled within each other, your complex models can actually capture nonlinearity very well. Now, the reason why I've given this background is because whatever we're going to learn right now is to basically try and capture that nonlinearity. Right? When you're solving a very complex classification problem, your neural networks with the hidden layers in between help us get that nonlinearity. The hidden layers in between help us capture that nonlinearity in a much more efficient fashion. Right? So think of this. What we are simply saying is that if I'm able to capture sales as beta naught plus beta 1 times my ads plus beta 2 times my number of stores. This is assuming a simple linear combination. But if, for example, if I don't assume a linear combination, if I don't assume a linear relationship, and if I say that, hey, forget about the linear model, if I want to build a more complex model out of this, one of the ways that you can try and do is, of course, you can use the other random forest models or the other models to build. But what you can also try to do is you can leverage your neural network approach and say, hey, look, instead of just directly assuming a linear combination, this is my sales, this is let's say ads, and this is number of stores. Instead of just assuming this linear combination, I can actually take this one step further. That I can end up building a more complex representation by saying, hey, look, I have my ads and number of stores, but instead of taking a direct linear combination, I'm going to first create a certain kind of a combination in between, right? Similarly over here as well, I'm going to create a certain kind of a combination in between, and then use these features that I generate in between as my possible outcome to predict my output. I'm not going to directly use ads and stores, but instead first compute a linear combination of my ads and stores, extract some other forms of relationships, and then use those relationships to predict my output, which is my sales. By adding this additional layer, what I'm doing is I'm adding an additional layer of complexity. I'm adding an additional layer of complexity. So what I'm doing over here is I'm doing some kind of a feature engineering. In between this layer, what is happening in this layer is I'm taking my ads and I'm taking my store. So take a look at this. Take a look at this. Absolutely, Sushira, spot on. You hit the nail on the head. Adding an additional layer is like performing a PCA. Exactly. So what does a PCA do? Your principal component analysis is like your principal component analysis essentially captures a linear combination of your input features. That's very, very similar to what we are doing over here. I'm taking my input features and I'm computing a linear combination over here. Similarly, I'm taking my input features, I'm computing a linear combination over here. Once I get a linear combination of my features, so this is going to be, if let's say this is beta naught, sorry, beta 1, beta 2, beta 3, and beta 4. This is going to be, what is the value that is going to come in here? It is going to be beta 1 times ads plus beta 3 times stores. Similarly, in this particular node, I'm going to have values like beta 2 times my ads plus beta 4 times my number of stores. So now, instead of just using directly ads and stores to make a prediction, I have now been able to capture another additional set of features over here. I've been able to capture a linear combination of my features, and then I'm using those linear combination to finally predict my outcome. I'm saying my output is not just directly based on ads and stores by default, but they're actually based on a linear combination of my features. Yeah. So that way, my input features are going to be not just my raw features, but actually engineered features of my raw features, a set of engineered features of my raw features. Does that make sense, folks? I hope that adds some kind of understanding. If I have my raw features, I'm building a model with my raw features, and I'm building a model with engineered features. That means I'm extracting more features out of my raw features and then using those as a part of my model. which model do you think will do better? The model with newer features, additional features? That's exactly what we are saying over here. I have a set of raw features, and along with my raw features, let's say I build a simple model. This is just raw features, and then I'm building a model. Here I'm using my raw features, and then I'm enhancing these features, and then building my model. Out of these, which one do you think will be a better model? The second one will of course be a better model, because I'm enhancing my features. I'm not using my features as is. I'm actually doing some kind of a I'm applying some kind of a mathematical function on top of my features, and then using them to generate my predictions. And that's the reason why having this layer in between is really going to help. Does that make sense? Like for example, if I give you, take this for example. If let's say I give you weight of a person, and if I can give you the height of a person, what feature can you engineer out of this? If I give you the weight of a person and height of a person, what feature can you extract out of this? You can generate the BMI of that particular person. And body mass index, exactly. You can essentially generate the body mass index of that particular person. Similarly, if I give you, let's say, the expenditure of a particular person, and if I give you the salary of a particular person, what can you extract out of this? What feature can you generate? You can extract savings of that particular person. The only difference is, right, in the case of savings is a linear combination of salary and expenditure. I can simply do salary minus expenditure and I will get savings. But in the case of BMI is not a straightforward difference of the two. BMI is basically is a non-linear combination. So BMI will require me to do something like weight divided by a height or something like that. I'm not exactly sure about the formula, but something like a weight by height or something like that. I'll have to do a non-linear combination. This is linear because I'm just adding or subtracting. Here I'm dividing multiple features. So this is a non-linear combination. Yeah, that's the basic difference. So don't worry about it too much. The point that I'm trying to drive over here is that when you have raw features, you can build a certain kind of a model. But when you have raw features with additional features, the model that you end up building will be far better than your raw model, than your raw features. What you're what you're trying to do over here is that instead of you manually trying to create these features, instead of you trying to manually figure out, okay, I have expenditure and I have salary, so let me create a salary and salary minus expenditure to create a new feature. What you are doing over here is you're taking the help of some mathematical functions, and you're automatically trying to create those features. You're trying to automatically engineer those features. How are you engineering those features? What you're saying is that, okay, let me take ads and let me take the stores, let me add them in a certain fashion. Similarly over here as well, I'm taking ads and I'm taking stores and I'm adding them in a slightly different fashion over here. So this could basically end up generating a different kind of a set of features. This could end up generating a different set of features for me. Does that make sense? Absolutely. So what I'm doing over here is I'm adding my features in a certain way. That way I'm able to generate a different kind of a relationship between my features. All of us are okay till here? All of us understand why the hidden layer is really helping in this case? Are you able to kind of build that intuition? Nice. Okay. Now the thing about now the thing about this is, okay, why should I only have one layer? Can I have more layers? Why should I only do a linear combination? Can I do other types of combinations? I mean, like, who's stopping me to just do a linear combination of my features? Right? I can actually do much more combination of my input features. I can take my features and then I can do some kind of a division. I can probably, instead of just having one layer, I can have multiple layers. And why do I have only two nodes over here? Can I have like 100 nodes over here? Absolutely, yes. I mean, we can do all of that. And that's essentially what is going to make this problem into a deep learning problem. So when somebody says that, hey, look, I don't want to have a single layer, I want to have like 100 layers in between. And then, hey, look, I don't want to simply apply the linear combination. I want to apply more complex functions over here. And then somebody would say, hey, look, I don't want to have like, I just don't want to have two nodes over here. Instead, I want to have like 100 nodes in each of these. And that is essentially what would make this problem into a much more complex problem. more complex because you have more hidden layers, and more hidden layers means you're extracting more and more interesting features, and the more and more interesting features that you generate, your predictions are going to be more and more complex. So one layer would have one set of one set of functions, the other layer would have another set of functions. You can also try to do at every node, but then imagine if you have like 10 layers, and if you have in each layer, if you have like 100 nodes, applying one function at every node will be very difficult. So the best thing to do is you apply like one set of functions at every layer, so that you kind of simplify it for yourself a little. We can dig into the details as we go along, but I want you to build this intuition of um, why hidden layers really help enhancing the output of the problem. More features means typically more features means better solutioning that you can do. Okay, cool. So just to kind of summarize, what we are now saying is that, hey, look, instead of building a simple straightforward neural network like this, um, for simplicity's sake, I'm going to call it x1 and x2 from now on, guys, so that x1 and x2 are nothing but my variables. And just for simplicity's sake, I'm going to call this w1 and w2, which are nothing but my weight, right? These are features and these are my weights. So the output was, until this particular point, w1 x1 plus w2 x2. But instead of making it so simple, you can also kind of say, hey, look, I don't want to keep this so simple. So I want to kind of add more layers in between. Something like, let's say somebody decides to, let's say, add one layer with 3 hidden nodes, one hidden layer with 3 nodes, and then one output layer. So in each of these, what's going to happen is I'll have inputs flowing in from here and from here. So this is again still x1, x2, w1, w2. So this is w1 x1 plus w2 x2. Similarly, from here to here and from here to here, this is w3, w4. This is w3 x1 plus w4 x2, and similarly from here to here. And then once you have all of this, everything flows from here to here. So this is going to be 5, 6. So this is going to be W7 and W8. So whatever value is going to be in here, that times W7, so the W8, and this is W9, that times W8, and this times W9, that will be your final output. So suddenly, from here to here, what do you see? Here, how many weights did I have to compute? In this case, how many weights did I have to compute? Just 2. I was just trying to solve for 2 weights. But from here to here, what happened to the number of weights? My number of weights just went up from 2 to 9, just by adding one hidden layer with 3 nodes, right? So with just computing a linear regression problem would take us a good amount of time to solve, because in the case of linear regression, you're just solving for X number of weights, depending upon how many features you have. But here, if your number of inputs are going to increase, and if you have good number of hidden layers, can you see how the number of weights go up exponentially? You actually see how the number of weights just increase exponentially, because more and more hidden layers means more and more combinations. More and more combinations means more and more number of weights. And the number of weights that you will end up having to compute will increase exponentially. That's one of the other reasons why computing or actually solving a linear regression or solving a neural network problem is far more complex than solving for a simple perceptron type of a setup. Solving a simple linear regression sort of a problem. This is actually super simple. When you look at this one, this becomes super complex because the number of weights are much higher, and also because the number of the more the number of weights, the number of computations are actually much higher. Now, so we've been able to establish the fact that hidden layers are going to help the model, because more hidden layers means more complexity. But then when we talk about more hidden layers, one of the things that we said was, we don't know how many hidden layers do we have to capture. We don't know that. Secondly, when we talk about uh, when we don't know how many hidden layers we need to put, and we don't know how many nodes should be there in each hidden layers and all of that, it becomes like super complex. So that's one of the reasons why we would want to make sure that we kind of come up with some kind of a heuristic around how many hidden layers should be there and how many nodes should be there and all of that. Generally, there is a heuristic that people have, but then we will come to all of that when we get into further details. The point that I'm trying to drive here is that right now we've just drawn a network over here that you see on your screen, but we don't know if this network is really going to be good enough or not. So just like how you tune your hyperparameters, you might have to tune how many nodes should be here and how many layers should be added. All of that has to be tuned by us. We have to figure out how many layers and how many nodes we need to keep adding as we go along. That's up to us. It depends from case to case. It depends from model to model. It depends from the data to data. So it's case by case. Uh, there is a heuristic around it. There is a kind of a ballpark idea around how people should typically go about designing their architectures, network architectures. But there is nothing written on the stone. There is no mathematical proof to what would work and what would. So we will have to figure it out. There are certain widely used approaches, but then we will learn about those as we go along. Right now, just know that we will need to figure the number of layers out. There is no rule of thumb right now. Just assume that there is no rule of thumb. We will learn about certain heuristics as we go along. Brilliant. Okay, let's come back to this. Now, we need to first learn about how do I compute W1 and W2. We still haven't learned how to compute W1 and W2 yet. If I know how to compute W1 and W2, I can use the similar approach to compute the multiple weights that we saw in a larger network. If we are able to solve a perceptron model, then we can use a similar approach to solve for a larger problem. So the most common approach towards solving for the weights in a linear regression problem is by using the classic ordinary least squares approach. So if you all remember the ordinary least squares approach that you learned, it's the same exact approach. We can just do a quick refresher around it. I'm just going to spend like a few minutes just doing a quick refresher. That way, it'll make it easy for us to work with. So what we are going to do is quickly. So let's say this is what we have. Let's say I have two inputs. I have x1, I have x2, x1, I have x2, and I have, let's say, my y. And then we have my predicted value y hat. This is nothing but w1 x1 plus w2 x2. So let's say the values are 10, 5, 8, 12, 6, 3. And then let's say w1 value is 1 and w2 value is 2. And let's say this is 25. And let's say this is 30. Let's say this is 15. So quickly, is w1 is 1 and w2 is 2. Assume. The first step is assume or randomly initialize w1 and w2. We have randomly initialized w1 and w2. You can initialize with any values that you want, but then we have to keep continuously changing these values to see what's the best. A typical hit and trial approach will ask us to keep randomly changing these values, but we don't know how to change those values. So one approach that is commonly suggested is that ignore what these values are. Just kind of assume that they are w1 and w2. So if, for example, you were to make a prediction, what would this prediction be? So forget about the fact that this is W1 and W2. Forget the fact that it is 1 and 2. Let's say this is W1 and this is W2. So what would this prediction be over here? So it's going to be 10 times W1 plus 5 times W2. Similarly, this is going to be 8 times W1 plus 12 times W2. And this is going to be 6 times W1 plus 3 times W2. So this is the actual value. This is my predicted value. What would be the error? Error is going to be the actual value minus predicted value. So it's going to be 10 times W1 plus 5 times W2 minus 25. Similarly, in this case, it's going to be 8 times W1 plus 12 times W2 minus 30. In this case, it's going to be 6 times W1 plus 3 times W2 minus 15. Doesn't matter y minus y hat or y hat minus y, it wouldn't really make a difference. Actual minus predicted minus actual, it wouldn't matter because what we are doing is we're essentially going to, you can do a y minus y hat or y hat minus y, it doesn't matter because what we're going to do is we're going to compute MSE, mean squared error. This is error. So if I were to compute a mean squared error, then I'm going to compute an error square. So the error square is simply going to be the square of all of this. And then I need to sum up all of these values and then divide it by 3 because I have 3 values over here. Mean of the squared error, right? So the mean of the squared error in this case is going to be 10 times W1 plus 5 times W2 minus 25 the whole square plus 12 times W2 minus 30 the whole square plus 6 times W1 plus 3 times W2 minus 15 the whole square, the whole thing divided by 3. That is my mean of the squared error. This part is just the error. This is the square of the error. And then I'm doing the mean squared error of the whole thing, of my complete model. This is my mean squared error. Now, if my model were to be really good, if I were to assume that my model is really good, what should happen? My MSE should be minimum. Hopefully 0, but at least the minimum possible value, as minimum as it can possibly get, right? I want this to be as minimum as it can possibly be. So to compute the minimum, so exactly the numerator has to be 0. 0 is like the best possible case, guys, but I don't know if we can really hit a 0. So that's essentially why I'm saying I want it to be as minimum as possible. Preferably 0, but at least it has to be as minimum as it can possibly get. So I need to find, so my problem now has become find W1 and W2 such that my MSE is minimum. That's my problem. All of us agree on this? This is linear regression, guys. I'm not doing anything different here. This is simple, plain linear regression, right? Ordinary least squares. Now, from here, what do? What we do is we say that there are multiple ways of solving it from here, but because we would want to solve it the ordinary least squares approach, what we generally do from here, anyone? What do we do from here? Because I want it to be minimum. What is the best approach towards finding my minimum? I differentiate, absolutely. Hit and try is one approach, Kundan. I can try the hit and try approach. My hit and try will take me forever because then I'm basically searching in the dark. I'm not solving, I'm not optimizing. I'm searching for it in the dark. I can try hit and try approach, but it'll just take me forever to solve it. So the best way is to leverage some kind of mathematical approaches over here. What if you actually look at this? If you actually look at this, so I want to kind of establish this intuition in you guys as well, and that's one of the reasons why I'm doing this. So if you observe this one, this complete equation with W1 and W2, what is the degree of this equation? Forget about the 3 in the denominator. Just look at the numerator part. What is the degree of this particular equation? When I say degree of the equation, what is the maximum power? Right? What is the maximum index that we can get to? 2. Yeah. So when you have something of this form, right? Something like y is equal to ax square plus bx plus c. It's very similar to this, right? It's just that you may not have a bx term over here, but you could have something like it. But because in this particular case you have w1 and w2, in this case you have both w1 and w2. This particular thing is a polynomial. Will look like a, if for example you had something like this. Let's say you had MSC is equal to, or let's say I simply put y is equal to ax plus b. This is a simple straight line. But if you have y is equal to ax square plus bx plus c, then you basically have a parabola. It looks like this. This is like 8th standard mathematics, 9th standard mathematics case. I'm not reinventing the wheel here. This is how the nature of this particular curve will look like. It'll look like this based on the value of a and b. It'll look like this, or look like this, or look like this. It depends on the value of a and b. The point that I'm trying to drive here is that the value of when an equation looks like this, it your final outcome will basically the curve will more or less look like this particular form. Will look like a parabola. We call this as a parabola. But when you have y is equal to ax1 plus bx2 plus c, so in this case, how would your curve look like? Anyone? What would this be? It'll be a plane. In this case, it'll look like a plane. Yeah. So this is x1, this is x2, and this is y. This is how the plane would look like. If you don't know about this, it's okay, folks. It's absolutely fine. I think you just need to kind of sing along and just learn that when something looks like this form, when you fit a linear regression equation with multiple features x1 and x2, you're essentially fitting a plane. Yeah, just learn that. Similarly, when you have y is equal to ax1 square plus bx2 square plus cx1 x2 plus d, when something looks like this, if this looks like a parabola, what would this look like? Anyone? What would this look like? This is again same x1, x2, and this is y. Any guesses? If this looks like a parabola, how should this look like in 3 dimensions? Not a circle. Yeah, it look like a bowl. Yeah, you're right. Basically look like a bowl. Think of it like a bowl. A parabola in 3 dimensions. It's like a bowl. Think of it like a doll. Yeah. So that's how this is going to look like. Okay. The point that I'm trying to drive here is that this equation that you see over here basically looks like this. It's just that instead of x1, x2 is essentially going to be w1, w2, and here it is going to be MSE. That means for different values of w1 and w2, you're going to have different kinds of errors. If you pick this particular value of w1 and this particular value of w2, you'll have a certain amount of error, right? You'll have a certain amount of error. Similarly, if you pick different values of w1 and w2, you're essentially going to get different values of MSE. I want to pick a certain value of w1 and w2. I want to pick a certain value of w1 and w2 in such a way that I get the lowest possible error. I want to pick a certain value of w1 and w2 such that I get the lowest possible error. Okay, how do I get that? The simplest of the simplest math tells us that if you were to kind of get the lowest or the minimum most point, the best way to do it is you differentiate this particular equation. Here, this is the part where things can get a little tricky, guys. So if you haven't understood all of this, it's okay. So just like a background. But what we are saying here is that if you want to find the minimum value of, so I want to find the values of W1 and W2 such that my MSE is minimum. That's the fundamental point. So how do I get this? The way I'm going to get this is by differentiating my MSE.
Let's have a quick quiz question, guys. And the question is, what is the concept of deep learning in AI? And your options are a teaching for training neural networks with many layers, a method for unsupervised learning in complex environments, a framework for representing knowledge in a hierarchical structure, or a process of fine-tuning machine learning models using reinforcement. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
Equating it to 0. Similarly, dou MSE by dou W2 equal to 0. So I'm going to differentiate this equation 2 times with W1 and with W2. We call these as partial derivatives. This is the part of uh, AI which requires you to learn a little bit of math. This is all 10 standard mathematics, guys. We are not learning something which is beyond 10 standard by any means, right? Um, so it's okay if you're struggling here a little. The point is that to get to the minima, to get to the minimum most value of this particular sphere, what I'm saying is that I want to get to the minimum most value of this particular sphere. I want to get to here. I want the values of W1 and W2 where the sphere is at the bottom most. Why the bottom most? Because when it is bottom, that means my MSE is minimum. How do I get there? The best way to get there, according to certain concepts of math, is that the best way to get there is by computing partial derivatives. So you can compute the partial derivatives like how you see here, dou MSE by dou W1 and dou MSE by dou W2. And that way it will give you, if you compute the partial derivative of this equation and partial derivative of this equation with W2, you're going to get two linear equations. So two linear equations with W1 and W2. So two equations and two unknowns. Then you can solve for W1 and W2. Two equations, two unknowns. So you will get basically equations that look like this. So you'll get basically something like 8W1 plus 5W2 is equal to 0, and 6W2 minus 5W3 is equal, 6W1 minus 5W2 is equal to 8. You'll get two equations like this. I mean, these are arbitrary equations, of course, that I've currently put. With these two equations, do you think we can solve for W1 and W2? Absolutely. What you can do is you can just add. So you can simply cancel 14 W1 is equal to 8. So W1 is equal to 8 by 14. If W1 is equal to 8 by 14, take W1 and substitute it back in this equation or any one of these equations, you will get the value of W2. So 5W2 is equal to minus 8W1. So W2 is equal to minus 8 by 5W1. And so W2 is equal to minus 8 by 5 multiplied by 8 by 14. So this is my W2 value. So this is W1 and W2 values correspondingly. So with these values of W1 and W2, what we are saying is that work with that values of W1 and W2, this network will give me my best possible model. With the values of W1 and W2 that I kind of was able to extract here, I will be able to build my best possible network or best possible linear model in this particular case. Yeah, let me just repeat that once again for the benefit of everyone. There are a few parts that I've skipped, and we'll learn about those in more detail as we go along. But simply put, what we are saying is that I hope all of us have been able to follow until here, right? So there is historical data. This is historical data, right? This is historical data. I already have this data with me. So I'm trying to fit a linear equation, this is my model. I want to find those values of W1 and W2, which will give me my lowest possible value or my best possible model. So if assuming W1 and W2, these are going to be my predictions. So if my model were to be perfect, that means this error that I compute, mean squared error, has to be the lowest. So if my error has to be the lowest, then what I need to do is that I need to make sure that I compute the best possible values of W1 and W2 such that my MSE is minimum most, because they are the only two variables here. There's nothing else over here. Based on the values of W1 and W2, the value of MSE will be determined. So if my W1 and W2 should be in such a way that my MSE is minimum. Generally speaking, this equation basically looks like this curve, right? Because for different values of W1 and W2, as my W1 and W2 values are going to change, my predictions, as my W1 W2 values are going to change, the error is going to change as per this particular parabola that you see, paraboloid that you see over here. So but I want to get to the bottommost point. I want to basically get the W1 and W2 values in such a way that my MSE is the minimum. I want to get those W1 and W2 values such that the MSE is the minimum. How can I get there? The best way to get there is by computing partial derivatives. Why am I computing partial derivatives? Because when you compute a partial derivative or your first order derivative, Vishal, both mean the same. When you basically compute your partial derivatives, what you are computing is you're basically computing the slope of the equation. The slope of the equation simply means that, at this particular point, if you see the slope, there is no slope, there is no tilt of that particular equation. If you compute the tangent in this direction and in this direction, in both directions, the slope is almost zero, right? So that's what I'm saying. I want to get to a point where my slope is zero. So when you actually when I actually perform the partial derivatives of this particular equation, you're going to get two equations. I don't know if these are the equations. These are random equations that I put. Because these are second degree, when you solve, you're going to get first degree equations. So you get these two equations. You solve for these two equations, you'll get W1 and W2. So what I'm saying is that these W1 and W2 values are the values that are going to give you your least possible error. Least possible error means best possible model. That is the complete science behind whatever we've just done. Okay, this is just assuming W1 and W2, just two weights that we've solved for right now. Are all of us okay until this particular point? So that's a problem that we're going to learn as we go along. We will learn about scenarios like global minima, local minima, saddle points, and all of that. But in general, what we are saying is that because in this particular case, because with just W1 and W2, it is pretty straightforward. It's always going to look like a parabola. But at times you may also have at times you may have multiple minima, right? When you have more number of weights, you may have multiple minima, and that's where a problem gets a little tricky. We'll get there, Siddharth. We'll talk about that as we go along. The problem might not be so simple when we do deep learning. When we do neural networks and actual deep learning, the problem may not be so trivial. The calculations may not be so simple. Right now, we're just assuming two weights and no hidden layers, so it's pretty straightforward. But when you have hidden layers and when you have everything else, things can get a little more trickier. And that's exactly where your issues of local minimum might also come in. Do these kind of equations really help us in corporate world? I think my take on it is very different. I mean, I think at the end of the day, you're learning a concept, uh, and data science and ML and AI, the concepts that we're currently learning, they're all a combination of math and techniques and computer science and business. So it's a combination of everything. Um, we haven't discussed something over here that requires us to learn engineering mathematics, right? So we haven't learned something that is completely out of the world. We're just doing 10 standard mathematics. So just to kind of give you an intuition, all that we've discussed right now is just 8th, 9th, 10th standard math, and then we'll try to keep it at this particular level. I mean, the idea is not to go down a research route. The idea is not to make this math heavy and sound overly cool or overly complex. No, that's not the point. The idea is, and on a daily basis, you're not going to do any of this. This is basically just to understand the concept of what is actually happening under the hoods. Under the hood, how is the problem getting solved is basically what I'm trying to explain. Uh, we can actually solve these problems even without knowing all of this. But I think because we're investing some time in learning, let's kind of learn it the right way. That's my opinion, Parvesh. But to be honest, I mean, we can also solve all of this even without learning all of this. I mean, I can simply say that, hey, look, you can the way you actually solve for this is by using a specific function in Python or TensorFlow, and then you can get it up and running with it. But I don't know if that will really serve the purpose. I can simply do functions in Python, but that way I don't think I would really be imparting a lot of knowledge. Now think about this. Given this kind of a setup, this kind of a scenario, now that we've learned how to actually solve for a single layer neural network, and now that we've been able to solve for a very very simple problem like what we see on the screen, the next question is, how do we learn when we have multiple hidden layers? When we have multiple hidden layers, the problem is all the more complex, because then you're not simply solving for W1, W2. This equation is just not going to be W1, W2. This equation will be way more complex. If this equation becomes way more complex, this curve is not going to look like a parabola anymore. This will be a way more complex surface, right? Take a sheet of paper, hold it on both sides, and twist the paper in either direction, right? So take a piece of paper or a piece of cloth, and then you twist it from either sides in different directions. The kind of surface that it creates is the kind of is the kind of surface that you're going to have. We call these as hyperplanes, right? This is a simple plane, but imagine somebody is holding this plane from this direction, and somebody is holding in this direction. You're twisting it here in this direction, twisting it in the other direction from either side. Think of the kind of surface it will create. So you'll see a lot of bumps and a lot of crests and a lot of troughs and all of that, and we call those as hyperplanes. So when you have more weight, when you have more weight, and more complex equations get created. More complex equations means that this will not simply be a parabola or a paraboloid anymore. This will be a super complex surface. When this becomes a very, very complex surface, the solution is not going to be so trivial. So there we will have to make a lot of approximations. We will have to make a lot of approximations. So the point that I'm trying to say is that as deep learning as you keep adding more and more layers, the problem you're is going to become more and more difficult to solve. You will require more and more computational power to solve those problems. That is why somebody asked me yesterday, why do we need GPUs to solve deep learning problems? The reason we need GPUs to solve these problems is because when you're solving a 10 layer deep neural network, and in each layer, if you have, let's say, like 50 or 60 hidden layers, sorry, nodes in each layer, imagine the number of weights that you're solving for, and imagine the kind of complexity that is under the hood. It'll be super duper complex. And then when it is super duper complex, when it becomes so difficult, the amount of what do you say, the amount of computational power that is required, your CPUs will not be able to provide that. And that's exactly where GPUs come in. And GPUs will help us solve them in a much more efficient fashion. Yeah, so I mean, you guys can actually go through it and let me know if these are the two equations. You've gone the additional mile to come up with these equations. So yeah, I mean, you can actually solve for these two equations. You'll have a lot of online solvers. Like for example, you'll have a lot of simultaneous equation solvers online. You can just plug in uh, your stuff. So something like this, 400 W1, and then the other one was Y. I'm just putting X and Y for simplicity. X. Yeah, so the values of X and Y are, man, who cares about all of this? Give me the answer. Yeah, see, there you go. So your W1 is 15 by 8 and your Y is 5 by 4. W1 is 15 by 8 and W2 is 5 by 4. So 15 by 8 is how much? 15 by 8 is approximately around 0.9. Sorry, 1.9-ish. And then 5 by 4 is 1.25. 1.25. Yeah. So you could use W1 and W2 values. So we've been able to kind of sort of represent the neural network model or the linear regression model using the neural network framework. And then we've also learned how the coefficients of the neural network of the linear regression model essentially translate into the weight of a simple simple perceptron, a neural network, of course, without a lot of hidden layers. And then we've also learned how to actually go about solving for a simple linear regression problem, like how you would solve like how you would solve a classic single layer perceptron or a single layer neural network. And then we've learned, the process of how to actually solve for a linear regression problem, and then how you could how partial derivatives are really going to help, and eventually we've computed the weights and all of that. We've also learned that adding yeah we've also learned the impact of adding um, newer and additional hidden layers in between. We've also learned that adding additional hidden layers is going to increase the complexity of the model and actually going to help us capture more and more patterns, because we're doing some kind of feature engineering, or automated feature engineering by taking linear combination of features. And that way, once we kind of capture the linear combination of those features, we can then build a model which is slightly more complex. And we learned that over here, when we said that adding these two additional nodes is going to basically help us add more complexity to our model. Uh, Building a model with just raw features is uh, is is going to be lesser accurate than a model which is enhanced with additional features in this particular case. Uh, so this is where we are. We still haven't really dwelled into the depths of neural networks, but we're getting there. I think we're slowly building up to it. We will get there. Now, I hope we're all okay until this particular point. I hope the learning is. I hope we're all sort of fine until this particular point, and we sort of understand where we're headed towards. Brilliant. So back again. Now, let's just go back here, and then let's just start looking at how the hidden layers are going to help us enhance the model. Until this particular point, we haven't really added any hidden layers, but then we'll start slowly learning about how hidden layers are going to help us start solving problems. So, but before we get there, I'm just going to add one more additional challenge to you guys. If you're solving for a classification problem, let's say you have x1, x2, same, but instead you have, let's say, your y, but this time your y is, let's say, a 0 or 1, right? You don't have a numeric outcome, but instead you have a 0 or 1. Your simple model will look still like this. Simple perceptron would still look like this. You have x1, x2, and then you have y, but this y in this particular case is not going to be straight a linear combination. It's not going to be a simple linear combination. It's not just simply going to be W1, W2. It's not simply not going to be W1 X1 plus W2 X2, because if it is W1 X1 W2 X2, you're then simply going to get, you're simply solving a linear regression problem. But if you want to convert this into a probability, if you want this to kind of your predicted value, if you want it to be either 0 and 1, one of the things that you will then need to do is, if you want it to sort of return a probabilistic outcome, one of the things that you need to do is you got to apply you basically need to apply a sigmoid transformation over here. Hence your outcome will, instead of just being y, you'll have to apply something like this. It's going to be 1 by 1 plus e to the power of minus, uh, with a sigmoid transformation, w1 x1 plus w2 x2. Yeah, nothing very different. It's just that except for the direct outcome over here, it's going to be w1 x1 plus w2 x2. Similarly, these things are going to change. Here you're not going to compute MSE. Here you're not going to compute MSE, because if it is a linear regression problem, you can compute MSE. But if it is a classification problem, if it is a binary class classification problem, Mayank, you're absolutely right. If it is a two class or a binary class classification problem, then you're not going to compute MSE. What is the error that you're going to compute? What is the error that you're going to compute here? You're not going to minimize MSE, because mean squared error works really well if it is if it is a linear regression problem. If it is a classification problem, and if you're trying to validate the outputs, if you're trying to compute the errors that have occurred, you would then be doing it via confusion matrix is at a much later point, Kundan. But to actually build the model and optimize for W1 and W2, we compute something called as log likelihood, or you will also come across something log likelihood or maximum likelihood, right? You might also come across something called as log loss. These are different terminologies for the same thing, but essentially what we are trying to optimize for over here is that we are trying to optimize uh, for basically a binary loss. We're not trying to optimize for a numeric loss, but rather a binary loss. Okay, everything will be the same. It's just that instead of doing an MSE, we would be using another function called maximum likelihood or log loss. That's the point that I wanted to drive. Okay, cool. Back again here. So now, so we have a simple x1, x2, two inputs, and instead of a direct output, let's say you have a hidden layer. You have a hidden layer, and these hidden layers are basically like this. Um, the best way to, and similarly from here to here, and from here to here, and then these outputs are then going to simply help us get from here to there. Okay. Um, Now this is your the the most obvious way of sort of representing this is from a naming convention standpoint. Well, different people represent these names differently. uh, from a naming convention standpoint, people call this W11 because it goes from the first node of this layer to the first node of this layer, and this is called as W12 because it goes from the first node of this layer to the second node of this particular layer. This is going to be W21 and W22. Yeah, and then you could basically call this W3 and W4. That's a decent naming convention, so to say. um, Now, as I said, the value of h1, and I'm going to call this h2, and this is your final output layer. This is, let's say, y, right? So anyone, what is going to be the value at h1? W11 times x1 plus, because W11 times x1, this is from here to here and this as well. So these are two inputs that are coming in. Similarly, W21 times x2. Similarly, for h2, the value is going to be W21 times x1 plus W22 times x2. And your value at y, your output is going to be, what is going to be the value at y? W3 times h1 plus W4 times h2. Remember one point, that until this particular point, we haven't added any kind of a bias term. We haven't added any kind of an intercept term. Remember intercept? When we talk about linear regression, we say y is equal to mx plus c. We haven't added any of the c terms yet. We will add that as we go along. Let's not worry about that right now. But just remember that you will have one more term everywhere. So instead here, you're essentially going to have C1, C2 plus C3. Essentially, you're going to have one more constant terms all throughout. Yeah, so for now, for simplicity purposes, I'm not really taking them into considerations. Okay, for the purposes of the simplicity sakes. So this is what your values at H1, H2, and Y are typically going to look like. Okay, the way you could, H2 is going to be, I'm really sorry, guys. Thank you. Thank you. Who can it? Parvesh, thanks so much, man. Yeah, this is 2-1. Sorry, W12. W12. Perfect. So the way this is also represented, right? You could also basically represent the value of h1 and h2 with, in some form of a matrix representation as well. And we will learn that as we go along. So people also represent it with w dot x, summation sigma w into x, where w and x are two vectors, right? W1 x1 is what they also refer to this as. Uh, Essentially what I'm saying is that this could basically look like this as well. So you could basically have one row, two columns, sorry, W11, W21, and then you can have x1 and x2. So when you do this, this is basically one row, two columns, and two rows, one column. This would basically return one single value for you. You could represent it using a matrix representation as well. Similarly here as well, W12, W22 times X1, X2. And here, this is going to be W3 and W4 times H1, H2. And then you can simply represent it using a numeric representation as well. This is a matrix product, matrix multiplication. Now, assuming that because in this particular case, we just have like two weights flowing into H1 and H2, it sort of becomes very easy. But at times what may happen is that because there are multiple weights, you might have multiple weights, and this might actually become much bigger. And this might actually also become much larger as well as we go along. So your weight matrix can also become larger. Your X1, X2 also might become larger. Net, the point being that uh, the best way of kind of visualizing these matrices and these computations is by using matrix representations. So you will see that as you go along in a lot of places, in a lot of literature, you will see that instead of just representing the computation using a simple math like this, people prefer representing it using matrix representations. That way, it's sort of easier for people to understand that you have two weights and two X1, X2s, and or rather two inputs and two weights. So the combination is what we see over here. Also, what people generally do is that instead of representing it this way, they also say that the hidden layer values are W11, W21, W12, W22, and multiplied by X1, X2. So when you do this, this is basically a 2 by 2 matrix, and this is a 1 by 2 matrix. Sorry, 2 by 1 matrix. So this would return again H1, H2 values. This would basically return H1, H2 values. You can also represent this whole thing. I mean, this layer computations can simply be represented like that. Okay. Yeah. So that's the other thing that I wanted to sort of represent as well. Cool. I hope we're all clear until this particular point. Now, going back to the computations that we just saw, just a second, just want to clear some space. So to make it more easier for us to understand, at times what people also do, because to kind of make the math a little more, rather the feature generation. So H1, H2, as you observe, are like the intermediate hidden layer values that are basically getting generated. And we all know that the reason why we are doing this is because H1, H2 are basically going to give us additional complexity, are basically helping us add additional layers or basically additional features that are getting created at the background. And that's one of the benefit of having your hidden layers. So instead, what people also do at times is they say that, okay, why should I just do a linear combination? Can I not just apply some kind of a function on top of this? You know, instead of just doing a linear combination, I'll apply some kind of a function on top of this, right? I'll apply another function on top of this. And instead of just taking the outcome as it is, I'll apply some other function on top of this, right? So why do I just want to take the values as is? Why do I just want to take a linear combination? Instead of just doing a linear combination, I can actually do much more than just a linear combination. I can actually take a linear combination and apply a function. So if you remember your support vector machines or from your previous learning, one of the things that support vector machines does is that SVM adds certain functions in between that helps us or performs something called as a kernel transformation. Do you remember something called the kernel transformation? A kernel transformation is basically nothing but instead of just using the features the way they are, you transform your features into a higher dimension. You apply a function and you transform your features into a higher dimension. By doing that, what happens is that you gather some kind of an additional non-linearity. You basically get some additional non-linearity into your data, or your model starts to represent more non-linearity. And the way you achieve that is by adding these kind of additional functions. So instead of just taking a linear combination, you take a linear combination. Additional to that, you apply some kind of a function. These functions that we apply, these functions that we apply are called as activation functions. Okay? Why do we apply these functions? Again, the reason why we apply these functions is because even if you don't apply those functions, the combinations are still linear. So you will really not get the kind of benefit that you want. So if you really want to capture a lot of non-linearity, that means then you require functions which are more non-linear in nature. So rather than just doing a simple addition and multiplication, if you're able to apply more complex functions, like for example, apply a sine transformation or a tan, a hyperbolic transformation, apply some kind of complex transformation functions on top of your existing data. That way, what you will get is instead of just fitting, just basically fitting y is equal to w3 h1 plus w4 h2, you're basically fitting y is equal to some complex function times w3 h1 plus w4 h2. Here it is simply not a linear combination, but because you're applying an additional function, this model, the final layer, could actually be a much more complex representation of your input layer. So that way you're capturing more non-linearity within your data. Does that make sense, everyone? Do we all understand why we are applying an activation function over there? The reason why we apply activation functions is because it will help us capture more non-linearity. Hidden layers already are helping us capture non-linearity, but if you want to capture more amount of non-linearity, larger amount of variability within your features, you apply more functions. If you apply more functions, then your your models are even more complex. Yeah, does that make sense? So just to kind of give you an intuition, if for example, in a simple linear model representation without a hidden layer, let's say forget about a hidden layer. Here, let's say I'm applying an activation function. Let's say the activation function is a sine transformation. Let's say the activation, or rather, forget about a sine transformation. Let's say I'm using, let's say, a square transformation. This is x1, this is x2, this is w1, this is w2, and this is y. If I did not have an activation function here, what would we have? We'll simply have y is equal to w1 x1 plus w2 x2. Simple linear model. But when I put an activation function over here, I'm saying square this thing. Now my function is going to be w1 x1 square plus w2 x2 square plus 2 w1 x1 x2 w1 w2 x1 x2. This. Now if when you compare y is equal to w1 x1 plus w2 x2, when you compare these two, this is the first one and this is the second one. Can you tell me which of these two models is more complex? Everyone, the first one? Do we all agree that the first one is more complex than the second one? Correct, exactly, right? So more complex because you're able to capture, this is more non-linear, right? This is just fitting a line. This is basically fitting a curve. So between this and this is much better than this model. This is simply fitting a simple straight line, while this is actually like a curve, like a parabola sort of a thing, because it's second degree. So this will basically look like a parabola, something like this or something like this. So clearly this is a better model than the other one. Yeah, that's the whole point about applying activation functions. So when you apply an activation function, suddenly what happens, data which was previously just getting represented in a straight line, or a model which is just fitting for data in a straight line, now suddenly starts to fit for a more complex dimension, more complex shapes. If you apply an activation function, what may happen is that your your model performance time may go down. That means the computations will become more complex because you'll need to apply more and more functions. So the time that is taken for actually doing the computations is higher, but it'll increase accuracy because you're building a more complex model. Yeah, cool. So, and imagine instead of just applying that activation function at the last layer, by the way, we are already applying an activation function for the last layer in the case of a classification problem. Can you tell me what function are we applying in the last layer? That for a classification problem, we are already applying an activation function. A sigmoid activation. Absolutely right. A sigmoid activation is a is also another activation function, because you're trying to get that non-linearity. Yeah, as simple as that. Because if you just do w1x1 plus w2x2, it's a simple straight line. But if you apply the if you apply the transformation, what it does is it basically transforms that into a sigmoid curve. This is a non-linear function. That's the whole point of performing of applying activations. Patterns that you couldn't capture earlier with simple linear combination can be captured using activation. Yeah, I mean, the choice is ours, right? Sigmoid is one activation function, but then there are a ton of other activation functions that one can apply. The question is, can I apply any activation function? Yeah. So the question is, so can I apply any possible activation function? I mean, can I apply any activation function? Like, for example, can I apply a sign transformation? That means anything that comes out of a node, I'll apply a sign transformation to it. Or anything that comes out, I will just, let's say, apply some kind of a cosine transformation to it, or a tan transformation to it. Can I apply any transformation that I want? Can I apply any activation that I want? Well, while we would want to apply anything that we want, there are certain traits that an activation function should have. There are certain fundamental traits that an activation function should have. And one of the traits that an activation function should have is the fact that they should be differentiable, they should be continuous, and all of that. There are certain mathematical traits that an activation function should have. The reason why it should be differentiable is because we are computing. If you remember, we are computing. We're computing some kind of partial derivatives in between. So we want to make sure that we apply a certain kind of functions which make our computations also easier. You don't want to kind of put all possible load on the computers. You want to apply such kind of functions which make the computations also a little easier. So you can apply any function you want, but it's just that you have to keep certain things in mind. Things like, firstly, whatever function you apply, you have to make sure that the functions are continuous and differentiable at different points. You don't want to apply discontinuous functions. Like, for example, you don't want to apply something like a modulus transform or other kind of transformation. You want to apply functions which have certain specific traits, and one of those is the fact that they have to be differentiable. And there are certain other key elements that we have to take into consideration. People have gone about uh, identifying different kinds of activation functions. For all you know, this is an active area of research, right? As we speak, there is probably some guy sitting on some corner of the world trying to figure out what is, trying to research a new activation function. So you can come up with your own activation function someday and put it against your name. I will be proud to say that you were a part of my class back then. The point being that activation functions are an active area of research. Everybody comes up with newer activation functions, and there's so much that's going on in that space. Uh, but historically and empirically, people have done a lot of research and they've identified a certain set of activation functions which are very, very effective.
Just a quick info, guys. Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka, IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.
So let's start with machine learning interview question. Here is your first question. It is a kind of pretty basic question, and the question is, explain machine learning, artificial intelligence and deep learning. It is very common to get confused between the three in-demand technologies, which are machine learning, artificial intelligence and deep learning. These three technologies, though a little different from one another, but are quietly interrelated. While deep learning is a subset of machine learning is a subset of artificial intelligence. Some terms and techniques may overlap in these technologies and it is quite easy to get confused among them. So let's learn about these technologies. If I talk about machine learning involves various statistical and deep learning techniques that allows machines to use their past experiences and get better at performing specific tasks without having been to be monitored. If I talk about artificial intelligence uses numerous machine learning and deep learning techniques that enable computer systems to perform tasks using human-like intelligence with logic and rules. If I talk about deep learning, then deep learning comprises of several algorithms that enable softwares to learn from themselves and perform various business tasks, including image and speech recognition. Deep learning is possible when systems expose their multi-layered neural networks to a large volume of data. I hope so guys, you would have got brief idea regarding machine learning, artificial intelligence and deep learning. So our next question is, what is the difference between bias and variance in machine learning? The answer to the same question is that bias is the difference between the average prediction of a model and the correct value of the model. If the biased value is high, the prediction of the model is not accurate. Hence, the bias value should be as low as possible to make the desired predictions. If I talk about the variance is a number that gives the difference of predictions over a training set and an anticipated value of another training sets. High variance may lead to large fluctuations in the output, therefore a model's output should have a low variance. If you could see in a diagram, you could see the following trade-off. So here is a bias and variance trade-off. Here is a desired result in the blue circle at the center. If we get off from the blue section, then the prediction goes on wrong. I hope so guys, you would have got a brief idea regarding the difference between bias and variance in the machine learning. Now let's move on to our next question. Our next question is, what is clustering in machine learning? If I talk about clustering is a technique which is used in unsupervised learning that involves grouping data points. The clustering algorithms can be used with a set of data points. This technique will allow you to classify all the data points into their particular groups. The data points that are thrown into the same category have similar features and properties, while the data points that belong to a different group have distinct features and properties. Statistical data analysis can be performed by this method. Let us take some of the examples. Some of the examples can be k-means clustering. If I talk about the k-means clustering, this algorithm will be commonly used when there is a data with no specific group or category. K-means clustering allows you to find the hidden patterns in the data, which can be used to classify the data into the various groups. The variable k is used to represent the number of groups the data is divided into, and the data points are clustered using the similarity of features. Here, the centroids of the clusters are used for labeling new data. Another clustering algorithm can be mean shift clustering. If I talk about the mean shift clustering, the main aim of this algorithm will be to update the center point and the candidates to be mean and find the center points of all the groups. In mean shift clustering, unlike k-means clustering, the possible number of clusters need not to be selected as it can be automatically be discovered by the mean shift. So here are some of the examples of the clustering algorithms. I hope so guys, you would have got a brief idea regarding what is clustering in machine learning. Now let's move on and discuss our next question, which is, what is linear regression in machine learning? This is the most popular questions which is asked in the machine learning interview. Now let's discuss the answer of the same. Linear regression is a supervised machine learning algorithm which is used to find the linear relationship between the dependent and the independent variables for predictive analysis. Here the equation can be, consider y equals to a plus b dot x, where x is the input or the independent variable, where y is the output or the dependent variable, and a is the intercept and b is the coefficient of x. You can see here the diagram with best fit shows that the data of the weight y or the dependent variable and the data of the x of the independent variable. Here the straight line shows that the best linear relationship that would help in predicting the weight of the candidates according to their height. To get this best fit line, the best values of a and b should be found. By adjusting the values of A and B, the errors in the prediction of Y can be reduced. This is how the linear regression helps in finding the linear relationship and predicting the output. I hope so guys, you would have got a brief idea regarding what is linear regression in machine learning. Now let's move forward and discuss our next question. Our next question is, what is decision tree in machine learning? If I talk about the decision tree, a decision tree is used to explain a sequence of actions that must be performed to get the desired output. It is a hierarchical diagram that shows the action. This algorithm can be created for a decision tree on the basis of the set of hierarchy of actions. In the above decision tree diagram, a sequence of actions has been made for driving a vehicle with or without license. So you can see how the decision tree algorithm works in the machine learning domain. I hope so guys, you would have got a brief idea regarding what is decision tree in machine learning. Now let's move forward and discuss our next question. Our next question is, what is overfitting in machine learning? Actually, overfitting happens when a machine learning has an inadequate dataset and tries to learn from it. So overfitting is inversely proportional to the amount of data. For small databases, overfitting can be bypassed by the cross-validation method. In this approach, a dataset is divided into two sections. These two sections will comprise the testing and training dataset. To train the model, the training dataset is used, and for testing of the model for new inputs, the testing dataset is used. This is how we can avoid the overfitting. I hope so guys, you would have got a brief idea regarding what is overfitting in machine learning. Now let's move forward and discuss our next question. Our next question is, what is hypothesis testing? If I talk about the hypothesis testing, machine learning allows the use of available dataset to understand a specific function that maps the input to the output in the best possible way. This problem is known as a function approximation. Here, the approximation need to be used for the unknown target function that maps all plausible observations based on a given problem in the best manner. Hypothesis in machine learning is a model that helps in approximating the target function and performing the necessary input to output mappings. The choice and configuration of algorithms allow defining the space of the plausible hypothesis that may be represented by the model. In hypothesis, the lower h is used for a specific hypothesis, where the uppercase H or the capital H is used for hypothesis space that is being searched. So this is what exactly the hypothesis testing is. I hope so guys, you would have got a fair idea regarding what exactly is hypothesis testing. Now let's move forward and discuss our next question. So our next question is, what is the difference between supervised and unsupervised learning? If I talk about the supervised learning, the algorithms of the supervised learnings used the label data to get trained. The model takes the direct feedback to confirm whether the output that is being predicted is indeed correct. Moreover, both the input data and the output data are provided to the model, and the main aim here is to train the model to predict the output upon receiving the new data. Supervised learning offers accurate results and can largely be divided into two parts, which is classification and regression. If I talk about the unsupervised learning, the algorithms of the unsupervised learning use unlabeled data for training purposes. In unsupervised learning, the models identify hidden data trends and do not take any feedback. The unsupervised learning model is only provided with input data. Unsupervised learning's main aim is to identify hidden patterns to extract information from the unknown sets of data. It can also be classified into two parts, which is clustering and association. Unfortunately, unsupervised learnings can offer results that are comparatively less accurate. I hope so guys, you would have got a brief idea regarding what is the difference between supervised and unsupervised learning. Now let's move on and discuss our next question. So our next question is, what is Bayes' theorem? If I talk about the Bayes' theorem offers the probability of any given amount to occur using the prior knowledge. In mathematical terms, it can be defined as a true positive rate of the given sample conditions divided by the sum of the true positive rate of the said conditions and false positive rate of the entire population. Two of the most significant applications of Bayes' theorem in machine learning are Bayesian belief networks. This theorem is also the foundation behind the machine learning brand that involves naive Bayes classifier. So as you can see the formula here, P of A by B equals to P of B by A dot PA divided by PB, where P of A by B is a probability of occurring B given the evidence B has already occurred, where P of B by A is equals to probability of B occurring given the evidence A has already occurred. Here PA is a probability of A occurring and PB is a probability of B occurring. I hope so guys you would have got the idea regarding what is Bayes theorem. Now let's move on and discuss our next question. So our next question is, what is PCA in machine learning? If I talk about the multidimensional data, it plays an important role in the real world. Data visualization and computations become more challenging with increase in the dimension. In such scenarios, the dimension of data might have to be reduced to analyze and visualize it easily. This is done by removing irrelevant dimensions and keeping only the most relevant dimension. This is where the principal component analysis is used. The goal of the PCA is to find a fresh collection of uncorrelated dimension or orthogonal and rank them on the basis of variance, which defines the process of PCA in machine learning. I hope so guys you would have got a brief idea regarding what is PCA in machine learning. Now let's move on and discuss our next question. Our next question is, what is SVM in machine learning? If I talk about SVM or support vector machines, it is a machine learning algorithm that is majorly used for classification. It is used on the top of the high dimensionality of the characteristic vector, which basically defines what SVM is in machine learning. I hope so guys you would have got a fair idea what are support vector machines in machine learning. Now let's move on and discuss our next question. So our next question is, what is cross-validation in machine learning? If I talk about the cross-validation allows a system to increase the performance of a given machine learning algorithm which is fed a number of sample data from the dataset. This sampling process is done to break the dataset into smaller parts that have the same number of rows, out of which a random part is selected as a test set and rest of the parts are kept as a train sets. Cross-validation consists of the following techniques, which can be hold-out method, k-fold cross-validation, stratified k-fold cross-validation, and leave p-out cross-validation. I hope so guys you would have got a fair idea regarding what is cross-validation in machine learning. Our next question is, what is entropy in machine learning? The answer to the same question is, entropy in machine learning measures the randomness in the data that needs to be processed. The more entropy in the given data, the more difficult it becomes to draw any useful conclusion from the data. For example, let us take the flipping of a coin. The result of this act is random and it does not favor heads or tails. Here, the result of any number of tosses cannot be predicted easily as there is no definite relationship between the action of flipping and the possible outcomes. I hope so guys, you would have got a brief idea regarding entropy in machine learning. Now let's move forward and discuss our next question. Our next question is, what is epoch in machine learning? If I talk about epoch in machine learning, which is basically used to indicate the count of passes in a given training dataset where the machine learning algorithm has done its job. Generally, when there is large chunk of data, it is grouped into several batches, and all these batches go through the given model, and this process is referred to as iteration. Now, if the batch size comprises the complete training dataset, the count of iteration is same as that.
Let's have a quick quiz question guys, and the question is, which of the following is an example of an ethical concern related to AI? And your options are optimizing resource allocation in the healthcare using AI algorithms, or enhancing cybersecurity measures with AI-based intrusion detection systems, or developing AI-powered virtual assistants to improve productivity, or ensuring fairness and avoiding biased AI decision-making processes. Please mention your answers in the comment section below.
Of epochs. In a case, there is more than one batch which is equals to d dot e equals to I star b, which is a formula where d is a data set and e is the number of epochs and I is the number of iterations and b is the batch size. So you can remember d dot e equals to I dot b, where d is a data set, e is the number of epochs and I is the number of iteration and where b equals to batch size. So this equation generally defines the relationship between epoch, dataset, iteration and number of batches. I hope so guys, you would have got a fair idea regarding what is epoch in machine learning. Now let's move on and discuss our next question. Our next question is, what is the variance inflation factor? The variance inflation factor is the estimate of the volume of multicollinearity in a collection of many regression variables, where VIF equals to variance of the model divided by variance of the model with single independent variable. That's it for variance inflation factor. I hope so guys, you would have got a brief idea regarding what is variation inflation factor, and it is one of the most important questions which can be asked in a machine learning interview. Now let's move on and discuss our next question. So our next question is, what is a confusion matrix? If I talk about the confusion matrix, it is used to explain model's performance and gives the summary of predictions of classification problems. It assists in identifying the uncertainty between classes. Confusion matrix gives the count of correct and incorrect values and error types according to the model, where you can see accuracy is defined as TP plus TN divided by TP plus TN plus FP plus FN. I hope so guys, you would have got a fair idea regarding what is confusion matrix. Now let's move on and discuss our next question. So our next question is, what is the type 1 and type 2 error? Type 1 error is false positive, is an error where the outcome of a test shows the non-acceptance of a true condition. For example, suppose a person gets diagnosed with depression even when they are not suffering from the same. It is a case of false positive. If I talk about the type 2 error or false negative is an error where the outcome of a test shows the acceptance of a false condition. For example, the CT scan of a person shows that they do not have a disease, but in fact they do have a disease. Here the test accepts the false condition that the person does not have the disease. This is a case of false negative. I hope so guys, you would have got an idea regarding what are type 1 and type 2 error. Now let's move on and discuss our next question. So our next question is, when should classification be used over regression? Both classification and regression are associated with prediction. Classification involves the identification of values or entities that lie in a specific group. Regression entails predicting a response value from the consecutive set of outcomes. For example, if you want to predict the price of a house, you should use regression since it is a numerical variable. However, if you are trying to predict whether the house situated in a particular area is going to be high, medium or low priced, then the classification model should be used. I hope so guys, you would have got a fair idea that when should you use classification over regression. Now let's move forward and discuss our next question. So our next question is, explain logistic regression. This is also one of the most asked questions in a machine learning interview. So logistic regression is a proper regression analysis when the dependent variable is categorical or binary. Like all regression analysis, logistic regression is a technique for predictive analysis. Logistic regression is used to explain data and a relationship between one dependent binary variable or one or more independent variable. Logistic regression is also employed to predict the probability of categorical dependent variables. Logistic regressions can be used in the following scenarios. So here are some of the examples, such as to predict whether a citizen is senior or not, or to check whether a person has a disease or not. I hope so guys, you would have got a fair idea what exactly is logistic regression. Now let's move on and discuss our next question. So our final question is how to handle missing values in a dataset. So if I correctly answer this question, in Python pandas, there are two possible methods to locate the lost or corrupted data and discard those values. The first function is null. It can be used for detecting the missing values. The second one is dropna, where it can be used for removing a column or row with null values. And there is also another which is called fillna, which can be used to fill all the void values with the placeholder values. I hope so guys, you would have got a fair idea regarding how to handle the missing values in a dataset.
Just a quick info guys, Intellipaat offers advanced certification in data science and AI in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you can learn all the important concepts of data science and AI from esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in field of data science and AI.